bird dummy load is good for 500 watts for like a half an hour. So I'll get a camera going and we'll put 100 watts into it and see what happens. Okay, we've got the two birds set up. I've got a transceiver ready to go. Up on top is an N8LP, LP100A, also a highly accurate peak reading watt meter. And we're going to see what these 3 watt meters show when I key this transceiver. Well, they're going to show the same, and if so, how much? So keying it, the LP100 says 104 watts. The two birds also showing about 104 watts. So there's a max power on the Yaesu FT450 getting 104 watts, and likely that's exactly what's going out. Now, what happens when you switch to SSB? The rule of thumb that we used to use was, when I was a kid, double the meter reading when you're talking on SSB, and that'll show you what the full scale meter reading is. So let's test that. This bird has a peak reading device in it. This is a peak reading watt meter. This one does not have it. So this will be the one that we're going to look at. I'll try to get out of the way here. What will that one show, since it's not a peak reading watt meter? In other words, if I'm running 100 watts single sideband, what will that meter show, since it's not a peak reading watt meter? And that's the case in most linear amplifiers and other devices. The plate current meter, grid current meter, screed current meter, and other things, they're not peak reading. They're just reading, I don't want to say average, because that's not the case. So I'm going to change modes on this transceiver, the SSB position, and if you'll notice, occasionally I've got 115 watts output on the LP100. No, make note of that, because that's one of the reasons for doing this video. Is key down it did 100 watts or 104 watts, but its peak output is going to be higher. So when you tune up an amplifier or an antenna tuner, you may find that your output is higher. There's 115, 121 watts. 100 watt transceiver puts out 121 watts. Now, I'm going to put that meter into the peak reading position. Now the bird is showing about the same, about 115 watts on peaks. So it matches the LP100, both peak reading meters. This one with a transistorized device in it is reading pretty much in line with the LP100. Now over here is the bird watt meter, and I've got the mic gain set to max. It's all the way up, which you shouldn't do, but we're doing this as a test, and I'm into a dummy. It is showing about 25 watts. So if I double that, the power out is 50 watts, and that would be the old way of calculating, but it's not. It's more than 4 times that. On average, it runs about 5 times what the meter indicates if it's not an amplified peak reading meter. Why is that important? Well, let's say you have a linear amplifier and you tune it for 400 watts. And let's pick a number. Let's say 200 mils of plate current. You may actually be peaking an amp at times, not the whole time, but some of the time, causing a lot of distortion. Case in point, a neighbor bought 2 tubes for his linear amplifier, put them in, and they went flat after a couple of weeks, a month of operation. So we got 2 more from the manufacturer, and they went flat after a couple of weeks. If you've seen some of my videos on tuning up an amplifier, I recommend turning the load control and advancing it beyond where the peak output occurs. And that's because there's 115 watts. That's because your peak output is going to exceed what you can put doing just a carrier. Now to show it again, I've got 1, 2, 3, 4, 5, 115 watts, 120, there's 114. Let's put the transceiver back in carrier position, key it, see how many watts. they're all showing 104 watts or 105 watts. So again, key down 104 watts, it's actually putting out about 10% more and sometimes 20% more. So if you're tuning up an amplifier and you're exceeding by 20% grid current, plate current, screen current, tubes are going to be ruined in short order. Along with that, you're going to be splattering, or the transceiver will be splattering because the amplifier is tuned up at one point, and it also could be an older style transmitter where you literally tune it up. What's the message here? Well, first of all, a meter that's not amplified or has some circuit in it to make it read peaks, it's probably going to show 20 to 25%, maybe 10% of what the peak reading really is, because it just can't move fast enough. Digital meters are another story. There's no inertia. They go right up. It's all, it's got an amplifier in it. This is a highly accurate meter. And as you can see, when I keyed it, it showed 104 or 5 watts, and so did the birds. Oh, if you recently got new tubes for your amplifier and you flatten the other ones in a few months' time, it's probably not the tubes. It's probably the way you tuned it up. If your friends and neighbors are telling your signal's broad, it again may be that when you look at the ALC meter, which is how you set the mic gain, is with the ALC meter. If you've set the mic gain so that the ALC meter is full scale, I guarantee you it's going way past that, and you are going to be splattering, which is one of the reasons why I recommend keeping the ALC meter to about 1/3 scale, and that's what a lot of the instruction books also recommend. I hope you found that interesting. If you have a comment or if you have an idea about how this test should have been done or a suggestion or a question, put it below. If you haven't subscribed yet, please do. I'm really happy with the number of subscribers. We're approaching 16,000, which is just terrific. I'm Jim, W6LG for Hammer Deal Basics. Thanks for watching. See you the next time.
Okay, so we're going to demonstrate the use of an antenna matching unit to get this station ready to make a contact on 20 metres. Some radios, like this IC7300, do have an internal antenna matching unit, but that might not be suitable for the full range of antennas that you want to use. In this case, we're going to use an external one. You can get manual models, like this, or an automatic model. Similarly, some of them have an internal SWR meter, or you can add one externally. Here we'll use the single needle external SWR meter. So we'll switch the radio on and set it up on the 20 meter band. First of all, we'll make sure that we find a frequency that nobody else is using. We are going to be transmitting a carrier while we tune the antenna, and so we don't want to be interrupting anyone else's contact. That sounds clear. We're going to need to transmit a carrier constantly, so I'll change to the FM mode and also reduce my power level to about 10 watts. You don't want to be transmitting any more power than you really need. There we go. We're now ready to start setting up the antenna matching unit. So I'll start transmitting. I'm going to use this external SWR meter. We'll start off by changing the function to the calibrate position and use the cal knob to set the needle to the calibrate mark on the right hand side of the scale. I'll then switch to the SWR position and we can read off our SWR on the top scale, which is about 4.5 to 1. That's not what we want. We're trying to get it down to as close to 1 to 1, or the far left-hand side of the display, as we can. I'm now going to start matching the antenna. And I'm going to use these 3 different controls: transmitter, antenna, and the roller inductor. And I'm going to need to use each of those in turn to try and minimize our SWR. We're aiming for 1 to 1, which is on the far left of the screen. I'm now going to go to the first control and try and adjust that to see a dip. So I've got the lowest value I can using these 2 controls. Now I'll come on to the third control. You can see that's slowly coming down. Oh, and now if I carry on, it goes back up. So I'll look for the lowest point and then come back to my first 2 controls. Each time I'm cycling through the 3 controls to get the lowest value I can. And here, you can see if I switch to cal, we're still at the right-hand side at the calibration mark. Switch back to SWR, and I'm now at an SWR of 1 to 1. This is now ready to make my contact on 20 meters.
Is the frequency is, one more time, is the frequency is W6LG.
Whiskey 6 Lima calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf. CQ, CQDX beaming JA Whiskey 6 Lima Golf. W6LG calling CQDX, CQ, CQDX. CQDX calling CQDX. Beam towards Japan, Whiskey 6 Lima Golf. Whiskey 6 Lima Golf calling CQ, CQDX. CQ, CQDX calling CQDX. Beaming JA, Whiskey 6 Lima Golf. Whiskey 6 Lima Golf calling CQ, CQDX. CQ, CQDX calling CQDX, beaming Japan. Whiskey 6 Lima Golf, W6LG listening.
Juliet Alpha 0, Delta Charlie Queen.
Hey, good afternoon. JA0 Delta Charlie Queen. I think I got that right. Yeah, Delta Charlie Queen, Whiskey 6 Lima Golf. Takashi, nice to hear you. 5x959, my name is Jim. Japan, India, Mexico, Jim. And I'm in California. JA0 Delta Charlie Queen from Whiskey 6 Lima Golf. Dozo.
Returning, Jim. Very good morning to you. Or I should say good afternoon or good evening over there. Thank you very much for coming back to my call. And maybe it's just a good condition, but you are much stronger than you usually are. Your condition is very familiar for me. Anyway, you have 5 and 9. 5 and 9. It's into Nagano, Japan. Yes, my handle is Takashi, Tango Alpha, Kilo Alpha, Sierra Hotel, India. Takashi is my handle. Also, I'm glad to know that my signal is 5 and 9 over there in California. Here, it's cloudy, but sometimes we are able to see sunshine among the clouds. Temperature about only 0 plus minus 0 degrees C out of the doors. How copy over there? Jim-san, W6LZ, Juliet Alpha 0, Delta Charlie Queen. Microphone back to you.
Okay, Takashi-san, nice to meet you. Anyway, yeah, you're 5x9, 59. I've got 2 4-element Yagis, 8 elements in total for 20 meters, pointed towards JA, and some phasing lines to one of them. The Yagis are about 20 meters apart. Transceiver's an Elecraft K3, and I'm using a homemade amplifier. So what is your antenna? JA0 Delta Charlie Queen, Nagano Whiskey 6 Lima Golf near Sacramento, over.
Sorry, the copy, W6LZ in Sacramento, Juliet Alpha 0, Delta Charlie Queen in Nagano, returning 100% copy. Your signal is coming in here remarkably. Always 5 and 9, your last transmission. Now I know your gears are excellent. Sounds good. K3, it's also a familiar transceiver for me. Anyways. Okay, microphone back to you, Jim. W6LZ, JA0 Delta Charlie Queen. Put it back to you.
Okay, arigato, Takashi-san. Nice, strong signal. J0DCQ, Nagano Whiskey, Nagano. I'm not saying that right. I'll try the next time. W6LG. Very good.
Okay, I enjoyed talking with you. Also, if I could speak English more fluently, I could have more delighted you. Anyway, okay, thank you so much. Wonderful QSO. Whenever I have a time, I'm on the band. If you can hear me, please call me again. May I say sayonara, W6LZ, JA0 Delta Charlie Queen. どうもありがとうございました。Catch you later.
Okay, I did understand every word with no problem, Takashi, so thank you very much. Thank you. I've really enjoyed it. I see you're also Alpha Italy 6, Florida, England. That's poor phonetics, but I think you understand. 73, my friend. Take care. Hope to see you again soon. JA0 Delta Charlie Queen, sayonara. W6LG, arigato.
Oh, you spoke fluent Japanese. Your Japanese sounds really natural. So, sayonara.
Bye-bye.
Hi, I'm Jim, W6LG, your ham radio Elmer here on YouTube. Welcome to my radio room in Rockland, California. This is a box that I maybe there's others like this out there. I simply don't know, but I want to mention a couple of things that I think are really important with regards to this box. Number one, this cord is says on it 14 gauge, 14 AWG. It says 3-14 AWG. So it's a 3 conductor. So 14 gauge. 14 gauge by US standards, as far as I know, is good for 15 amps. The plug on this box, it's got a nice long cord, and there's a plug, and it's a molded cord, and the plug. And note that the plug is a standard 15 amp plug, and I'll bring that up on the screen too. So that's a standard, if it'll focus, and maybe it won't. There we go. And it says right on it 15 amps. Now, what I want you to note is the writing on this box, the printing says 120 volt AC, 25 amp, 3000 watts maximum. Okay, the cord is a 15 amp cord, but it says 25 amp. And so 120 volts, 25 amps, sorry, can't hold it still, 3000 watts. All right, that's something I'm not real happy about. Here's something I'm less happy about. There's the fuse, if I can get it to focus. Got to get it in the right spot. Okay, there's the fuse. AC line in, ground, fuse. 30 amp. So to go over that again so it's real clear and get me back up on the screen. A 15 amp cord, 15 amps max. A 30 amp fuse protecting the 15 amp cord. The outlet in a wall, the wall outlet for that matter, is in a typical residence, unless the outlet has other purposes. Generally speaking, it's going to be a 15 amp, going to be wired with 14 gauge wire, 14 gauge non-metallic cable, sometimes called Romex. Occasionally outlets are 20 amp, and if they're 20 amp, one of the prongs on the plug is vertical and the other one's horizontal. So a 20 amp plug has a different configuration in the US. In this one, they're both vertical, which is 15 amps. The cord is 15 amps. The fuse is 30 amps. 30 amp fuse protecting a 15 amp cord. It also says that the implication is that these are 25 amp outlets. They're not. They're a standard 15 amp outlet. So these are 15 amp outlets. It says, if I get my fingers in the right place, 25 amps. The cord is 15 amps. The plug is 15 amps. The fuse is 30 amps. So what do you think? 30 amp fuse, 15 amp cord. I think what I may do is not use this box, or if I were going to use it, I would take the 15 amp fuse that I happen to have on the shelf and put it in there, tossing the 30 amp fuse. I did look, it is a 30 amp fuse. So the math altogether doesn't add up, because it says 3,000 watts here, but a 30 amp fuse times 120 volts in the US would be 3,600 watts. The cord is capable of handling, according to my understanding, 1,800 watts. So I've got 1,800 watts here, 3,600 watt fuse, and it says 3,000 watts here. And again, the implication is that each of these outlets is good for 25 amps. They are 15 amp outlets. If you have any questions or comments, or if you think my math is not quite right, let me know. Post a comment. Explain your thoughts about this box. In the meantime, for me, it's what the heck were you thinking? To the manufacturer. What in the world? I'm Jim, W6LG in Rockland, California.
Like many others, I live in a crowded place with more neighbors than space around the house. While this is a good thing for a quality life, it is less than satisfactory for a ham radio operator. There are mainly two solutions to this dilemma: a divorce with a move to a remote location, or a remote station. Because I love my wife, a remote station is a proper solution. Today we will cover one of the most critical topics of such a project. Connect the flex radio at the remote station to our shack PC at home. Fortunately, we can use the same technology to connect securely to our home network from everywhere without the hassle of OpenVPN or WireGuard. Secure, simple and free of charge. So, this knowledge is valid for most of us. Hello wireless enthusiasts. Here is the channel with the strange Swiss distortion in the signal with a new video around wireless and other exciting stuff. Remember to subscribe if you do not want to miss the following emissions. While many possibilities like OpenVPN or WireGuard exist, these possibilities do not properly work for remote locations, for sure not with a flex radio. They also need a public IP address or a DIN DNS service and port forwarding. Not easy to install. We will use M0ODZ here, a new class of VPN software, to avoid this hassle. Let's start with a simple scenario. We want to connect our smartphone and laptop to the home server running Home Assistant via a VPN. As a first step, we must create a free account on M0ODZ.com. Then we are asked to create a new network. It automatically gets a name, but we will call it Home, And we want to be it a private network where we can select who we want to connect. If your network were public, everybody could connect to it. Next, we choose one of the proposed IP address ranges. That's it. We created our private and encrypted network that spans the whole internet. Its ID is here. Now we can start to add nodes. The first I add is my laptop because I want to securely connect it to my home network. For that, I have to install the zero-tier client on my laptop and start it. The laptop got an address, and we can connect to our freshly made network by entering its ID. Returning to our management console, we see that one device wants to join. If we check this box, our laptop is connected. To connect to my Home Assistant server is also a piece of cake. We search the zero-tier add-on and install it. Before we start, we have to enter our network ID. I had to add it in a YAML file, but I assume it should be possible to add it here. After the start, your server appears in the zero-tier console, and we can accept it as we did before with our laptop. Just a tip. Never delete a device. I did it and was no more able to recreate it. I had to create a new network to solve the issue. So better hide it if you do not need it anymore. The iPhone is connected the same way by installing the zero-tier app. Now you can securely check your home automation from the McDonald's Wi-Fi. The newly created VPN assigned these addresses and shows the physical addresses of the devices. You see, my Surface and the iPhone have different IP addresses than my home network. Because I wanted to simulate an on-the-road situation, I tethered my Surface via my iPhone. Can I connect to my Home Assistant with this address? Yes, I can. Cool, it works, without DIN DNS and port forwarding. We could add as many devices as we wanted. 25 nodes are free of charge. You can stop the video now if you only wanted to connect your home network. All others can join the challenging ride until the remote network, including a cellular router and a beefy 4G antenna, is placed at the remote location to connect to the Flex radio. What is the next problem to solve? We need a cellular router. I choose the industrial cellular router RootX14 from Teltonika because one of my colleagues recommended this brand. The RootX14 supports Cat12, which means 600 megabits per second download and 150 megabits upload speed, and therefore probably is an overkill for this application. But Teltonika was so kind to sponsor this device for my tests. And they did much more for the success, as we will later see. I choose 4G because for the moment I did not want to depend on 5G. Because of political reasons, its rollout is not as fast as we would like. But before we drive to the remote station, I want to be sure that my Flex radio works across a mobile connection. So first we have to connect the router to the mobile network. This is easy. Just buy a SIM card and insert it. After boot, these RG45 connectors are connected to the internet. So if you just need an internet connection without VPN for your camper, for example, you are done. And because the RootX14 offers a Wi-Fi access point, you can connect all your gadgets via Wi-Fi and enjoy fast internet via 4G. For our remote station, we need more. We must create a new zero-tier network called Remote Station with our Shack PC and the Flex radio. Connecting the Shack PC is simple. Just install the zero-tier client and connect it to the ID of the Remote Station network. But what about the Flex radio? We cannot install a zero-tier client to connect it to our network. So was the whole idea with zero-tier not good? Fortunately not. Teltonika included a zero-tier client in the router. Because the RootX14 also offers a WireGuard client and I did not know of zero-tier, I tried it and failed miserably. Because there are not enough IP version 4 addresses, Mobile operators use tricks to connect millions of smartphones to the internet without assigning a public IP address to all of them. They use carrier-grade NAT. That, as you can read here, blocks all sorts of port forwarding, with the effect that usual methods like OpenVPN and WireGuard often do not work. Zero-tier is a different weapon. It can conquer even CGNAT. What a relief! The only thing you have to do is to install a client on every node and accept it into your network. Let's continue with our project. Unfortunately, we forgot something. Do you spot the problem? Yes, you're right. As we learned before, the Flex Radio is no PC and we cannot install a zero-tier client. Not good. What to do? We have to ignite stage 2. Instead of only connecting our router to zero-tier, we connect the whole network behind it. We add an address range and tell zero-tier that this network can be reached via the route X14. With this trick, all devices on the remote LAN are connected to my shack PC. Now we can ping the Flex, and it answers. Incredible! We could also connect a Raspberry Pi or an ESP32 to the remote network. And they would behave like they were in our shack. Let's check if the Flex Radio works. The radio already runs and we were able to ping it. So Smart SDR should auto-discover the radio and start to display lovely waterfalls. But no, nothing happens. Not as expected. I tried and tried, but without success. In my misery, I called Thomas from Teltonika for help. And because he is a viewer of my channel, he helped me instead of having lunch. I already knew that Flex Radio uses the Vita49 protocol for discovery. And Vita49 uses the data link layer in addition to the network layer. Fortunately, zero-tier offers to bridge also the data link layer to our remote network. Just tick Allow Ethernet bridging. Unfortunately, this is still not sufficient. After much digging and head scratching, one of Teltonika's support engineers found the solution. Somehow, he created 2 subsegments and bridged them. It is too complex for me to understand, but it is easy to build once you have the blueprint. This is why I leave a link to a document where you see all the needed settings. If you stick with the same network numbers, it should work in less than half an hour. If I start Smart SDR now, it immediately discovers the radio connected via the mobile network and the route X14. Now we can drive to the remote site to test our connectivity. You see, this little house is remote and no neighbors are around. And you see that we can profit from the antennas already in place. Now we have to do tests to find out if our dream becomes true. The router has 4 antennas because modern cellular systems use horizontal and vertical polarized signals to increase speed. We first used the out-of-the-box setup with 4 antennas. Unfortunately, the signal was poor and the up and download speed was only a few megabits per second. Not what we had hoped. We would not be hams if we would not find a solution to that problem. As usual, we need a bigger antenna. Teltonika sells an outdoor antenna with 4 connectors. The antenna is perfect for mounting on the roof of a camper. We mounted the antenna outside, but it was not a big help because it is omnidirectional. So we had to shift gears. And this is what we got a few days later. These 2 directional antennas, one for horizontal and one for vertical polarization. I connected one cable to the main and one to the aux connectors. And now we started to point toward the different cellular towers. We discovered 3 significant variables. The first was the company we bought the SIM card from, because not all had usable towers in our area. The next was the signal strength, which is heavily influenced by the propagation and distance to the next tower. The third was the utilization of the tower, because the tower's capacity is shared with all its users. A high-performance tower in a crowded area sometimes delivers a lower speed than a slower one in a remote location, because we have to share with fewer people. Of course, the usage of such towers fluctuates a lot, and we have to monitor the performance over time and maybe adapt our choice. We found the best upload speed at towers in the 3 to 5 kilometer range. Not close, but we got a good signal with a direct line of sight and directional antennas. The speed test of the router shows upload speeds of around 25 megabit per second. We do not know how much speed we need for a decent user experience with the Flex Radio, but I read that much lower speed should work. After mounting the antennas, we connected my Flex Radio to our new setup, and really it works. Perfect. We will continue with a permanent installation and add a kill switch for the radio, because it is required by law. So we were able to create a VPN to safely access our home server without any hassle by using zero-tier. We were able to connect a Teltonika Route X14 4G cellular router to our zero-tier network, conquering CGNAT of our mobile carrier. Connected a whole remote network segment to the network. Bridged the data link layer to make the Flex Radio work on the remote location. And finally, with the help of 2 logarithmic periodic antennas, we got a decent 4G signal to our remote station. This is all for today. As always, you find all the relevant links in the description. 73 to everybody, and please consider supporting the channel by using the links in the description. See you in the next episode.
Whiskey 6 Lima calling CQ low CQ. CQ calling CQ low CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. Been asked many times to go over the extra class exam, and this I think would be a good time. I've got some free time during the holidays. I'm recording this just before Thanksgiving 2018. Hard to believe it's 2018. Going to read each of the questions and only, for the most part, the correct answer. And where I think it's appropriate, I'll explain why that is the correct answer. If I don't agree with the answer, I may talk about that just briefly. But you have to answer the question with the answer that they're looking for. So if I say it's red and they say it's blue, you better answer blue. What I'm hoping is that if you go through these videos with me 2 or 3 times, you should be able to sit down and pass the exam. To that end, I've taken a lot of civil service exams and generally done pretty good. Carefully read the question. Sometimes it helps to read it twice. If you think you know the answer because you saw it in this video and you know it's A, then go ahead and answer A. If the question is one that you haven't seen before or don't remember and can't figure out what it is, just let it go for now and come back to it later. Usually when you look at these questions have 4 potential answers. Usually you can rule out 2 that are just so far away from what makes any sense, and then you're down to 1 of 2 possibilities. And at that point you got a 50-50 shot. Oftentimes there's a key word that's in the correct answer, so look for that very carefully. And sometimes that key word is in the question, and it's also in the answer. If you can't figure it out, makes no sense, then put down C as a last resort. So go through the exam, answer the questions that you can, leave, put a question mark next to the other ones, or just leave it, come back to it later. Read the question word for word. What I used to do was to tap my pencil on each word to make sure I didn't leave a word out, because you may read it as this is the correct answer when it maybe is asking you which is the incorrect answer. So just those two letters can make all the difference. So read it word for word. The other thing too is be real positive. If you have a chance to go sit in the room before you take the exam, maybe if you know where it's going to be, if it's in a local facility, go there. If it's in the library, go there and sit down. When you go in, be real positive. Be thinking that you are going to pass. You are going to get this. You're going to do it. I'm going to get all the questions right. So having said all that, keep a positive attitude. Read the questions very carefully. If you don't recognize it, see if you can rule out two of the answers, and then you're down to one of two possibilities. If you have no clue as to what the answer is, usually it's C. Small advantage that way, but if that's all you got, that's all you got. All right, let's start. I've got 3 monitors set up, one attached to a camera, and over on this one I'll be looking away, but this has this monitor, which I can switch to, has all the questions. And so I'm going to go through with this video E1. The sections are the following. E1 is Commission FCC rules. E2 is operating procedures. E3 is radio wave propagation. E4 is amateur practices. E5 is electrical principles. E6 is circuit components. E7 is practical circuits as opposed to impractical circuits. E8 is signals and emissions. E9 is my favorite subject, antennas and transmission lines. They've labeled it E0, but let's call it E10, and that's safety. So here we go with the first question, sub-element, they call them sub-elements, E1. I'll read them quickly, and I'll read just the correct answer, and I'll give a brief explanation as to why I think that's the correct answer. E1 A01. When using a transceiver that displays the carrier frequency of phone signals, which of the following displayed frequencies represents the highest frequency at which a properly adjusted upper sideband emission will be totally within the band? Very poorly worded. The answer for this exam is going to be 3 kilohertz. They're assuming a bandwidth on single sideband of 3 kilohertz. So keep that in mind because it's going to come up again. E1A02. When using a, by the way, that was D. E1A02. When using a transceiver that displays the carrier frequency of phone signals, which of the following displayed frequencies represents the lowest frequency at which a properly adjusted lower sideband emission will be totally within the band? And again, the answer is D, 3 kilohertz above the bottom edge. The reason why I object to that answer is some signals are wider than 3 kilohertz on single sideband. E1A03. With your transceiver displaying the carrier frequency of phone signals, you hear a station calling CQ on 14.349 megahertz upper sideband. Is it legal to return the call using upper sideband on the same frequency? The answer is no, because you'll be outside the band. Remember, we're talking about 3 kilohertz wide, top of 20 meters is 14.350. So the answer is C, no, the sideband will extend beyond the band edge. And they're talking about the upper band edge. E1A04, with your transceiver displaying the carrier frequency of phone signals, you hear a DX station calling CQ on 3.601 megahertz lower sideband. Is it legal to return the call using lower sideband on the same frequency? The answer is no. The sideband will extend beyond the edge of the phone band segment. So again, if you're on 601, it's going to extend down a total of 3 kilohertz. E1A05, what is the maximum power output permitted on the 60 meter band? The answer is C, 100 watts PEP effective radiated power to a half-wave dipole. They mentioned gain compared to an isotropic radiator. A dipole has 2.14 dB gain, so I guess that's why that's there. But anyway, it's 100 watts PEP to a dipole. E1A06, where must the carrier frequency of a CW signal be set to comply with FCC rules for 60 meter operation? 60 meters is channel, so the answer is B, at the center frequency of the channel. E1A07, which amateur band requires transmission on specific channels rather than a range of frequencies? Well, we just discussed that. That's D, 60 meters. E1A08, if a station in a messaging forwarding system inadvertently forwards a message that is in violation of FCC rules, who is primarily accountable for the rules violation? The answer is B, the control operator that originated the message. I stopped because it's rules violation, and I wasn't sure what they were aiming for, but it's the originating station and the control operator. E1A09, what is the first action you should take if your digital message forwarding system station inadvertently forwards a communication that violates FCC rules? And the answer is A, discontinue the forwarding the communication as soon as you become aware of it. Don't contribute to it. Don't make it continue on. E1A10, if an amateur station is aboard a ship or aircraft, what condition must be met before the station is operated? Of course, you have to get permission from the captain or the pilot. So the answer is A, its operation must be approved by the master of the ship or the pilot in command of the aircraft. E1A11, which of the following describes authorization or licensing required when operating an amateur station aboard a U.S. registered vessel in international waters? The answer is B, an FCC license. E1A12, with your transceiver displaying the carrier frequency of CW signals, you hear a DX station on 3.5 megahertz. Is it legal to return the call using CW on the same frequency? No, because you'll be outside the subband. So the answer is C, no. One of the sidebands of the CW signal will be outside of the band. E1A13, who must be in physical control of the station apparatus equipment of an amateur station aboard any vessel or craft that is documented or registered in the United States? The answer is B, any person holding an FCC license who is authorized for alien operation. E1A14, what is the maximum bandwidth for data transmission on 60 meters? And in this case, it's 2.8 kilohertz. Okay, on to the next portion, section B. E1B01, which of the following constitutes a spurious emission? And the answer is D, any emission outside its necessary bandwidth that can be reduced or eliminated without affecting the information transmitted. In other words, an unnecessarily wide signal. And if you're on the bands much, you know that happens a lot. E1B02, which of the following factors might cause the physical location of an amateur station apparatus or antenna structure to be restricted? And the answer is D. It's if the antenna is in a significant American historical, architectural, or cultural location. E1B03. Within what distance must an amateur station protect an FCC monitoring facility from harmful interference? The answer is A, 1 mile. Chances of that happening are pretty slim these days. Okay, E1B0, because they've closed monitoring stations. E1B04. What must be done before placing an amateur station within an officially designated wilderness area or wildlife preserve or an area listed in the National Register of Historic Places? They want to see an environmental assessment to be submitted to the FCC. I don't know if that's a full EIR. I don't believe it is. I was a planning commissioner for a while. I think there's a distinction there. In any case, an environmental assessment report. E1B05, what is the National Radio Quiet Zone? And that's C, around the Radio Astronomy Observatory. E1B06, which of the following additional rules applies if you're installing an amateur station antenna at a site near or a public use airport? So if it's close to an airport, a public use airport. The answer is A, you must notify the FAA and register with the FCC as required in Part 17 for obvious reasons. E1B07, what is the highest modulation index permitted at the highest modulation frequency for angle modulation below 29 megahertz? Don't have a clue. It says B 1.0. I have no idea what that means. Okay, E1B08. What limitations may the FCC place on an amateur station if its signal causes interference to domestic broadcast reception, assuming the receivers involved are of good engineering design? Don't know what TV set that would be, but anyway, the answer is D. The amateur station must avoid transmitting during certain hours on frequencies that cause harmful interference. That's a change from the past. E1B09. Which amateur stations may be operated under the RACES rules, Radio Amateur Civil Emergency Service, and I was the head of that for a while here in Nevada County. The answer is C. Any FCC licensed station certified by responsible civil defense organization. Could be the Board of Supervisors, could be the town mayor, could be the city council, whoever authorizes it. E1B10. What frequencies are authorized to an amateur station operating under RACES rules? Well, the answer is all amateur service frequencies, A. E1B11. What is the permitted, listen carefully to this one, what is the permitted mean power of any spurious emission relative to the mean power of the fundamental emission from a station transmitter or external RF amplifier? I believe it used to be 30 dB. The answer now is 43 dB. To give you a little perspective, 43 dB, 40 dB is a 1 in 4 zeros, so that would be 10,000 times. It's 43 dB, so that would be double that, 20,000 times weaker than the main signal. That's a long way down. Okay, on to the next section, C. E1C01. What is a remotely controlled station? It's a station controlled indirectly through a control link, and that's D, and that's becoming more and more common. E1C02. What is meant by automatic control of a station? The answer is A. The devices and procedures for control. The use of devices and procedures for control so that the control operator does not have to be present at the control point. sort of belabors it. It's just the guy doesn't have to be, the guy or gal does not have to be there. E1C03. How do the control operator responsibilities of a station under automatic control differ from one under local control, hands-on? And the difference is B, under automatic control, the control operator is not required to be present at the control point. E1C04, what is meant by IARP? It's A, and it's not capitalized, and it should be, an International Amateur Radio Permit. I believe that's a certificate that allows U.S. amateurs to operate in certain countries of the Americas. E1C05, when may an automatically controlled station originate third-party communications? When may an automatically controlled station originate third-party communications? The answer is never. E1C06, which of the following statements concerning remotely controlled amateur stations is true? And the answer is C, a control operator must be present at the control point. To read the question again, it is which of the following statements concerning remotely controlled amateur stations is true? A control operator must be present at a control point, and the control point can be obviously somewhere else. Now, well, here we go. EC07, what is meant by local control? And the answer is C, direct manipulation of the transmitter by the control operator. E1C08, what is the maximum permissible duration of a remotely controlled station's transmission if its control link malfunctions? In other words, it just starts to transmit. The answer is 3 minutes. At that point, it has to you have to set it up so it times out. E1C09, which of the following ranges of frequencies is available for automatic controlled repeater operation below 30 megahertz? The answer is D, the top end of 10 meters, 29.5 to 29.7. 29.7 is the upper end of the band. E1C10, what types of amateur stations may automatically retransmit radio signals of other amateur stations? The answer is B, auxiliary, repeater, or space stations. Auxiliary, repeater, or space stations. E1C11, which of the following operating arrangements allows an FCC licensed U.S. citizen to operate in many European countries and alien amateurs from European countries to operate in the U.S.? The answer is the CPT agreement. That's A. E1C12, what types of communications may be transmitted to amateur stations in foreign countries? This, bet a lot of guys would get wrong. It says, what types of communications may be transmitted to amateur stations in foreign countries? The answer is C, communications incidental to the purpose of amateur radio service and remarks of a personal nature. That limits a lot, so keep that in mind. E1C13, which of the following was required in order to operate in accordance with CEPT rules in foreign countries where permitted? And the answer is poorly worded. You must bring a copy of FCC Public Notice DA 11-221. You're not going to bring the copy. You must have a copy. Or take a copy. You're not, well, anyway. E1D, amateur satellites is section D. E1D01, what is the definition of the term telemetry? Recently, I did some telemetry in a hospital. It's a one-way transmission of measurements at a distance from the measuring instrument. So it's a one-way transmission of data. What is the amateur satellite service? And the answer is a radio communication service using amateur radio stations on satellites. E1D03, what is a telecommand station in the amateur satellite service? The answer is B, an amateur station that transmits communications to initiate, modify, or terminate the functions of the space station. In other words, it sends out controls. E1D04, what is an Earth station in the amateur satellite service? This one's a bit tricky because the answer is an amateur station within 50 kilometers of the Earth's surface, intended for communications with amateur stations by means of objects in space. 50 kilometers, okay. E1D05, what class of license is authorized to control to be the control operator for a space station? And the answer is C, any class with the appropriate privileges. E1D06, which of the following is a requirement of a space station? The answer is A, the space station must be capable of terminating transmissions by telecommand when directed by the FCC. FCC says shut it down, you better be able to do that. E1D07, which amateur service HF bands have frequencies authorized for space stations? Basically, the answer is, now we're talking about HF, and the answer is A, 40 and above. So A is only on 40, 20, 17, 15, 12, and 10 meter bands. E1D08, which VHF amateur service bands have frequencies available for space stations? Well, it says VHF, so that is 2 meters. You notice 6 meters is not on that list. E1D09, which UHF amateur service bands have frequencies available for space stations? 70 centimeters and 13 centimeters, that's B. E1D10, which amateur stations are eligible to be telecommand stations? The answer is B, any amateur station so designated by the space station licensee, subject to the privileges of the class of the operator license held by the control operator. So if the space station licensee says it's okay and you can do it within the parameters of the license that you hold. E1D11, which amateur stations are eligible to operate as Earth stations? The answer is D, any amateur station subject to the privileges of their license. Okay, on to section E. E1E01, what is the minimum number of qualified VE volunteer examiners required to administer an element for amateur operator license examination? And the answer is 3D. E1E02, where are the questions for all written U.S. amateur license examinations listed? And they are held by the VEC, so it's C, in a question pool maintained by the VECs. E1E03, what is a volunteer examiner coordinator? And the answer is C. It's an organization that has entered into an agreement with the FCC to coordinate amateur operator license examinations. E1E04, which of the following best describes the volunteer examiner accreditation program? And the answer is D. It's the procedure by which the VEC confirms that the VE applicant meets the FCC requirements to be an examiner. In other words, the VEC says the guy's okay to do it. E1E05, what is the minimum passing score on an amateur operator's license examination? This one I'm sure you know, it's 74% B. Who is responsible for proper conduct and necessary supervision during an amateur operator license examination session? And the answer is all of the volunteer examiners, C. What should a VE do if a candidate fails to comply with the examiner's instructions during an amateur operator license examination? The answer is B, immediately terminate it. You're done. Out of here. E1E08, which of the following examinees may a VE not administer an examination? What person can take the test? And the answer is a relative of the VE. That's C, relatives of the VE as listed in the FCC rules. They define how close a relative is. E1E09, what may be the penalty for a VE who fraudulently administers or certifies an examination? Mine would be, I shouldn't say it. Anyway, revocation of the VE's amateur station license grant and suspension of the VE's amateur operator license grant. In other words, they pull the license, and well, they should. Okay, next question, E1E10. What must the administering VEs do after the administration of a successful examination for an amateur license? And C, the answer is C, they must submit the application document to the coordinating VEC organization according to the VEC's instructions. Sort of goes without saying. E1E11. What must the VE team do if an examinee scores a passing grade on all examination elements needed for an upgrade or a new license? He passed, now what do you do? The answer is B, 3 VEs must certify the exam. Let's see, 3 VEs must certify the examinee is qualified for the license grant and that they have complied with administering the VE requirements. He passed the test and they did what they were supposed to do. E1E12. What must the VE team do with an application form if the examinee does not pass the exam? The answer is A, return the application to the guy taking the test. E1E13. Which of the following choices is an acceptable method for monitoring the applicants if a VE opts to conduct an exam session remotely? The answer is B, use real-time video link and internet to connect with the exam session to observe the VEs. E1E14. For which types of out-of-pocket expenses do Part 97 rules state that VEs and VECs may be reimbursed? The answer is A, preparing, processing, administering, coordinating an exam for the license. Okay, section F. On what frequencies are spread spectrum transmissions permitted? The answer is B, on frequencies above 222 megahertz. E1F02. What privileges are authorized in the U.S. for persons holding an amateur service license granted by the Government of Canada? And the answer is C, the operating terms and conditions of the Canadian amateur service license not to exceed the extra class privilege. In other words, he gets extra class privileges. That doesn't allow him to transmit in the Canadian, well, what would be the Canadian portion of the band, for example, on 20 meters below 14,150. E1F03. Under what circumstances may a dealer sell an external RF power amplifier capable of operating below 144 megahertz if it has not been granted FCC certification? And the answer is A, if it was purchased in used condition from an amateur and sold to another amateur. It's a bit vague, but if an amateur operator and it's sold to another amateur operator, that would also include homebrew amps and that kind of thing. E1F04. Which of the following geographical descriptions approximately describes line A? And it says the answer is A. A line roughly parallel to and south of the U.S.-Canadian border. Not a clue. E1F05. Amateur stations may not transmit in which of the following frequency segments if they are located in the contiguous 48 states north of line A? That must be due to radar. The answer is D, 420 to 430 megahertz. E1F06, under what circumstances might the FCC issue a special temporary authorization, an STA, to an amateur station? The answer is A, to provide experimental amateur communications. Pretty obscure question. E1F07, when may an amateur station send a message to a business? And the answer is D, when neither the amateur nor his or her employer has a pecuniary interest in the communications. In other words, they don't have any money involved. E1F08, which of the following types of amateur station communications are prohibited? The answer is A, communications transmitted for hire or material compensation except as provided in the rules. E1F09, which of the following conditions apply when transmitting spread spectrum emissions? And this is one of the few questions where it's D, all of the choices are correct. The station transmitting spread spectrum emissions must not cause harmful interference. Must be in an area regulated by the FCC or in a country that permits spread spectrum. The transmission must not be used to obscure the meaning of any communication. So it's really pretty strict. What is the maximum, E1F10, what is the maximum permitted transmitter peak power for an amateur station transmitting spread spectrum? The answer is 10 watts. And only 10 watts. E1F11, which of the following best describes one of the standards that must be met by an external RF power amplifier if it is to qualify for a grant to be certified by the FCC? And the answer is D, it must satisfy the FCC spurious emission standards when operated at a lesser of 1500 watts or full power. So if it's capable of 1500 watts, it needs to be there. If it's capable of 600 watts, it needs to be at 600 watts. And again, that's at 43 dB down. E1F12, who may be the control operator of an auxiliary station? The answer is B, technician, general, advanced, or amateur extra. And that was the last question in the first section, or called a sub-element. So in the next video, I'll do the next segment. This one was particularly long. It took about 30 minutes to read. If you have any questions, post them below. If you read a question from someone and you know the answer, please go ahead and answer it. If I made a mistake, let me know so we all know what that mistake is. If you haven't subscribed, please do. Right now I'm at 16,000 plus subscribers and would really like to get it to 30,000. That's my goal. Thanks for watching. I'm Jim, W6LG for M0ODZ Basics. I'll be doing the next sub-element E2 very soon. Thanks for watching. 73 from Wolf Mountain.
Now, sometimes you come across circuits that require matched diodes, whether it's for a balanced mixer or modulator for RF applications, or even something like a guitar effects pedal. So in this video we're going to talk about diode matching and the various techniques that you can use to identify and find matched diodes. We'll talk about a couple of techniques for matching diodes by just using the manufacturing lot when you buy them, or maybe using the diode check function that is in your DMM. That's a simple way to measure them and match them. Or maybe you'd put together a simple circuit with a power supply and a resistor using a DMM to check and match the characteristics of a diode. Or maybe do a more extensive voltage current or IV curve matching technique. And then we'll finally talk a little bit about some other matching considerations that might be important depending on the type of application or circuit you're working with. So let's get started. So the first one is lot matching, and I'll say that it generally doesn't work. I mean, you can oftentimes find diodes that are matched pretty well within a manufacturing lot, but there's really no guarantee, because even the stresses of packaging the devices and things like that can oftentimes change the diode characteristics. So I would say in general, you don't really want to use just simple lot number matching to match diodes. The next easiest one and simplest one is to use the DMM diode check. And in this case, the DMM puts a fixed amount of current through the diode and measures the voltage across it. And this works pretty well, and it's a very, very simple thing to set up. So here I've got my Fluke 87 set to the diode test function. I've got a couple of 1N914 diodes here that came out of a bag that was marked with the same lot. You can see this particular diode measures about 540 millivolts, while this one here measures about 615 millivolts. So the same lot, but not necessarily the same characteristics of that diode. So we can see one of the advantages of this method is it's really quick, really easy. You simply put the meter in that diode test function, connect it up. The downside is it only tests the diode at one forward current. The Fluke 87 I was just using makes about 0.65 milliamps, or about 650 microamps of current to test the diode. I've got a Fluke 79 here that does about 0.6 milliamps, but there's no consistency in the current that's being used. So you might get some misleading results certainly if you test the diodes with different meters. Also, you have to consider that the test current that's being used may or may not be close to the diode current that's going to be used in the particular circuit or application. So that's one of the downsides to this very simple method. Now, oftentimes the higher-end bench DMMs will give you a choice of what current to use to actually go test the diodes. So in the case of this Fluke 8846, we can see that in the diode test mode we have a choice of 1 milliamp or 100 microamps test current. Similarly, on this Keithley 2015, I've got a choice of, in this case, this is the 100 microamp setting, 527 millivolts, and the 1 milliamp setting, 632 millivolts. So in the case of the bench DMMs, you have a choice generally of two, sometimes more, different diode current settings, and that may allow you to pick a diode current that is closer to the particular application that you're going to be using the diode in. Now, if your DMM doesn't have a diode test function, or if the test current it uses is nowhere near the current that's going to be driven through the diode in the application or the circuit, you could use your own power supply, resistor, and DMM test circuit so that you can test the diodes and match them at a diode current that you pick or you specify. Now, the power supply could either be a fixed power supply or even a battery or something like that, whatever you've got around, or a variable lab power supply. The resistor can either be a fixed resistor or even a variable resistor or even a decade box. But at the end of the day, you just want to be able to adjust those two parameters, one or the other, to result in the test current that you want to send through the diode to test it. And of course, that test current is simply equal to the voltage across the resistor divided by the resistor value. And of course, you could measure the resistor with your DMM, you can measure the voltage across the resistor and predict it that way. Or if you simply measure across the diode and resistor combination, that would essentially be your supply voltage, whether it's a battery or a lab power supply. Subtract off the diode voltage and divide it by the resistor value. That gives you your test current. Now, of course, the larger you make the test voltage with respect to the diode voltage, the less precise you've got to be in terms of predicting this up front. You could just use an approximation, 0.6, 0.7, something like that, and get yourself close. So here's our simple setup. I've got a 10K resistor that I measured with the meter at 10.6K, connected in series with my diode under test, connected across a 10 volt power supply. So I can see my 10 volt power supply here. If I measure the voltage across the diode, I see 639 millivolts. So if I take 10 minus 0.639 divided by 10.6K, that gives me about 0.88 milliamps or 880 microamps of test current. Now, of course, if that's not exactly the test current I want, I can adjust the resistor value or adjust the power supply to get what I want. Once I get those test conditions right, then I can swap in additional diodes to see if they all measure that same voltage at that desired test current. So as we just saw, the advantage of this method is that you can pick the test current that you want so it matches your application. The downside is it's a bit more complicated to set up. So let's take a look at a way to alleviate a little bit of that. Now, of course, if you have two multimeters available, you could eliminate the need to have to compute the desired test current by simply measuring it directly. Use one meter as an ammeter in series with your resistor and power supply, and the other simply as a voltmeter across the diode. So now each time you put a new diode in, you can make a minor adjustment to the power supply or maybe a potentiometer being used for the resistor to set the current to be the same for each diode that you put in there and get a very precise match at that particular test current. Fast and easy to measure multiple devices, no computations necessary. The downside is obviously that it requires two multimeters. Okay, so here's the setup with 2 meters. I'm still using the 87 to measure the voltage across my diode, but I'm using the Fluke 79 here as an ammeter in series with my 10 volt power supply. So I'm seeing that same 880 microamps that I mentioned earlier with that 10 volt supply. But let's say I wanted a 1 milliamp test current. I can simply ramp up the power supply here, and let's see, I get up to about 11.3 volts here, and now I'm just over 1 milliamp of test current, and I can actually see my diode voltage now 645 millivolts. So now I can pop in additional diodes, and if necessary, do a fine tune of the current and measure the diode current, or excuse me, the diode voltage for each of my test diodes and find those that match the same voltage for a given test current. Now, one of the downsides of all the methods we've mentioned thus far is that they make the diode voltage measurement at one particular test current. And that's okay if that's the only place where they need to match. Because the reality is that the IV characteristics of the diodes can vary, even within a device family. You can have devices that turn on late but have a very steep turn on. You have devices that turn on early and have a very shallow turn on. And what you'll find is that, for example, at this particular test current, these two diodes have got the same exact voltage. But at a much lower current, they'd have a very different voltage. So it really depends on where that device is going to be used and if it needs to match over a wider range of diode currents. And if that's the case, and that's actually probably most likely the case, you really need to try to match multiple points across that curve. So of course you can do this with some of those previous measurements by making yourself multiple measurements at various test currents and plot them out yourself on paper or with Excel or something like that. But you do have to take into account what those curves look like so you don't get fooled by places where they have the same exact voltage, because they might be quite different when you actually test at a different current level. So again, the techniques would be to use the previous methods to make multiple measurements, or use something like a curve tracer, or even a modern instrument like a source measure unit to actually go make the measurement of these particular curves. Old curve tracers like this Tech 576 often have two test sockets and a switch that allows you to switch between left and right. So you can very quickly switch between two different devices and compare the curves visually on the screen. Let's take a look at the two diodes that we used at the beginning of the video with the simple DMM diode check. These diodes came out of a bag that was labeled with the same lot, but had very different results in the diode check. So I'll start off with one of the diodes here. If we sweep it up here, we can see we're running at 100 millivolts horizontally per division. So just past about a half a volt, we start ramping up, and we're at 200 microamps a division. So right in the middle, we're at 1 milliamp. And we can see where that is crossing here at the 1 milliamp boundary. If we switch over to the other diode, we can see that one is actually quite different. So very different characteristics between these two diodes. So I've now swapped in another diode that matches the first one very, very closely. So if we take a look at the curve for this device here and switch over to the other device, these two curves are very, very close to each other. So by using a curve tracer such as this, it makes it very easy to match the IV characteristics over a wide current range, and that's typically what's important in most applications that require matched diodes. So what other considerations are there when using matched diodes? Once you've established a matched pair, you want to ensure that when you mount them in the circuit that they are maintained at about the same temperature, because there is a pretty strong temperature coefficient, about 2 millivolts per degree C. So you got to watch for self-heating actually when you're actually doing the matching itself, especially if you're matching them at a higher test current. But then also when you mount them in the application, you wouldn't want one of these diodes sitting next to, say, a power regulator chip that gets hot versus the other one sitting away from it next to maybe a low power op amp. You want them mounted in a spot where they're going to be kind of matched in temperature. So here's a simple example illustrating that temperature coefficient or the temperature effect. I got the diode connected up to the meter here. If I simply exhale on it, you can see I made nearly a 10 millivolt change by simply breathing on the diode and changing its temperature. So you do have to watch that when you're applying the circuit in your application. Now the last thing to mention here is to consider the application. You really want to understand why that application needs matched diodes and what does it need to match. Is it a particular voltage current range within the diode curve that he has to match? What's the operating point in the particular circuit? That circuit might actually need the reverse recovery characteristics of the diode to match. Now, we didn't talk about that in this video, but I do have another video that talks about reverse recovery time measurements, and I'll link that down below. For RF or high frequency applications, it might be that the diode junction capacitance is what has to match in order to get the particular characteristics out of that circuit. I do have a video that talks about diode capacitance measurements in my varactor diode video. Again, I'll link that one down below. It might be leakage current or other characteristics that have to match in order for the circuit to work properly. So the bottom line is to really understand the application, what needs to match, and make sure you make those measurements to match those diodes as close as possible to the operating conditions that they're going to see in that application. And so I hope you learned a little something about diode matching and the different considerations that you've got to take into account when matching diodes. If you liked the video, give me a thumbs up. If you're a subscriber already, thank you. If not, please consider subscribing and also clicking the little bell down below the video in the YouTube page to get notified when I post a new video. Thanks again as always for watching, and we'll see you again next time.
Hey guys, I just want to say thank you very much. We had a great POTA session and a live stream. We got all of these contacts. I'll log those up. Thank you all so much. For some reason the stream stopped, the first one, which is fine, but thank you all for stopping by. We are past 450 subscribers. We're now at 488, which is crazy. So thank you all very much. Have a great day everyone. Some threes.
Can you CQ? Maybe, maybe not. Hi, I'm Jim, W6LG. Well, that's a surprise. I'm surprised. So, I'm surprised by the amount. It's crap. And I want to be understood. I'm a communicator, not a broadcaster. Greetings. I'm Jim, W6LG, as you can tell by the call sign growing out of the back of my head. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. Nothing's really more basic than calling CQ, and I hear it done often wrong and in a way that's probably not going to result in an answer. So I thought this would be a good time to talk about calling CQ. Let me give you an example of what I hear, and then we'll get into how to do it, or how I think you should do it. Oftentimes I'll hear somebody say CQ, CQ, KF6, SFS, CQ, CQ. And that's it. And a pause. And if you happen to tune across that guy, first of all, you're not going to know what his call sign is because it was KF6, SFS, and he didn't do it phonetically, and it is at Sierra Fox Sierra, or Fox Sierra Fox, or Sierra X-Ray Fox. Can't tell. So let's talk about some ways to call CQ where you are likely to get an answer, and let's also sort of set a time frame for doing it and a length of time to call CQ. There are, in my view, two types of CQ. One which is just sort of general, you're looking for anybody anywhere, you don't need to say that, but you're just calling CQ, so you say CQ, CQ. There's also a directed CQ where you're looking for a specific area. You might be saying CQDX, which means to me you're looking for somebody that's not on your continent, but if you're in North America, maybe you're pointed at South America, or you're looking for Europe or Africa. You can also say CQ, CQDX Europe to make it really clear you're looking for Europe. If you tune across a guy who's calling CQDX Europe and you're in Canada, it's really not advisable to answer that guy because he's looking for Europe and you're in Canada. And it happens so often when I call CQ that if I'm looking for Europe because the band is open to Europe, 20 meters is open to Europe, then I'll get a guy in Kansas who calls me, and I think, well, okay, I've been saying Europe, you're in Kansas. Anyway, a lot of people have put up videos on how to call CQ, and some of them have said that CQ had nothing to do with seek you, and actually it does. In fact, some of the examples of how to call CQ on YouTube are just way wrong. One guy says you need to be on an even numbered frequency like 14202 or 7202. No. You can be anywhere. We have a neat thing called a VFO, and it can tune anywhere in between. Anywhere on the 20-meter phone band, for example, is fair game. So if you're calling CQ on 14268.5 or 0.68 or whatever, the guy that tuned you in or the gal that tuned you in needs to be able to tune to that frequency. You don't have to be on an even numbered frequency. CQ goes back to radio telegraphy days, and it had a French meaning, meaning an inquiry. I speak no French, don't understand it, can't give it to you, but if you Wikipedia it, you'll see that CQ really was an inquiry call. And it evolved, it was adopted by the United States, and it really did mean CQ, or a general inquiry call. In fact, I've got some plaques that are from the 1920s, and they're falling apart. This one is one that was hanging on the wall in a telegraphy office, and this one happens to have the Q signals on it. One that is overused by us a lot is QSL. I would encourage you not to use that one as much as you can. So here's Department of Commerce, Bureau of Navigation, radio service, and it says General Inquiry Call, CQ. From, and again, it goes to the French language, which controlled a lot of the communications, DE, from, invitation to transmit or go ahead, K, and on it goes. And so a lot of the things that we're familiar with today are in here. Some are very different. Anyway, this was International Morse Code and Conventional Signals. List of abbreviations to be used in radio communications. And again, at this time there wasn't much in the way of voice communication, so these were used on code. I'm a big believer in plain language, and so in a subsequent episode, we'll talk about emergency communications, and these are plaques that I have, awards I have won for participating in real emergencies where stuff went on. I'll read to you this one, which is one I'm most proud of. Whereas Jim Heath displayed extraordinary unselfishness and dedication to the welfare of Nevada County residents in performing above and beyond the call of duty and providing support to the firefighting efforts and in assisting the many residents who suffered losses. That was during the 49er fire in 1988 from the Board of Supervisors. Back to calling CQ. I'm going to call CQ. Let's see who we can raise it. The way I call CQ is I want to do it for about 30 seconds to a minute and not any longer than that. But I'm going to say CQ, Whiskey 6 Lima Golf W6LG, and I'll say that a number of times so that someone listening, especially if it's in Europe, may not be hearing me all that well, and so he'll get the opportunity to get my call sign straight. In the past, I've had some really difficult calls like WB6JZC, and that one was a tough one, so I would repeat that several times. Also, when I call CQ today, I'm going to call just CQ, and I'll indicate which way my antennas are pointed. Because I'm not looking to go over the North Pole, it's not likely that's going to happen at this time of day. So there is a general CQ, and then there's a directed CQ where you're looking for a specific area. And repeat CQ several times. Give your call sign several times. Not in a row, but maybe CQ, W6LG, Whiskey 6 Lima Golf, CQ. Also, before you call CQ, and I almost forgot, ask if the frequency is in use. Somebody may be on there, but he may be listening, and he would hear you really, really well, and he may be in the middle of a contact, and you start calling CQ on top of him, he can no longer hear the guys talking to you. So I try to make it a rule to call CQ, to ask if the frequency is in use 3 times, just to make sure, and if somebody says it's in use, I'll move. That's why I've got a VFO. So ask if the frequency is in use, call CQ, and make it really clear when you complete your CQ call by saying W6LG listening or over, or just something so that if a guy in Europe who's maybe hearing you 4x5 knows that you're through calling CQ. And then in another episode, we'll talk about having a QSO with somebody, engaging that person in a conversation. If you want to have rapid fire contacts because you're at a national park or Route 66 or whatever, that's fine, and then you're 5-9 and you're on to the next one. But if you want to have a contact with somebody, an engagement conversation, ask them what kind of transceiver they're using or what their antenna is or where they are. Any number of things. Try to avoid politics, and there's a reason for that. I'll do that in another episode. But you'd be surprised where it will lead, and sometimes it leads to really amazing contacts where you meet a guy who on the air turns out to live have lived in your hometown, or somebody maybe you knew, or in one case a relative. So where the contact leads can be really interesting. Some guys are really good at engaging a person in conversation. Let's go call CQ, see if we can find somebody, and we'll go from there. So give me just a minute to move things around, and we'll go on 20 meters. W6LG, Whiskey 6 Lima Golf, over.
All right, let's call CQ and see if we can raise. I'm going to do that on 20 meters. I'm going to ask if the frequency's in use first. I'm going to do that 3 times. If I don't hear anybody, then I'm going to go ahead and call CQ, and I'm going to be beaming east with 2 Yagis, and we'll see what happens. So here we go. Is the frequency in use? Is the frequency in use? Whiskey 6 Lima Golf. Is the frequency in use? Whiskey 6 Lima Golf. Is the frequency in use? Whiskey 6 Lima Golf. Is the frequency in use? Whiskey 6 Lima Golf. CQ low, CQ calling, CQ, beaming east from Northern California, Whiskey 6 Lima Golf. Whiskey 6 Lima Golf calling, CQ low, CQ calling, CQ low, CQ. Beaming east from Northern California, Whiskey 6 Lima Golf. Whiskey 6 Lima Golf calling, CQ, hello, CQ. CQ, here on 20 meters, Whiskey 6 Lima Golf. W6LG listening. I'll try that again. CQ low, CQ calling, CQ. CQ calling, CQ. Beaming east from Northern California, Whiskey 6 Lima Golf. Whiskey 6 Lima Golf calling, CQ, hello, CQ. CQ. Beaming east from Northern California, Whiskey 6 Lima Golf. W6LG listening. I hear somebody calling, but you're in my noise. I'm sorry. No copy.
W6 Lima, not Juliet, but Golf. Lima Golf, W5IB.
Hey, how are you? W5IB, W6LG. How are you? My name is Jim, over.
Well, hello, Jim. The name here is Jay. Juliet Alpha Yankee. We're located about 50 miles southeast of Dallas.
Yeah, you're really strong. You must have a Yagi or two pointed my way. You're like 20, 30 over. Go ahead.
I'm running a 6-band 2-element hex beam pointed at you there. Go ahead.
Okay, you hit 40 over. 6-band 2-element hex beam. Well, it's working great. Big signal. I'm using 2 4-element Yagis on separate towers with phasing lines. Alicraft K3 and a homemade amplifier. It's hot here. How about where you are, Jay? Go ahead.
Well, for the first time in about 6 weeks, I can say it's the last 2 days have not been hot. We normally was like, for example, last Friday we were at 107. Today,
Okay, to complete this episode on calling CQ, I called CQ. A guy answered. He was a really nice guy. We had a great conversation. It lasted a lot longer than I put up on the video, but you can see where it went. There was a give and take. There was a sharing of information. We had a great time talking to each other, and it went on for a while. And in fact, subsequent emails were exchanged, and he's doing some research for me on something about a linear amplifier. So it's a guy that I'll hopefully come across again. He's really friendly, had a great sounding signal, and it was serendipitous, one of those things that happens. And that's part of the fun of ham radio. So call CQ, make it about 30 seconds, 45 seconds long. Give your call sign, indicate when you're listening, W6LG, listening for a call, and see who answers. And then you don't necessarily have to pick out the strongest one, but pick one that sounds interesting out of the group and engage that guy in a conversation. It's amazing where it goes. Anyway, thanks for listening. I've enjoyed this one. I enjoyed meeting the guy on 20 meters, and calling CQ for me is a lot of fun because it's just it's kind of fishing. You're not sure what's going to be on the end of the hook, and sometimes it's just a great conversation. Anyway, thanks for joining me. I'm Jim W6LG. Call CQ. See who answers. 73. Hi, I'm Jim W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain. One of the things I've been wanting to talk about, and I'm not sure how to approach it, is the use of slang, jargon, some of it CB radio-ish. And I understand that a lot of us were taught that that's what we were supposed to do. I certainly was in the novice classes that I attended. And perhaps you did too. When I first moved to Nevada County in 1981, I immediately became involved in emergency communications, trying to establish myself in the community. And one of the local fire captains, Charlie Jacobs, KC6LKC, almost immediately approached me and said, "We use plain language." And the more I thought about it and the more he told me about it, the more it made sense. He worked for the California Department of Forestry, now called CAL FIRE, and they communicated with umpteen jurisdictions up and down the state. I don't know how many, but it's hundreds. Each jurisdiction might have had its own 10 code, or there were other things that existed. Some of them actually used the Q signs. So it became a problem for the fire department to talk to a local jurisdiction, because somebody might say 10-7, which in one jurisdiction might be I'm headed out for lunch, to a dead body in another. So they went to plain language, and they enforced that with all of the jurisdictions that they dealt with. So when I was volunteering with CAL FIRE, CDF, the training was stick with plain language, and it really made sense, because part of the things I got involved in real emergencies, one after the other, during a short period of time. And if you're communicating in plain language, the fire captain you're shadowing, or the member of the board of supervisors that you're shadowing, working with, if he can listen to your handheld, your transceiver, and understand what that person is saying without it having to be interpreted, it's all the better. So if a guy says he's at the location of Smartville Road and Highway 20, and there's a fire that's crossed the highway, which did happen, everybody understands that. If you say your QTH is Smartville and Highway 20, they may not understand what you're saying. Some of that also has crept into single sideband voice communications on HF bands, and I'm not sure why it's being used so much. For example, QSL means I understood what you said, or did you understand what I said? The Q signs have both a question and a statement. And sometimes it's needed, but it seems to me that a lot of guys are saying QSL 20, 30, 40 times during a contact. And one of the things that I would say is if you just told the guy he's 5x9, or if I tell you you're 5x9, it really means you're strong and I'm understanding everything you're saying. You don't need to interrogate me every time about QSL. Here's what I mean. The one guy will turn to the other guy by saying, my handle is Jim, my QTH is Grass Valley. QSL, well, QSL doesn't exactly mean over, but you don't really need to ask. If you met that person, here's my simile. It's like meeting somebody on the street. If you met a friend on the street, or maybe it would be for the first time, you might say, "Hi, my name is Jim," but you wouldn't say, "Hi, my name is Jim." Did you understand what I said? And another one that seems to be creeping up a lot is personals. And it sounds kind of funny because the guy will say, "Well, my personals are," I don't want to know your personals. I'd like to know your name and a signal report, but beyond that, I'll ask you if I want to know. So QSL seems to be, every time the guy turns it over, he'd say QSL. Well, you don't need to do that. Once, maybe 15 times, probably too much. Another thing is handle. It's probably better to say my name is Jim instead of my handle is Jim. Or it implies a nickname. It sounds a little bit like Citizens Band. My personals, I think that's a European thing, but it just sounds kind of odd. And it's one thing to say your name, signal report, location. I don't know that you need to go into personals. Another one that I've heard a lot lately, and it's kind of funny, is whiskeys. I'm running 100 whiskeys. Well, I don't think you are. You may have had a few whiskeys, but I don't think you're running whiskeys. You may be running watts. So you might think about the slang that you're using. Back to emergency communications, and I'm getting towards the end of my time on the video. If you're involved in emergency communications, or if you belong to a group, I highly recommend that you consider plain language, simple English. Everybody understands what you're saying. Because when you're carrying on emergency communications, you may be communicating with one guy to deliver the message, but there may be 10 or 15 other people who are listening on the channel and need that information. So using plain language, everyone can understand. If you start falling into using Q signs or 10 codes or one of those things, then the people who really need to know what's going on, who are depending on your communications, have to ask, what's that guy saying? So by keeping it plain language, everybody understands. And I think that's true also of HF. If we stick with plain language, it really helps the guy you're talking to. And sometimes the guy you're talking to may have very limited English language, and I'm very grateful that a guy in another country whose mother tongue is not English is willing to learn enough English to communicate with me. He may only know enough to give a signal report, his name and location. A lot of Russian guys are that way, for example. And they're really struggling to communicate with us, and we need to make it easy for them to understand by saying, my name is Jim, and your signal report is 5x9. Are there times when I've said QTH or QSO, or almost never QSL, but yeah, and usually I think, I shouldn't have done that. So when I'm on the air, I try to stick with plain language. My name is Jim. I'm in Grass Valley. When a guy calls, I'll say, hey, thanks for the call. Nice to hear from you. I don't use whiskeys because I'm running watts, and I don't use the term personals. those are just a few examples of the kinds of things that are being used on the handbands. I'm just suggesting, again, it's not a rant, I'm just suggesting that you think about using plain language so that the guy you're talking to more easily understands what you're saying. And someone who might be listening, and when you're on the air, there are people who are listening to your conversation. Might be a shortwave listener, might be another ham radio operator. Make it easy on everybody and use plain language, things that are easily understood. All right, probably enough. Probably going to get some hate emails from folks, but just think about it for a few minutes. What would it be like if you just didn't use QSL? Or maybe you use it once instead of 15, 20 times during a contact. You don't need to, the guy doesn't need to confirm every sentence that he understands. If he doesn't understand something, he may say, hey, I didn't understand what transceiver you're using. Anyway, think about it, and if you have a comment, post it below. If you'd like to subscribe, please do that, and let's keep this discourse as civil as we can. That's it for today. Thanks for watching. I'm Jim W6. I started to say, thanks for watching. My handle is Jim QSL 73 W6LG. Bye-bye.
Let's see if we can get a happy Thanksgiving to this guy. Hopefully I don't mess it up, but we'll see. 579.
All right, having a little more fun on the bench here with the Tektronix MDO 4000 mixed domain oscilloscope and this little Motino wireless Arduino clone. So I spoke about this in my last video. This Motino is just an Arduino compatible clone that is married with a RFM12B UHF transceiver. This one happens to be 433 megahertz in that band. So the one I've got hooked up over here on the bench is just transmitting ASCII characters in bursts. And while it's doing that, it's actually communicating over 2 separate buses as well. So the microcontroller is talking out through or transmitting through an RS-232 bus on this pin over here, so I'm looking at that on the scope. And then it's also communicating with the RFM12B module using an SPI bus. And the 3 lines for that, the slave select, the clock, and the master in, slave out data lines are also being probed with the scope. And in the scope I could define up to 4 buses simultaneously, and each of those buses can be completely different. I'm just using the analog inputs here for that, but I could have just as well used the digital inputs as well, but we're just using the analog inputs for those buses for the time being here. So what I did is I just captured one of the bursts of transmissions from the Motino and captured all the different domains of it and all these various signals on the scope in one shot. So let's take a look at what we've got. So up on the top here, the first trace that says the letter A here, that's the RF amplitude versus time. So this is essentially the RF amplitude coming up and then going through the transmission and then shutting off. And that was captured on the spectrum analyzer input of the scope. The next line that says, it's got the little F, that stands for RF frequency deviation in the vertical axis versus time. So you can think of it as an FMD mod. And what we're showing is essentially the FSK, the frequency shift keyed data that's being sent during that RF burst. Okay. The other traces that we have, channel 1, 2, and 3 right here, are those 3 lines for the SPI bus. So I've got them displayed here, and then the SPI bus decode is shown in here. We'll zoom in on this in a moment to actually look at some of the data that's being sent. And then channel 4, this is the RS-232 line, and its decode is going to be shown in here. We'll zoom in on that in a moment as well. But before we do that, let's take a look at some of the details of the spectrum. So you can see the spectrum on the spectrum analyzer portion of the display, and the nice thing about this scope is it allows you to tie in your analog and digital signals with what the RF is doing over time. So if I look at the spectrum here, that spectrum is from a particular location in time within this transmission. And where that's indicated or where that's measured is right where this little orange or yellow bar is right here, orange bar. Let's call that the spectrum time indicator. So at this point in time, that's what the spectrum is doing. And we can see a number of different, it looks kind of noisy. And what that's indicating is there's a lot of modulation that's going on at that point in time. And if we look at where that's lined up in time, we can see there's a lot of 1010 FSK modulation at that location in time. We can move that. It's very simple to move that just by using the pan control here, and I can position that spectrum time wherever I like. So if I move it over a little bit to where I have some of this data that's being transmitted, you can actually see the change in the modulation. So I'll just pan that over. Let's see if I can get this all on screen here. So you'll notice I'll just pan over with the display. That's moving that spectrum time. And you can kind of see at this location in time here now, okay, we spend a lot more time at 0 and 1, okay, not as many transitions. The spectrum is cleaned up quite a bit. In fact, you see a little bit higher peak on the lower portion of the FSK, and that's because I've got this long 0 down here. If I keep positioning it around, you can kind of watch the change of that spectrum as I move that across. Okay, so depending on how much time it's spending at one frequency or the other, you'll see one of those peaks come up more than another, for example. So right here, I've got a little bit more time spending on the high than I do on the low, and you can see that now reflected in the spectrum. So that's one of the beauties of the MDO, is being able to look at those multiple domains. But let's look at some of the other activity that's going on here. I'll pan back over here a little bit. And if we zoom in just a little, and zooming in is actually very easy, just use the inner knob here. And once I zoom in, okay, what I'm doing is taking a portion of that record and expanding it out down here. So I can kind of see that I'm zoomed in here. And what I can see, if I look down at the RS-232 bus, okay, now I can actually see the RS-232 signals. Let's pull that up a little bit so it's easier to see. So there's the RS-232 signal there. And then there's the decode, H, I, J, K, L, M, N, etc., going across. Okay, so it's very easy to go see that RS-232 decode. That's running at 115 baud, but the SPY bus is actually running much faster. So we need to zoom in even more to see that. So I'm going to position one of those SPY commands right in about here, and so we'll start taking a look at the SPY bus. Now I can actually see, some of the RF data still here. Everything still is time correlated. But if I zoom in a little bit more, okay, now I can actually see, the data that's being sent and the actual bus signals that are coming from that SPY bus. So clock, slave select, and master out, slave in, and then I can actually see the data that's being sent there. So just a neat little look in multiple domains by being able to capture all these signals at the same time and look at the timing relationship of all of them. So anyway, just a little bit of fun with the Motino and this MDO, and I hope you enjoyed, and thanks for watching.
This is my song about the hobby of ham. I've taken up your time with my freaky jam. If you hear my CQ, you can give me a call if you choose. We can talk about the weather or the bottom of the cycle blues.
This is the Art of the QSO or Contact with me, Jim Heath, W6LG, your YouTube Elmer with Ham Radio Basics. And music by Raul Midon, A3RM, two-time Grammy Award nominee. This is how to have an interesting ham radio conversation on HF single sideband. We're going to talk about listen, listen, listen. There are different kinds of contacts or QSOs, that's some technical issues that need to be adjusted. Make the conversation about the other person. Some topics are okay, others probably not. And most importantly, enjoy the conversation. Don't get the bottom of the cycle blues.
The grid goes down, I will be there. And when there's no one else around, I can...
Hi, I'm Jim, W6LG, your YouTube Elmer with Ham Radio Basics. Welcome to my radio room here in Rockland, California. If you've just upgraded and now have HF privileges, this presentation is for you. And first of all, congratulations, because HF is going to be a lot of fun. Don't need to be afraid, don't need to worry. It's going to be relatively easy. And if you make a mistake, and guys will pretty much help you out. I first went on HF in 1964, so for me this is 57 years and probably between 50 and 100,000 contacts during that time, probably closer to 100,000. So I have some advice that we'll go over in this presentation, and probably the two important things to take away from this is listen, 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 and listen some more. And two, have fun, enjoy it, meet people, talk to people, have a good time. Just dig into it and have a good time. First, let's talk about the HF bands just in a very general way. And what you'll find is that conditions are frequently changing, often changing. So I looked over at the clock because I know that in about 30 minutes for me, 20 meters will begin to open up to Europe, and I'll be looking for some of my friends like S51DX or S57DX, Giannis and Slavko, and OK2RZ, Yuri. I say Yuri because I can't pronounce his name. And A71AM I've talked to recently, and DF2BO and DF2PY. Guys like that have been good friends for some of them for 50 years. As far as the bands go, the lower frequencies, the longer wavelengths, 40 and 80 meters, just in general, as a rule of thumb, they're good during the daytime for local contacts, not so much for DX outside the US, outside the continent, let's say. At nighttime, that layer that absorbs signals during the daytime is pretty much gone, and there can be some really good DX on 40 and 80 meters. 20 meters and up, probably 20 meters is the best choice for DX because it's even at the bottom of the sunspot cycle. There are days when it can be really good. At the bottom of the sunspot cycle, 40 and 80 tend to be better. As the sunspot cycle increases, 20 through 10 meters becomes the place to be. At the top of the sunspot cycle, 10 meters can be unreal. A simple dipole. When I first got on 10 meters at a new location 40 years ago, I put a dipole up about 8 feet off I tied it to a tree, so it was between 6 and 8 feet, between around 2 meters off the ground. I was working Europe with 100 watts with ease, but that was the top of the sunspot cycle. So 20 through 10 meters, the bands are very different. We're lucky to have them. We're privileged to have them. 20 meters is a good band for looking at the gray line, the area on the planet that follows a path of the gray line, and you can Google that and find out more about it, but the gray line propagation can be really good. 15 meters is generally a great band for several years during the sunspot cycle. It can be open several hours a day, and as I said, 10 meters at the top can be just an incredible band. When you get on HF, there's a couple things, and I'm talking about single sideband, there's a couple things to talk about, and I'm not going to get into feed lines or antennas, just a real quick discussion of setting mic gain and compression, because that seems to be a thing that puzzles a lot of guys. What I'd like you to do is to have the microphone 2 fingers from your lips, and I'm just saying that because it's one way I can describe it that everybody can get right. So 2 fingers, have the microphone right here. And the reason for that is if the microphone's like that mic is a long way away, it tends to pick up room echo, which I'm sure that mic is doing to some extent. So close talking the microphone and adjusting the mic gain for the proper level is the way to eliminate a lot of issues, including room echo. With respect to mic gain, the position of the control on the transceiver, the mic gain control, does not matter. What matters is what the metering is telling you. So look at the meter on the transceiver, put it into the ALC position, run the mic gain up and down until the indication is about half of the ALC scale. Put it right there for now. Then turn on the speech processor because you want to bring up the average. And I talked to a well-known broadcaster, W4RN, formerly W0YR, about that. And he and I both agree that some level of processing really, really helps. It could bring up the average 3, 4, or 5 dB. So turn on the speech processor, adjust it for about 5 dB of processing on the meter, then go back and reset the mic gain. Because you've adjusted the compression, it can affect the mic gain. Reset that for about half of the ALC scale. Don't put in a lot of lows. If you have an equalizer, add some highs, reduce the lows. So you want to have the lows low and the highs high. And that's my best description of how to set the mic gain so that it will sound reasonably good. And it's important to have it that way. You don't want to go on the air and have a bunch of distortion and try to talk to somebody and they can't figure out what you're saying. With respect to getting on HF, you might want to try calling CQ, and there are a couple different kinds of CQ. One is where you're just really looking to talk to anybody anywhere, and you can say that, CQ, anybody anywhere, it's W6LG. Or if you're looking for DX, and generally that means outside of the continent that you're on, say CQDX. But listening becomes really important. If you tune around and you listen and the band is dead, whatever band you're on, then calling CQDX probably won't do much. Another way to find out about conditions is to look at one of the DX clusters, and my favorite one is DX Heat, dxheat.com. Really well organized. You can select a single band and you can select a mode. You can decide from where the DX spots are coming. It's got some great filters built into it, and it's relatively easy. If you hear somebody calling CQ and you want to answer, it's just give that person's call sign. OK2RZ, this is W6LG. You may not even need to give the other person's call sign. In the case I mentioned, that's Yuri in Czechoslovakia, and there can be lots of interference, so sometimes I'll give his call sign. If it's a stateside guy, you can just give your call. That person may get 3 or 4 answers, or may get just yours. Again, listen, when that person answers, he's called CQ, I'm assuming it's a guy, he calls CQ, and you answer and he responds, pay attention to the signal report that you get. You may hear him S9, but he may only hear you S2 or 3. So again, listen, pay attention to what's going on. If your report is, let's say, down in the noise or close to the noise and it weak at the other end, then repeat things. You can say your name a couple times, give his signal report a couple of times. When you turn it back to him, don't just stop transmitting. Let him know you're turning it to him by saying, OK2RZ W6LG, over. Or OK4YL, this is W6LG. Back to you, Elena. So again, give that other person a clue that you're turning it back to him if conditions are weak. If he's hearing you S9 and conditions are stable, you can have kind of a back and forth like you would any conversation. QSL. It's a big bugaboo with me. I get tired of hearing it, and frankly, I think it's overused. QSL means, did you understand? If the person you're talking to says, you're 5 by 9, you don't need to say, did you understand? Did you understand? My name is Jim. QSL, did you get it? Did you understand? Just say over. QSL does not mean back to you. QSL means did you copy. Goes back to the days of the telegraph lines, and a message would be sent, and the receiving station would, the sending station might say QSL. It was a question, and the other person might respond. Today it seems to be used as if to say that's over. So try to avoid saying QSL. Another common thing that you may want to avoid doing is a lot of the jargon. Some guys say 100 whiskeys. You're not running whiskeys, you're running watts. So maybe better just to say watts. I no longer use handle. I try to speak in just plain language with respect to as much as I can. So my location is Rockland, California. My name is Jim. Your report is 5x9. Sticking with plain language, I think, is a really good idea, as a habit to get into. I've been involved in several emergencies. Found a guy lost in the snow, house on fire, forest fires. In my 57 years, I've come across all kinds of things. It's important to speak plain language. There were times when I would have a fire captain next to me and I'd be on 2 meters. And one time I remember really well, a friend of mine, Bob Laddie, was reporting the location of a fire, and he said it in plain language. So I didn't have to repeat to the fire captain what the guy was saying. He didn't say QTH, he said the location of the fire is. So the fire captain just had to hear what was going on and nothing more. I didn't have to interpret for him. Plain language is really important during emergencies. Stick with plain language. If you're talking to a dispatcher, I found a guy in the snow. He was lost and somewhat disabled in some regards. Just stick to plain language. I found him here. I'm hearing you okay. His name is. My location is. On HF, do the same thing. Just stick with plain language as much as you can. I fall into the habit of using a lot of Q signs because I have for years. But, for example, the name of this presentation is QSO, and really I mean contact. So try to stick with that. When you're on HF, slow your speech down just a bit. The person that you're talking to may not understand the language that you're using. Typical language, of course, is English. And some guys that you'll talk to sound like their English language skills are excellent when in fact they only know how to say my name is, or your report is, my location is. And they may actually use some of the Q signs like QTH. And so I remember one guy was a fellow on an island called Sao Tome, CR5SP. Didn't speak English, but he knew enough to say a signal. Everybody was 5'9", and he knew enough to say that, and his name was Al, and that was about it. So stick with plain language. If you're not certain that the person you're talking to understands English all that well, keep it relatively simple. Same thing with phonetics. Stick with phonetics that everybody can understand, and try not to use phonetics that might confuse someone. For example, I won't use the guy's real call sign, but I'll change it just a bit. Let's say my call sign was W6, here comes California. There's a guy that uses that. Here, and I won't say what state, here comes California, HC. See, I have to think about it. It's confusing. So just use phonetics that everyone understands and don't confuse the issue. Just stick with that. It's okay to ask questions. If you engage in a conversation and the guy seems friendly and you've listened to him have a couple of contacts and he is engaging in a conversation, it's okay to ask a couple of questions if you want. And, there are some really interesting people. Some of the questions that I've asked are, do you have any other hobbies, photography and that kind of thing? I stay away from politics and religion. A person's religion and their politics, that can raise a whole bunch of issues. That's a whole nother discussion. I don't even want to go down that road in this presentation. Also, I try to stick to things that if my conversation is as if my conversation is being recorded and played to a group that maybe would decide whether or not we can keep the amateur frequencies that we have. That would be like the FCC commissioners. So I tend to stay away from things that are controversial. I don't want to get into an argument with somebody. Just be nice, be friendly, and enjoy the person you're talking to. I've met some really interesting people in those 50 to 100,000 conversations, and as I said, many of them have been friends for 50 years, and several have visited me, like DF2PY, Wolf, and Mike and Sissy OE6NBG from Austria, and it's a thrill, an absolute thrill to meet folks like that. So it's okay to ask someone if they're retired or where they live or what they do, if they're on a farm, that kind of thing. Their equipment, their antenna. If you have a question about their antenna, ask him. The guy may be an antenna engineer, and you might learn a lot by talking to him. In any case, two things I wanted you to take away from this presentation. One is listen, 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 and understand what the person's telling you or what you're hearing on the band. And two, enjoy, have fun. It is just unreal. We are so lucky to have the frequencies that we have. We are so lucky, for example, this is 2021, and we've gone through this pandemic that is still with us, but we've been able to sit at our equipment and talk to people in the U.S., or if we're in the U.S., or around the world. Guys in Europe, same thing. They've been able to stay at home, like Yuri and his wife, and not have to venture out and risk getting the disease that's been fatal to so many. So we're lucky to have the frequencies. We're lucky to have what we have. We are licensed radio operators. It is a hobby, but we are licensed radio operators, and our frequencies are a privilege. So keep that in mind. In any case, have a lot of fun. Thanks for watching. If you have any questions, post them below. Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room. I'm going to install a coax connector, and I'm going to do it really quick. I need a jumper for my station, so I had this one from another this short piece of coax from another project. What I'm going to do is cut off the end. I'm going to do this with some of the proper tools. If you want to use a knife, go for it. You could even use a pair of scissors if you want. I'm going to use a coax prep tool, and to position the tool on the coax, I'm just going to sort of eyeball it. I know that the center conductor, I want to extend past the end of the pin, so I'm going to cut it at a point where it will be a bit long and then trim it afterwards, and that'll make more sense after I get it together. Okay, I've pulled that off, and I'm going to take off the dielectric. So, and the next thing I have to do is remove a little bit of the jacket on the coax. So I've got the center conductor long on purpose, and I'm now going to pull off a little bit, didn't quite cut through, so I'm going to do it manually here. Okay. And that's off. So now I've got about 3/8 of an inch of braid. I've got about 1 inch and a quarter, inch and an eighth of center conductor. I'm going to do a crimp connector as opposed to solder type because I like the crimp better. So I'm going to open up a bag. Got to remember to put the ferrule in. It's hard to do this one wrong. You can forget to put on the barrel of the PL259 and solder it, but you can't crimp it without this ring. So I'm going to push that on. So, and use these. Make sure there's nothing going across. Now I'm going to push this down until it's pretty much up against the jacket. And then I'm going to slip the ferrule over, grab the crimping tool, crimp that. Then I'm going to cut this off, and I dropped something on the floor. Alright, now all I need to do, and I'm going to do that off camera, is solder, get solder to flow in through the pin. That's installing a coax connector. How do you test it? There's a guy who did a video and he licks the coax connector. I don't recommend you do that. Puts an ohmmeter on one end and licks the other. I don't even want to go there. So, transmit through it. Test it with an ohmmeter, of course, real quick, and if it shows open, it's probably okay. You can check continuity from pin to pin. But put it into the transmitter, put a few watts through it, make sure it works okay, and then go to 100 watts. It's just that easy to install a coax connector, and it's much easier than fiddling around with a PL259 that you have to solder through these little holes and not melt the dielectric. All right, get these things off. That's it. That's how you put on a coax connector, and it's the same thing for RG58, RG8X, RG59, LMR400. It's the same process, and that connector will work fine. It's just got to do a little bit of soldering. Thanks for joining me. If you have any questions, post them below. If you have a comment or an idea about how to put on a PL259, let me know. I'd like to read about it. And for now, I'm Jim, W6LG for Ham Radio Basics. Thanks for joining me. See you the next time. Thanks.
Today's video topic is one that's been on my to-do list for quite a while. It's been requested many times. What we're going to talk about is the gain bandwidth product and slew rate and how it applies to op amps. In addition to describing what is meant by gain bandwidth product and slew rate, we'll also demonstrate and measure some of these characteristics using a circuit built up here on the breadboard. So let's take a look at the schematic of what we've got on the breadboard so you can do this yourself. We've got an LM358 op amp configured as an inverting gain amplifier. These two resistors are just a voltage divider to set up the virtual ground point. We're taking a signal out of a signal generator through an adjustable attenuator so I can control the magnitude of the voltage going into the amplifier. Terminated that in 50 ohms so the signal generator sees a constant load. AC coupling that into the amplifier. And I've got three different feedback resistors that we can put in here to configure basically an inverting gain of 1, negative 10, or negative 100, or 0 dB, 20 dB, and 40 dB. This discussion will apply to the vast majority of general purpose op amps on the market, because the vast majority of these op amps are internally designed to be compensated with a single dominant pole. What that means is that the open loop frequency response is going to fall with this single pole response, which really means that the gain, open loop gain, falls at a rate of 6 dB per octave change in frequency, or 20 dB per decade change in frequency. So each time we increase the frequency by a factor of 10, the gain falls by 20 dB. And this is basically what we call a single pole response. So at very low frequencies at DC, you're left with the maximum, open loop gain of the op amp, which is typically, maybe 100 volts per millivolt, something like that, a factor of about 100,000. But typically at frequencies, below a kilohertz or even lower sometimes, the frequency response breaks and then falls at this rate. This single pole response has a nice property in that the product of the voltage gain that you configure when you set up a closed loop amplifier like this, the product of that voltage gain and the bandwidth that will result from that amplifier is a constant value called the gain bandwidth product. Again, in most cases, the gain bandwidth product is also equal to the small signal unity gain bandwidth. So again, for unity gain, if the AV is equal to 1, then the bandwidth is equal to the gain bandwidth product would be the unity gain bandwidth. At other gains, let's say we set up an amplifier with a gain of 10, that would be 20 dB. So 10 times, in this case, 100 kilohertz would be 1 meg. If we set up a closed loop gain of 100 or 40 dB, then 100 times 10K is also 1 meg. So you can kind of see how this product plays in. Now the nice thing about that is, typically using it the other way around is, let's say you need an op amp circuit that has got a gain of a particular value, you can then predict what the bandwidth will be by basically taking the gain bandwidth product divided by that gain you're going to use. That will essentially tell you the bandwidth. We'll measure the bandwidth of this op amp under a couple of different gain conditions. So right now I've got it configured with a 10K feedback resistor, and that gives us an inverting gain of 10 or 20 dB. And I've got the attenuator set up so that the output amplitude of the amplifier is 1 volt peak to peak. So to find the 3 dB bandwidth, we just increase the frequency of the signal generator until the output amplitude falls to 707 millivolts peak to peak. So I'll just reach over here and start adjusting the frequency up on the signal generator. And as we move up here, we can see the amplitude starting to fall. I'm going to increase the sweep speed of the scope here a little bit so we can still see the waveform. Keep increasing that waveform frequency. Now we can see we're starting to get down, right about here or so. Right about here we're at that 707 millivolts peak to peak. That's the amplitude has fallen, and our frequency on the signal generator is just about 63 kilohertz. 63 kilohertz at a factor of 10x. So if we've got a gain of 20 dB or 10x, and a 3 dB frequency of about 63 kilohertz, that means that the gain bandwidth product for this particular op amp under these conditions is about 630 kilohertz. So let's take one more measurement point and see if that all lines up. We'll start by bringing the frequency back down to about 1 kilohertz here again, and slow the scope back up. And I'll take out this 10K resistor. Let's stick in a 100K resistor. The 100K resistor will now configure a gain of 100x. So I'm going to decrease the input amplitude by a factor of 100. So now I've got that same 1 volt peak to peak occurring at that 1 kilohertz. So we'll again increase the frequency of the signal generator until that signal level drops down to about 707 millivolts. And that should be coming right up about here. Let's see. One more click or two. Looks like right about here. So we're right at about 6.4 kilohertz. So 6.4 kilohertz now with a gain of 100x. So again, 100x times 6.4 kilohertz gives me the 640 kilohertz for the gain bandwidth product. And that's pretty close to the 630 kilohertz that we calculated for the 10x. I've plotted those two results on the graph paper here. So for the gain of negative 10 or 20 dB, we had a measured bandwidth of about 63 kilohertz. And then for the gain of 40 dB or negative 100, we had a gain or a bandwidth of about 6.4 kilohertz. So I've plotted those two here, and if we drew a line between them, we can see, they kind of line up on a straight line here. The DC open loop gain of this op amp is somewhere in the neighborhood of between 90 and 95 dB, and so that's kind of where that breakpoint would be. And we can see that this leads to a unity gate bandwidth of about that 630, 640 kilohertz shown down here. So let's go the other way and go down to unity gain with the op amp and see if we can get out to that 630, 640 kilohertz unity gain bandwidth. So we'll replace the feedback resistor with a 1K feedback resistor. That will configure us for an inverting gain of 1. I'll increase my signal amplitude here so that I'm back up to about that same 1 volt peak to peak. And let's start increasing the frequency here. As we keep increasing this up, I'm going to speed the scope up again. Okay, so we're up at nearly 100 kilohertz here. We're starting to drop. But we can see that we're dropping now to 700 millivolts here, but I'm only at a frequency of about 130 kilohertz. So what's going on? Well, the key to what's going on here is that we are now being slew rate limited. Take a look at that waveform. That is no longer a sinusoid. So we're running into the slew rate limit of this op amp for this given frequency. So let's talk about what's meant by slew rate limit. The op amp slew rate is basically defined as the maximum rate, how quickly the op amp can move the output voltage. And this is often limited by the internal compensation capacitor and the available current to drive it. Just what I'm talking about here, if we look at the schematic of an LM358, this is out of an old National Semiconductor data book, this is the compensation capacitor we're talking about. And oftentimes there's a limited amount of current that's available to charge or discharge that capacitor. And that gives rise essentially to a limited rate at which the output can be swung. So this is a problem typically for large signals, not so much of a problem for small signals. Because what you'll find is that large signals, even at the same frequency, have a higher slew rate. Let me show you what I mean by that. So the slew rate of a signal is essentially the measure of how quickly the voltage has to move, or essentially the slope of the voltage versus time. So for this particular signal at just 10 kilohertz, at this signal level we can see the slope, the maximum slope that you reach is about that. If I increase that signal amplitude, I haven't changed the frequency, but that slope has now changed. So higher amplitude signals place a larger demand on the op amp in terms of slew rate because the output has to move faster in a given amount of time. So oftentimes, the slew rate limit of the op amp will become the bandwidth limiting factor, even before you essentially run into the gain bandwidth product, especially for larger signals. Okay, and as we saw in the scope, as signals get larger, the slope gets steeper and we need a faster slew rate. So what can happen is for small signals, okay, you've got no problem generating a given frequency, but as that signal gets larger in amplitude, you actually may run into the slew rate limit of the op amp and therefore distort the waveform because it can't move the voltage any faster with time. And that's what we saw when we just tried to look at the unity gain bandwidth or the unity gain response of the op amp. Of course, we can visually see this if we look at the response of this sine wave in unity gain, and again, relatively large amplitude here. If I increase the frequency here, watch what's happening with the slope of that waveform. Okay, I'm going to grab frequency, start increasing that. You can see the slope is increasing steeper, 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 and it gets to a point where it can't get any steeper, and the waveform is now getting distorted. Okay, so if we take a look at that slope, it looks like it's pointing up at about 1 o'clock. In fact, another way to look at this, let me slow this down again, and let's change the waveform to a square wave. And here you can actually see there's that slew rate limit. Even though the square wave coming out of this signal generator is on the order of about 5 nanoseconds rise and fall time, we're looking here at 4 microseconds of division, so we're taking the better part of 4 or 5 microseconds to swing that point. So we're looking at the slew rate limit of the op amp. And so if I go back to the sine wave here, as I increase the frequency here again, I'll leave my pointer. We can actually see we're running into that slew rate limit. We're not going any steeper. So instead of getting a higher frequency sine wave, we're just distorting that waveform because we just can't keep up. And that's essentially what slew rate looks like, or slew rate limiting looks like on an op amp. So how do we get around that problem? Well, typically, as I was mentioned earlier, if the amplitude of a signal is lower, the slew rate limits are less. So if I reduce the amplitude, you can see that signal now starts to look more sinusoidal. I reduce the amplitude here a little bit more, it's more sinusoidal again, and the signal looks more ideal because that lower amplitude signal doesn't have as steep of an edge at that frequency. So that's why oftentimes when you see unity gain bandwidth defined in an op amp, it's defined effectively for quote-unquote small signals, because that's the only way you're going to be able to get around the slew rate limit for large signals. Now, sometimes a slew rate is specified in the datasheet, sometimes it's just shown in a graph like this for large signal pulse response. For a very fast input pulse here at unity gain, the output is going to be slew rate limited. And you'll also find sometimes that the slew rate for the rising edge and the falling edge won't be the same because there may be a different current available for charging or discharging that internal compensation capacitor. So in this particular data sheet for this LM358, this is showing about a 2.5 volt rise over 10 microseconds. So that gives rise to about 0.25 volts per microsecond. That's oftentimes the way you'd see slew rate specified in terms of volts per microsecond. So let's look at what this op amp is doing. So if I switch the waveform over to a square wave, I can see that that slope it's being governed by the slew rate limit. If I just turn a pair of cursors on here and have those cursors positioned on that, I can read directly off the scope that we're looking at about 203 kilovolts per second, which also translates to about 0.2 volts per microsecond. So that basically lines up with about what we saw in the datasheet. So we can relate that back to sinusoidal frequency as well. So again, for this op amp, we're looking at about 0.2 volts per microsecond. And let's say we're going to be putting a sine wave through your amplifier, and what peak voltage you're going to need out of that. So you can basically calculate the slew rate of the sine wave through this formula. You take the peak voltage of the sine wave multiplied by 2 pi times the frequency of that sine wave, and that will give you the slope, or the maximum slope, the steepest that voltage needs to change. So as long as for the signal amplitude that you need to use, and the frequency, the maximum frequency you need to use, as long as the slew rate of that sine wave is less than the slew rate limit for the op amp, then you'd be able to use that op amp at that frequency. So I hope you learned a little bit about what's meant by gain bandwidth product and slew rate limiting, and how either of these things might determine the ultimate frequency response of your op amp stage. Thanks again for watching. Please subscribe if you haven't done so already, and we'll see you next time. The regular viewers of my channel may remember video 280, where I did a complete and comprehensive review of this Rig Expert AA55 Zoom. One of the things I showed in that video was how to use an open, load, and short calibration standard to calibrate out the effects of a transmission line, so you can predict the impedance or measure the impedance at the end of the line. When I showed how to use the calibration function, I used this OSL, or Open Short Load Calibration Standard. This one's made by Rosenberger. And a lot of people asked, hey, where can I get one of those? Well, you can find them on eBay and places like that. Unfortunately, oftentimes they cost as much as the analyzer does. Well, in this video, I'm going to show you how you can build your own for a fraction of that cost. Part of the reason that this standard costs so much is because it is designed to operate to several gigahertz. Well, this analyzer only goes to 55 megahertz, so we can build something that a little bit lower performance, but perfectly adequate for amateur use at HF and even low VHF frequencies. Now, since most HF amateur radio operation uses PL259 and SO239 connectors, we'll build our standard using that. So I picked up a couple of these inexpensive SO239 to SMA female adapters, and this is what we're going to make our standards out of. I'll put a link for this adapter that I'm using here in the video description down below. Now, to make our OSL standards, we're going to need 3 of these. On each of them, we'll cut off the end of the SMA connector here, and one of them just file it smooth and leave it open, and that'll be our open standard. And then on one of them, we will short the center conductor to the outer ground shell, and that'll be our short. And on a third, we'll add 50 ohm termination from the center to the ground. So first thing we need to do is prepare each of these by cutting off the top of the SMA connector. Of course, one way to do this is to clamp the adapter in a vise and grab a hacksaw blade and cut the end of the connector off. But sometimes clamping something like this, especially if it has threads, is difficult to do without damaging it, and it also can get hung up. So I've got a neat little trick I'm going to show you of how I cut these off. I've got a couple of these SMA shorting plugs laying around here. So what I'm going to do is thread that onto the end of the SMA connector, and that's going to help us in stabilizing this when we go to cut the connector off. Now, the hexagonal head of the shorting plug fits really well into the jaws of the chuck of the drill press. And we can just hand tighten this. It's got plenty of grip on there now. And what we'll do is run the drill press here, and then we can just use a cutting tool to cut the connector off. And we can do this with a little file if we want to use a file. But what I've got here is a nifty little, tiny little metal saw blade that fits in the end of an X-Acto knife handle. So our first standard is an open, and all we do is simply file everything off nice and smooth and give ourselves a nice reference plane there for our open. For the short standard, we're going to use a little copper foil and put that around the base here, and I'll solder it all down. Now for the 50 ohm load standard, I'll take a pair of 100 ohm surface mount resistors and solder them each from the center pin to ground. And there we have our three standards, our open, our short, and our load. Let's see how well they work. Okay, so let's start off with nothing connected to the input of the analyzer. And we run the Smith chart here. We can see that essentially we're sitting very close to the open circuit point on the Smith chart, right over here at this at the 3 o'clock position. So now I've attached a short length of coax. Now that's open at the end, and if we run this Smith chart here again, now I can see all the points have essentially rotated around down the Smith chart here. So that's not representing the impedance that's seen at the end of the cable, it's representing the impedance that's seen looking into that cable here. So if we want to take the cable out of the system and make our measurement with respect to this point here, we need to calibrate to here. Okay, so we'll start the calibration process, and tells us to prepare our standards. Let's connect the open to the end of the cable first, and we hit OK. And it's collecting data on the open. Next we do the same for the short. Short's connected, hit OK, collect the data on the short, and connect the load, and collect the data with the load. So let's see how effective our cal standards were. So again, here's our Smith chart without the calibration to take out the effects of the cable. When we run that again, we can see all of our points sitting way down here. And if we apply that calibration, all those points move right here. In fact, we'll run it again. See all those points collecting right there at the open circuit position on the Smith chart. So now we've seen how easy it is to take a couple of RF adapters and create an open, short, and load calibration standard for an antenna analyzer like this RigExpert AA55 Zoom. If you like what you see, give me a thumbs up. If you haven't subscribed already, please do so, and click the bell down below the video here if you want to get notified each time I post a new video. And thanks again for watching. I recently published a number of videos on the Smith chart, including how to design an impedance matching network using the Smith chart. Now, of course, in order to do this, you need to know the complex impedance of the device that you want to match. One problem that many people run into is that some of the very common antenna analyzers that are out there, like this MFJ259B, don't tell you the sign of the reactive component. In other words, they don't tell you whether X is positive or inductive, or if X is negative or capacitive. So how do we determine what that is? One very common method that you'll see written up is to increase the measurement frequency slightly and note what happens to the reactive component. If it increases, then it's inductive or positive. If it decreases as you increase the frequency, then it's capacitive or negative. The problem is this isn't always true. In fact, it does not apply when you're measuring an antenna or a load through a transmission line, because the transmission line will do some transformations on the impedance. So if we can't follow this method when measuring a load through a transmission line, what do we do? Now the answer, of course, is Smith chart to the rescue, using a very simple process. We make 3 measurements of the resistive and reactive components at 3 frequencies in increasing order. And we plot these on the Smith chart twice, once for each sign of X, and then connect each of these sets of 3 points with a curve. So we wind up with 2 curves on the Smith chart. Now the sign that results in an arc that rotates clockwise as the frequency increases is the correct one. This is simply just a very convenient property of the math behind the Smith chart. So let's go run an example and show you how it works. I've got a transmission line and a complex load connected to my analyzer here. So let's make 3 measurements. At 4 megahertz, the resistive part is 49 ohms and the reactive part is 19 ohms. Let's adjust up to, say, 4.2 megahertz, and we'll record 59 ohms and 26 ohms reactive. And then if we go to 4.4 megahertz, we'll record 64 ohms and 46 ohms reactive. Now, of course, if we followed this method up here, the increasing value of X as frequency increases would tell us that this is an inductive load. Let's go see if that's true. Now, of course, in order to plot these values on the Smith chart, we've got to normalize them to our system impedance of 50 ohms. So that's simply taking each of these values and dividing them by 50. And I just finished completing those. So these are the values that we're going to plot on the Smith chart. We'll start off with a 0.98 and 0.38. So 0.98 in the real axis is going to be really close to this unity circle. And the 0.38, let's start with the positive one, is going to be very close to the 0.4. So our first point is right here. And then to plot the negative version of that, we go down here and plot down here for a negative 0.38. So those are our first 2 points. Okay, with the remaining points plotted, we can now kind of connect these up with a curve. And this one curve goes this way, and again the frequency is increasing in this direction here. Okay, and the other curve goes down in this direction, this way. Okay, and in that case the frequency is increasing in that direction. Now if we take a look at these 2 curves, this is the one that's going in a clockwise direction. This one is rotating in a counterclockwise direction. So that's not the right answer, and this tells us that the X component here is indeed negative, meaning that it is capacitive. We're on the lower half of the Smith chart. And just to be sure we've got it right, we'll plot the Smith chart here on my Rig Expert antenna analyzer. And this one will actually show us the curve. And indeed, the Smith chart is showing that our curve is here on the capacitive side, and the X component is indeed capacitive. And there you have it. If your analyzer is like this MFJ259B, and does not give you the sign of the reactive component, you can follow this simple process and determine that for sure by yourself. Now, thanks again for watching. If you like what you see, please give me a thumbs up. If you haven't subscribed to the channel already, please do so, and of course tell your friends. Thanks again for watching, and look forward to all your comments. Thank you.
The other question that often comes up is, what is it all about? What is amateur radio? Well, I'd like to offer an explanation as to where the expression ham came from, and also talk about amateur radio. And I've had a license since 1964, when I was 14 years old. Ham was sort of a derogatory or negative comment about a new operator on a telegraph. And that would have been in the late 1800s. The schools that taught telegraphy were called ham factories. The guys who came out of them were called hams. And it was generally kind of along the lines of being ham-handed, not very good with the hands. Sending good characters on a telegraph key is an art, and some guys can do it just incredibly well, others not so much. So the expression ham during telegraphy times was a poor operator. In about 1913 to 1915, as amateurs, radio operators started appearing on the scene, licensed by the radio service at that time. That was the Department of Commerce, I think. The expression ham radio started to carry over, rather the expression ham started to carry over to these operators. At that time, in 1913, 1914, 15, 16, 17, 18, along in there, the guys who were transmitting signals were sending something called spark gap. There were two pieces of metal spaced at a correct distance. Some had carbon at the tips, I think. And they would generate really high voltages, and they would key that with a telegraph key. And so it would have this buzzing sound, this arcing sound. And they were sending signals to other guys who might be 100 miles away, might be 50 miles away, might be on the next street. And so for them, it was a thrill just to make contact with anybody. Their receivers were, at best, not much more than a crystal set, which had wide ranges of frequencies that they would hear at one time. And when these guys would transmit, their signals also were super wide. But as things evolved and the use of really well-made homemade equipment and then commercial equipment, the kind of signal that was sent out improved dramatically. The expression ham carried forward into those operators, not so much in a negative way, but that they were experimenters. And today the expression ham radio operator is not negative at all, but it refers to somebody who is an amateur radio operator and has the appropriate license. Each country has its own regulations regarding transmitters and the ability for amateurs to get on the air. I think every country but one or two allow that these days. I think one of them is where it's not allowed is North Korea. So ham radio started off as a negative comment about amateur radio operators. So what is an amateur radio operator? First, there's three parts to my definition of what an amateur radio operator is, or what ham radio is. Number one, it is a licensed radio service, licensed by the Federal Communications Commission. The amateur radio operator has to pass an exam, and the number of amateur radio operators in the United States is somewhere north of 600,000, I think. They keep us around because, and we have a large number of frequencies, because during emergencies and during disasters, oftentimes, ham radio or amateur radio is the only means of communications. Why is that the case? Well, because ham radio operators practice for emergencies. Many have set up repeaters on UHF and VHF to convey messages. And right now in the adjacent two counties, there's a fire, and communications are being carried on as a backup to the fire departments by ham radio operators who have repeaters in place. Even though the power is down in large portions of Northern California, their equipment is battery operated or solar powered. So ham radio operators are ready for emergencies. I've done many during the years I've held a license. Most ham radio operators have participated in an emergency. What are those emergencies? Could be a fire, as is going on now. Could be a flood. It could be a snowstorm. Could be any dam breaking. Could be any number of things where ham radio operators step up. Oftentimes, it is a backup means of communicating. During the 49er fire, which was one that I was involved in for about a week, we provided secondary communications, maybe simple things like needing food being delivered to a camp where firemen were staging and would come in after being on the fire line for 2 days and would come in to eat and rest. Sometimes it's simple things like that. Other times it's reporting that a fire has crossed a line. Some ham radio operators will man a lookout tower and report on the progress of a fire. So emergencies, number 2, it is a incredible hobby with so many facets to that, I can't name them all. But those things include digital communications, where ham radio operators talk to each other using digital modes, where the signal is extremely weak. So weak that with my ears, I can't hear it, but the equipment can dig that signal out of the noise and convert it to text that runs across a screen. Pretty amazing stuff. Sending pictures, talking to the space station, any number of things. Building antennas, designing antennas, building amplifiers, installing equipment. Just a huge range of things that amateur radio operators have used, incorporated into sometimes other hobbies, maybe flying in a remote control airplane. There are so many that it's just mind-boggling. The third part of amateur radio, so there's 2 parts. Number 1, and most important, is it's a licensed radio service. 2, it's a hobby that is just incredible. There's no other hobby that has so many facets, nothing. And 3, another, and I'm going to say unique. A unique feature of amateur radio is the friendship that's made. Unlike other things that require a license, licensed amateur radio operators make friends in other countries around the world, and those friendships can last 50, 60 years. In my case, I've had some of those friends for over 50 years. So it's, and though the friendship that is developed means that one ham radio operator will do something to help another. It may be as simple as providing transportation in a circumstance, or explaining how something functions, or making a YouTube video to explain how to build or operate something. There are friends who just get together on a daily or weekly basis, meet on the air. Those friends could be in the United States. They could also be in the Middle East, or in Europe or Asia, Australia, New Zealand, in Oceania, anywhere on the planet. And given the radio propagation on HF and the variations in the sun's affecting communications, talk to those guys on a fairly frequent basis over the air and having a good time doing it. Other ham radio operators get together on networks, and some of them have the purpose of providing emergency services. Others are just getting together and saying hi. So amateur radio is a licensed radio service. It's a hobby with just an incredible number of facets, and I've only mentioned a few. And 3, and for me the most important part, is the friends and the friendships that go on for decades. That's what ham radio, amateur radio is. If you have a question about amateur radio, post that below. If you have a comment, put that below also. And if you haven't subscribed, I would highly recommend that you do. Amateur radio operators have a series of numbers. It's called the 92 code, and Welcome to this beautiful property at 16067 Wolf Mountain Road, presented by Mimi Simmons.
Hi there, I'm Mimi Simmons from Century 21 Cornerstone Realty Group, your local community broker. Thanks for touring my listing today. You can see this listing as well as many other listings that I have and everything in the MLS on www.mimisimmons.com, or you can contact me for an appointment at 530-265-7940. Have a great day.
My name is Jim Heath, Heath. I grew up in the San Fernando Valley, and I think a result of where I grew up, I've now come down with acute myeloid leukemia. The disease that I have is, at my age, really impossible to treat. And as the oncologist explained to me, what likely will kill me is an infection of some kind. And that seems to be the case because I've been admitted to the hospital now 6 times with sepsis. The point of this video is to discuss the Santa Susana Mountains and a facility there that I think has caused my disease. I've done a lot of YouTube videos as an amateur radio operator explaining how some things work and how to work with some things. This video has nothing to do with that. It has to do with acute myeloid leukemia. I was diagnosed about 2 years ago with myeloid dysplastic syndrome, which is sometimes been called pre-leukemia, because about a third of the patients who have MDS develop AML. Myeloid dysplastic syndrome becomes acute myeloid leukemia. The times in the hospital last year were serious. Sometimes I was in guarded condition. A couple of times taken by ambulance. And that was what happened a few days ago. I had fallen asleep and was pretty shaky when I fell asleep. Normally, I'm pretty steady with my hands. I woke up shaking all over. I knew with that kind of shaking that I was likely spiking a fever. Took my temperature, and it was about 102 degrees. We called 911. I was fortunate enough to have an ambulance close by, and a fire truck showed up out in front of the house with firemen ready to deliver care and to get me to the hospital, and that did happen. I was admitted into the emergency department at Kaiser and taken to an isolation room because I have very low white count. Anybody who's around me has to be wearing a mask. Otherwise, that person could infect me, and the infection could be fatal. Tests run recently at the hospital show some heart damage, and likely that's a result of the stresses and the infections that I've had, and the lack of oxygen to my heart, to my brain, and to other muscles. The amount of oxygen in my blood can drop into the 70s if I'm relaxed and just laying down, chilling out, watching TV. It tends to want to drop because I don't have very many red blood cells. My red blood count is about 2. My white count is about 1. My ANC is 0.3 for those who understand things. Hemoglobin right now is probably about 7.2. As a result of tests being run while I was in the hospital and other times during, I go to the hospital twice a week for blood tests. I've had 20 transfusions since last year. The acute myeloid leukemia is part of a series of things that are affecting me. Another one is severe osteoporosis. Another one is a goiter. And I'd like to talk about the goiter a little bit first, and when I got it, and why I think I got it. grew up in the San Fernando Valley. There was a nuclear reactor in the Santa Susana Mountains on a 2,900 acre site. It's also the site where Saturn rockets were tested. And there is a connection. The nuclear reactor blew up, releasing more radioactivity than 3 Mile Island. I'll say that again. The nuclear reactor released more radiation into the atmosphere than 3 Mile Island. A lot of that is on the site. As a kid, the rockets were tested. The exhaust from the rockets were really pointed into the San Fernando Valley. We could hear them, we could feel them. What it was doing was blowing all kinds of chemicals, unburned fuel, into the San Fernando Valley, sometimes also picking up the radiation. The radioactivity was released in 1959. And at that time, shortly thereafter, I developed a goiter. The thyroid gland in my neck swole up, the glands swole up, and became hard, and they still are. I can still feel them. I was eventually taken to UCLA Medical Center, where they tried to figure out why a 10-year-old kid would have a disease related to a thyroid gland becoming enlarged, likely by radiation. Where did I get that? We didn't know. Today we know. I also think that the acute myeloid leukemia that I have is a result of the exposure to the fuels that were in the rockets and being blown into the San Fernando Valley. That site currently is owned by Boeing. I think at the time it was a joint ownership, and I think one of them was Rocketdyne. Most people don't know about it, about the Santa Susana Mountains and the damage that was done to people in the San Fernando Valley. It's been reported, I should say, by some of the TV stations in LA, like Channel 4 and Warren Only. But nothing really has happened to fix the situation, and it may be too late to do anything about it. My situation is grim. I know that, and it's become a little bit more difficult every day. Again, I'm having trouble keeping oxygen in my blood. As a result, I just sometimes pass out. It looks like I'm falling asleep, but actually I'm just down and out. I've had that happen during video conversations with others, to the point where one group decided they didn't want me in the group anymore, because a couple of times I did that, where I just went head down, and they're in all parts of the world, and they're panicked about what they can do to help me. The illness that I have, I firmly believe, is a result of exposure to benzene and other fuels that were pumped into the San Fernando Valley from Rocketdyne. And also the radiation that was released, I believe, is still on the ground in the San Fernando Valley. I believe the tests should be run. A lot of the San Fernando Valley has been developed that at the time was undeveloped. So it's hard to say how much has been covered up and is maybe encapsulated. I don't know. I know a little bit about amateur radio and electronics. I don't know much about radiation. At UCLA, when I was taken there in 1959 at the age of 10, the treatment was to, first of all, measure the radiation. You measure the goiter using radiation, and then ultimately to do an ablation. How am I doing now? I'm doing okay, not really strong, just out of the hospital a few days. It was not fun being in the hospital, and it wasn't fun to talk to the oncologist who came by my room to give me the news of the number of blasts in my blood. The way that was done was with a bone marrow aspiration. The final results of that are 4 weeks out, but the preliminary results are likely accurate according to the oncologist. So, to restate, I believe that the site north of the San Fernando Valley, the 2,900 acres, I believe is dangerous today. There was a fire that went through there a couple of years ago that likely put up plumes of radiation as stuff was being burned. It's an open sore north of the San Fernando Valley. It's a cancer, and that cancer, I think, is going to cause a lot of people grief. As I'm thinking back to the time I had the goiter, there were 2 kids who lived near me. They were just a few blocks up from where I lived. They were across the street from each other. Both of them developed a cancer at the time. It may have been leukemia. They both died about a year later, and within weeks of each other, they were both dead. Again, we didn't know about the Santa Susana Mountain issue. We just knew that it was bizarre that these 2 kids would have the same kind of cancer, and where did they get it? How were they exposed? What were they into? How did that happen? Well, today I know the answer, and it's the site that's owned by Boeing. Along those lines, it's unconscionable to me that a company could own a site that is dangerous, that they know is dangerous, and not fix it. And also for the state of California and the federal government not to fix the site. If the company that owns the site won't fix it, then the Fed should step in and fix it. If you would like to make a contribution to my Patreon account, I've put a link to that in the description of the video. The description is brief. Hopefully it'll catch some attention. And maybe finally something will be done with that site. Again, my name is Jim Heath. I currently live in Rockland, California, and I have acute myeloid leukemia, and it is terminal.
Hi, I'm Jim, W6LG for Ham Radio Basics. Welcome to my radio room here on Wolf Mountain Lookout. My favorite antenna, for a lot of reasons, is the dipole. It's simple, it works. In emergency situations, it can be strung up as an inverted V, an upside down V with the center insulator attached to a pole, a tree, a fence post, all kinds of things. It is real forgiving in terms of its length. It doesn't have to be perfect. Pretty much anything will work, from house wiring to electric fence wire even. So, and that makes some changes, but this is a dipole, and I've mounted it to the top. And as funny as it looks, I've mounted it to the top of an antenna analyzer. It's not pretty, but it'll make the point of what a dipole is. And in this case, instead of having something like this in the middle, I've just got a coax connector, and I soldered on 2 lengths of house wiring. How long is a dipole? Well, that's really easy. The formula that I use is not one that you'll see in a book. It is simplified just a bit so that I can remember it. And the formula, my formula for a dipole is 1, 2, 3, 4. That I can remember. One side is 234. 1, 2, 3, 4. One side is 234 divided by the frequency in megahertz. So I cut this a little bit long. It is about 20 inches. So if I take 234 and divide it by 1.75 feet, it's the number of feet into 234. Resonant frequency about 134 megahertz. So a little bit shy of 2 meters. Okay, so let's see where this antenna is resonant. It's got a couple of dips, so it's probably reacting with the other wires on the table. It's about 45 ohms at 137.7 megahertz. I said 133.7, so it's about 4 megahertz different, and part of that probably has to do with the insulation on the wire and its diameter. So let's see where it starts to go above 2 to 1. It's above 2 to 1 at about 156 at the high end and about 132 or 33 at the low end. So about 24 megahertz of coverage. On 2 meters, let's go to 144. It's 1.5, 148. It's about 1.6. So that's really pretty good. What happens if I add 100 feet of coax? And in this case, I've got on the table 100 feet of RG8X. What will happen to the dipole? It's going to change the SWR. Okay. So it's so broad I was having trouble figuring it out here for a second. So its resonant point is about 136 megahertz. 2 to 1 SWR now is down to 115 megahertz and up to, well, it won't go that high. So probably 180, 190 megahertz. So we added 100 feet of coax. The resonant frequency stayed pretty much the same, but its bandwidth became enormous. What does that tell us? Well, the feed line is really lossy, so the reflected power is decreased as it comes back into this box. In other words, the SWR here is one thing. The reading that this makes at the end of 100 feet of coax is very different. So we have a lot of line loss because this is RG8X. It's not good coax for 2 meters and above. It's not good coax for a lot of frequencies. So it looks to be really, really lossy because all of a sudden it shows a huge bandwidth. So when you install an antenna and the SWR looks really good, that may be good and it may not. Speaking of which, I want to show you this. Swing this around. This fancy looking box is my automatic antenna tuner. Instantly tunes the antenna, which is made up of 2 rods about, I think they're about 19, well, they're probably close to 20 inches long. Feed point is down here, and it instantly matches to the transceiver. I mean, instantly. So let's see how this looks. I'm gonna disconnect my dipole, such as it is, which would work, by the way, and it'd work fine on 2 meters. Oh,
speaking of which, if this is a dipole, and if we get an understanding about how this works, when it's configured like that, it's a vertical, right? So if we added more radials, it would look more like a vertical, bent and not very pretty, but it would be a vertical. When it's like this, it's a dipole. If we can understand how this works as a dipole, we can probably figure out a lot of different antennas. So let me bring up a video that I shot outside yesterday. It's far from perfect, but I took exterior Christmas lights, holiday lights, whatever you'd like to call them, strung them out on about 8 feet of fiberglass pole, and transmitted into it. And if you watch this video closely, look at the bulbs in the middle that are at the feed point, and then look at the bulbs on the end that are red. And as shaky as it is, the filaments for the bulbs in the middle, I think they were blue, hardly light up at all. The green are lit a little more, the orange considerably more, and the red are really bright. So what does that tell us about how the voltage divides on a dipole? The bulbs at the end are bright, the bulbs in the middle are barely lit. So the high voltage is on the end, and the high current is in the middle. Now, why is that important? Well, it's important because it tells us a couple of things. It tells us what part of the antenna is doing most of the radiating, and it's not the high voltage, it's the high current. So a good deal of the power that's radiated by this antenna occurs in roughly the middle, about a third of the way up. In other words, you can take an antenna, put some kind of capacity hat on the end of it, take off this end, and either put a trap here or some kind of capacitive loading, and still have a relatively efficient antenna for a dipole. Let's say you decide you need to feed this at the end. Okay, this is the low impedance, high current. This is the high voltage, high impedance. So if we combine this and put the coax connector down here, what does the impedance look like? Well, if we do the formula, it comes out infinite, but in fact, it is about somewhere in the neighborhood of 5,000 ohms, 4,000 ohms, in that ballpark. So we need to do transformation. In other words, if we're hooking up RG8X here, that's 50 ohms, we need to change the impedance or match the impedance with a transformer of some kind. Very easy to do, no big deal. It's typically a 9-to-1 or 10-to-1 transformation. Again, high current in the middle, high voltage on the end, high impedance, low impedance. If we feed it here, it's high impedance. If you can remember that, you can pretty much figure out any antenna. That's an exaggeration, but you can pretty much figure out a lot of antennas that we use on HF. This device, which was similar to one marketed by a company, I think they were in Florida, ran a lot of ads in some pretty well-known ham radio magazines, and I made a copy of it. So I've still got batteries going in that camera. Let's look at the SWR. Again, this is an automatic matchbox. It will immediately tune. There's some parts on the inside. If you put an ohm meter on it, it appears to be open. So let's just set it on the table here. Well, I'm at 175 megahertz and it's 1-to-1 or darn near it. Let's tune down. I'm at 143 megahertz and it's 1-to-1. Isn't that amazing? It works great. I've got a great SWR on all frequencies. There is a point to this. There's 128 megahertz. It's still 1-to-1. Let's go down to 10 meters. It's still 1-to-1. It instantly tuned. Here's 14 megahertz. It's 1-to-1. And in fact, if I'm turning the knob, and it's 1-to-1 everywhere. No matter what frequency I go to, it's 1-to-1. So, how does this magic box work? It automatically tunes. It says right on it that it's rated at 100 watts. So you get a very good SWR. The manufacturers of these kinds of antennas have done them as dipoles and as verticals. If you hook this up and you listen with it, you'll hear a few signals. But what is this? How does this work? Well, if I take off the cover and you look inside, you're going to see about 50 resistors. Yeah, it's a dummy load. It's a dummy load, and the resistors are connected to these two rods. One through a grommet, the other one, the case, is connected directly to the rod. So it produces a 1-to-1 SWR on any frequency, I think. Well, it's going to get weird when you get up to gigahertz, but on all HF frequencies up through VHF, probably even 70 centimeters, it's going to be 1-to-1. So when you see your SWR being low, it may be because you've got huge coax feedline losses. It may be that your antenna is not very efficient. So these are things to be aware of. When a company advertises an antenna that tunes everywhere with a low SWR, be really suspicious. An efficient antenna tends to be fairly narrow in its performance. It has a high Q. This thing is nothing more than a dummy load. And in fact, I'm not sure which would work better, my light bulb dummy load or this thing. What have we discussed today, and what's coming up in the next video? Well, we've discussed that high currents in the middle on a standard half-wave dipole, high voltage is on the end, and because it's high voltage, it's high impedance. At the high current place, that's where most of the radiating is done. It's not on the ends. Thanks for watching. I hope you've enjoyed this. If you have a comment, please post it below. If you've enjoyed this episode, please do subscribe. I'm trying really hard to get to 10,000 and subscribers, and I think I'm at 8,100 plus. Last couple of videos have had a lot of views. Anyway, thanks for watching. I'm Jim, W6LG for Ham Radio Basics 7.3. Thanks. Bye-bye.
Most of us own a Baofeng. It is cheap and does the job. What would you say if we could transplant its heart and combine it with a Raspberry Pi or an ESP32? We would get a dirt cheap and compact device for all sorts of analog and digital modes. So let's look at this small bugger. Hello wireless enthusiasts. Here is the channel with a strange Swiss distortion in the signal, with a new video around wireless and other exciting stuff. Make sure you subscribe if you do not want to miss the following emissions. In the past we had to build our transceivers out of discrete parts. Today we get more and more integrated modules. One example is the powerful and cheap LoRa transceiver modules, which cost less than $10. If we connect them to an antenna and a microcontroller, we can do many projects. However, they only transmit digital signals. The modules in today's video are different and include a complete analog transceiver for either 2 meters or 70 centimeters and have an output power of 1 or 2 watts. The same modules are sold under different names, SA818 or DRA818. The U version is for UHF, the V version for VHF, and the 2-watt version is called SA868. Their feature list is similar to a standard handheld analog radio, except that they are single band. This is no surprise as its main chip is the same as in most cheap handhelds. Let's have a look at what's inside. The heart is the RDA1846 or RDA1846S RF transceiver chip. 2 things are astonishing for me. First, the chip contains an SDR transceiver, and second, its datasheet is from 2009. When it was introduced, I'm sure it was revolutionary, and I do not know of a successor chip with better properties. Maybe you know? The RD1846S chip costs less than $2. Together with a small MCU, an antenna switch, and a power amplifier, it forms the SA118 module. To create a full-blown 2 meter or 70 centimeters voice transceiver with an SA818 module, we have to add a microcontroller, a microphone, and a loudspeaker. To transfer digital signals, we need a sound card instead of a microphone and a loudspeaker. The SA818 modules use 3.3 volts for communication and therefore are compatible with the Raspberries or the ESP32s. As usual, they forgot one small thing inside the module: the low-pass filter. As with all Baofengs, the SA818 creates quite strong harmonics. Here I have a board with more parts. Uwe added a loudspeaker amplifier and a microphone amplifier with automatic gain control. And he included this tiny low-pass filter that supports up to 8 watts. Incredible! With this board, we can quickly build a full-blown walkie-talkie. It also contains a connector with the relevant signals and 2 jumpers to influence the behavior of the microphone amplifier. You will find more information about these jumpers in the MAX 9814 datasheet. Because the MAX 9814 is hard to solder, we ordered a few boards with soldered parts from JLC PCB. I paid it with my own money, by the way, and it was not very expensive. So let's start a project. First, I want to build a walkie-talkie for 145.5 MHz. So I solder a VHF version of the SA818 on the board. According to the diagram, I need an RX and TX signal and ground. For future projects, I want to use a Raspberry Pi Zero 2W. This is why I start with its bigger sister, the Pi 3 Model A. This board has a USB connector for an external sound card. As usual, we have to solve some problems. The Raspberries offer a serial connection on GPIO 14 and 15. After some fumbling, I discovered that we have to enable serial, but disable the serial console. Then the serial port is available at def TTY-S0. We could send AT commands to the SA818, and it would respond. But as usual on this channel, we want more. I found a Python program that can be used to program the module. We can install it using pip. Simple. With this command, I set the frequency to 145.5 MHz and the squelch to 1 for a quiet environment. Now we have to connect a microphone and a loudspeaker. Because of the LM386, we can use a decent speaker, and I connect a cheap Electret microphone to the input of the MAX 9814. Fortunately, the chip offers a bias voltage. Now we need a second handheld to check our newly built walkie-talkie.
Test Hotel Bravo 9, Bravo Lima Alpha.
And here comes the next hurdle. For the first tests, I screwed a small dummy load on the antenna connector, and everything went fine. When I replaced the dummy load with an antenna, many strange signals appeared on the wires. I should have expected these problems because of the long wires and the relatively high output power. So I connected this J-pole antenna and put it a few meters away.
Test, Hotel Bravo 9, Bravo Lima Alpha.
As you hear, everything works fine now. Let's go digital. What is a good project to test if this marvelous chip also works for digital modes? Of course, Direwolf and Zastier. And how to install it? Of course, with Build-A-Pi made by Jason, KM4ACK. It installs all sorts of useful ham radio programs on your Pi. The only thing you need is time. Its installation took at least 4 hours on my Pi 3. I strongly recommend extending the swap file on these small Pis, otherwise they can block. As said before, we must replace the microphone and the loudspeaker with a sound card. I use the cheapest one I found because the specs are not important. Maybe somebody with good KiCad skills replaces the microphone and loudspeaker amplifiers with a sound card chip and creates a hat for a Pi Zero? That would be awesome. I saw the cables to the microphone and the headphone jack and connect them to our board. We only need one channel, by the way. If you solder your SA818 on an experimental board, you should be able to connect these wires directly to the module. Because I found a good video for the installation of Direwolf and Zastier, I can omit the setup details here. As soon as we enter the call sign, the modem speed and the GPIO number for the PTT into direwolf.conf, we can start. Because I am in the basement, I use my Anytone to create an APRS signal. And really, after tweaking the sound level, I get the messages coming. This is cool. The receiver works fine. So we go on with Zastier. First we have to add the AGWPE network, because Direwolf waits for a connection from an AGW client. Next we have to connect GPIO 25 to the PTT pin of the SA818 and go to Interface Transmit Now. We hear a packet radio signal on 145.5, so we have to change the frequency as before. RX and TX are still connected and it is quickly done. Here in Europe we use 144.8 MHz for the APRS network. Maybe Jason can help us to find a way to automate the frequency adjustment before we start Direwolf. Then our solution would be better than a standard Baofeng. And did the signal arrive on APRS.FI? Yes, it did. Fortunately, I'm not far from an APRS iGate, and it heard me from the basement. Now I can start to send messages via the APRS network. The next frontier will be WinLink, and I hope it will run too. But this is the topic of another video. On the internet you find many other projects with these modules. For example, this Echolink hotspot. It runs on an Orange Pi Zero. This is an excellent platform because it has a built-in microphone input and does not need a sound card. It just does not run Raspberry OS. Voltlock designed this hat, by the way. OH2LAK built a repeater with 2 modules. Hamvoid built an All-Star node in an Altoid box and connected 2 of them to a repeater. We even get an Arduino library to program the SA818. We could create a smaller device using this library and the ESP32 module with the built-in sound card. Watch video number 419 to learn more about working with audio and the ESP32. If you do not want to build your own kit and have deep pockets, the Shari project is maybe for you. You even get a cheaper knockoff on AliExpress. Please tell us if you have already done projects with these modules or what other ideas you have. And if you would be willing to create a Pi Zero hat including a sound card chip. But what about the harmonics? With the LFCN 160 Plus filter between the module and the antenna, the second harmonic is still too high because this filter does not have enough attenuation at 300 MHz. An LFCN 120 Plus would probably be better. For 70 centimeters, you get the LFCN 400 or 490. Also here, the 400 is probably the better choice. I also found these FRS modules. Unfortunately, I did not find a lot of information about them. Maybe you know more? The -4 module are rated for 3.5 watts, by the way. That is all for today. As always, you find all the relevant links in the description. 73 to everybody, and please consider supporting the channel by using the links in the description. See you in the next episode.
Now in my previous video, I built this pin diode based transmit receive switch. And I used some pin diodes that I picked up in a collection of parts at a Hamfest, and they were just unlabeled, just as pin diodes. No markings, there's no markings on the components. So I wanted to verify that they were indeed pin diodes. And a way to do that is to take a look at the device capacitance as well as the reverse recovery time. And so while doing that, I thought, well, maybe a video on diode reverse recovery time would be a good one to do. So that's what we're going to talk about today, is the reverse recovery characteristics of diodes. So what is the diode reverse recovery time? When a diode is switched from forward to reverse bias, a reverse current actually flows for a short period of time. Now, a way to kind of illustrate this is, let's say we have this switch thrown in this position here. We're sending a positive voltage, through this current limiting resistor through the diode. So the current through the diode is shown like this. When the switch is thrown in the opposite direction, to essentially have a negative voltage applied to the diode, you say, well, it's going to act like a diode and it blocks all the current flow. And that's true, but not instantaneously. What happens is that there's a reverse current that flows. Sometimes it can go down and be current limited by the voltage and the resistor. Sometimes it might just pop down and then recover back. So you actually get this reverse current that flows where the diode doesn't block like a diode for a short period of time. Now, this is due to essentially the stored charge in the PN junction. When the junction is forward biased, there's a space charge that's built up around the junction that basically allows the junction to then conduct. When you reverse the bias, that charge has to be removed, and then essentially carriers have to recombine to reform the depletion region, which causes the diode to block. And this doesn't happen instantaneously. The reverse recovery time can range from a few nanoseconds or less for high-speed switching diodes to a few microseconds or more for high-power rectifiers or even pin diodes. So the reverse recovery time is going to depend very highly on the particular device and what its application was designed for, as well as the current levels that are involved. For a given device, if we operated at a higher forward current, the reverse recovery time will be longer because there's more space charge that has to be removed. So we'll see that the reverse recovery time is proportional to the forward current. It's also proportional to the amount of voltage applied in the reverse direction, so how quickly we can remove that charge. So testing for reverse recovery time is going to be very highly dependent on the test setup. Now, many of the manufacturers of diodes, when they specify reverse recovery time, will also include what their test configuration was. So the values that are in the specification table are really only going to apply under those specific test conditions. So the little test method that I show here might not match the results of a line item in the datasheet, because this test setup that I use here might not match what the manufacturer used when they actually made that characterization. So why do we care about reverse recovery? Well, if you had a diode that had a lot of a long reverse recovery time, that could be a significant source of loss in like a switching regulator, where we want to snap the current off very quickly. It also could be a source of inaccuracy of a peak detector, where if we're trying to put charge onto a capacitor to measure the peak voltage level. If there's any reverse current, then that would bleed charge off of that capacitor and cause an inaccuracy in that measurement. So there can be, some reasons why you'd want to think about what the reverse recovery is in your application. There can be some benefits too. It can be beneficial in some signal switching applications. And again, if we take a look at my video on pin diodes and RF switching, we'll see that that stored charge allows us to use the diode to switch RF currents, even when those RF currents and voltages would normally reverse bias the diode. We're taking advantage of the fact that the diode is still conducting even when the voltage across it is reverse biased to be an effective switch. So there's pluses and minuses to the effect that we have here. Now, as I mentioned, different manufacturers will have different test setups for measuring the reverse recovery time. I'm using a very, very simple setup here just to show the effect. I've got a pulse generator that's set up to output a pulse that goes from a negative voltage starting off at say -1, going to +1, and then going back to -1. I've got it set up for just a few microseconds of width. The pulse generator itself, like most function generators, has essentially a 50 ohm output impedance, so that's going to tend to limit the current. We're going to basically just send that directly through our device under test, our diode that we're testing, and go into a 50 ohm termination. In my case, I'm using the 50 ohm termination that's built into the scope, but if your scope doesn't have a 50 ohm termination that you could turn on, you can use just a 50 ohm termination, a 50 ohm resistor, and probe it with say a 10x probe with your scope, or use a 50 ohm 3-through termination right at the input of the scope. So this is the test fixture I use for testing devices like this. It's just a pair of SMA jacks soldered to a piece of scrap circuit board. I used an X-Acto knife to kind of hog out, essentially a conducting strip between the two connectors, and hogged out a little bit of the center of there to create two little isolated strips. And I soldered in a couple of just pin sockets, a couple different sizes, that make it very easy for me to take a device, and stick it, into the socket to make measurements. Now with a piece of wire inserted in my test fixture, we can easily see the applied pulse that I'm going to be putting essentially through the diode. So in this case it's starting off at -1 volt going to +1 volt, and that's looking into 50 ohms. Of course, when we go through the diode drop and things like that are going to make these voltages change, but that's okay. We're just going to use this as a quick way of visualizing the reverse recovery effect. Okay, so if I move my shorting wire here, and let's replace that with the first device we'll test is this little power rectifier diode. We'll stick that in here. We can now see that effect of that reverse recovery. Now, the horizontal scale here is about 400 nanoseconds per division, so we've got probably about a microsecond or so for this thing to kind of get pretty darn close to being off. Now, of course, that's all going to depend on the bias conditions. We're looking at about 600 millivolts or so in the forward direction here. That's 600 millivolts across the 50 ohm termination. So 10 to 12 milliamps of forward bias. And then when we go turn off, we can actually see this is going down to about 1.3 volts or so. So we're at 25 or so milliamps going in the reverse direction for a little while, and then we can see it tail off back to 0. So if I increase the forward bias, that will increase the amount of charge that's stored in the junction and make a correspondingly longer reverse recovery time. So let me increase that, and we can actually see that effect. The forward bias is increasing, that reverse recovery time is also increasing. So you can kind of see how that effect works. Now also, if I increase the negative bias, make it more negative when we turn the device off, we can remove that charge quicker. So if I grab the low level and make it lower, we can actually see that the peak current gets higher, but the reverse recovery gets a little bit shorter. And if I decrease that reverse bias, we can see how the reverse recovery can take very long. So increases in reverse bias can tend to shorten the reverse recovery time. And of course, this is all dependent on the particular devices used. So let's take this rectifier out. If I put in this guy as a 1N4001, we stick that into the socket here. We can see it's got a slightly different characteristic, a little bit longer reverse recovery time. Doesn't go quite as deep in terms of the peak reverse current. I've got another even higher power diode here. This one's similar to a 1N4004, I believe. And we can see that, again, just a little bit longer, in the reverse recovery pedestal, but then the recombination time is a little bit faster in terms of that exponential, kind of decay here. So all these devices behave a little bit differently. I've got an unmarked glass switching diode here, and if we stick that in the socket, we can see that its reverse recovery time is actually much shorter. In fact, we can zoom in on that and get a better feel for that. So that's about 40 nanoseconds of division now. So say 40, 80, 1.2 or 120 nanoseconds. That one's basically pretty much off. So it's probably an order of magnitude faster than the switching diodes the rectifier diode I was showing you earlier. Now, high-speed switching diodes that are designed specifically for that, things like a 1N914. I've got a very, very fast reverse recovery time. So if we stick that diode in here, we can see that I can barely see what's going on here. But if we zoom in, okay, and I got to zoom in even further on that. Let's kind of center that up or so and zoom in on that. Okay, so now I'm at 4 nanoseconds of division, and I can see that I'm recovered, from going through 0 and recovering back up again in about 4 nanoseconds. Okay, so very, very fast in terms of its reverse recovery characteristic. And that's typical of like 1N914 or a 1N4148 that are designed for high-speed switching applications. Now, Schottky diodes, on the other hand, since they don't have a PN junction per se, they don't have the same stored charge. So if I stick this 1N5711 Schottky diode in there, we see just a very slight undershoot here, and that's probably more due just to reflections and stuff in my fixture as opposed to any real reverse recovery. Now let's kind of go back and take a look at the original reason I started playing around with this fixture was to take a look at the reverse recovery of these pin diodes that I used in my transmit receive switch. So let's see if I can get that to sit in the fixture here. So I can see here now, if we zoom in on this here, that the reverse recovery of this pin diode is on the order of, let's see, there's that 40 nanoseconds of division, so 40, 80, about that same 120 nanoseconds. But I can see the recombination time is actually really pretty quick on this, and so this kind of long duration here, where we're just current limited by the source and load, is really what's advantageous for us in the RF switching application that I use the pin diodes for. That and the low capacitance when the device is off. So I hope you learned a little something about what reverse recovery is in a diode, a quick way to measure it, and some of the conditions that affect how that reverse recovery behaves. Thanks again for watching. Comments are always welcome, and see you next time. We've got another back to basics topic today, this time a 555 based one-shot or monostable multivibrator. And that's quite simply a circuit that outputs a single pulse in response to a trigger. Now the reason for doing this, I had a A viewer asked me if I had ever designed a circuit that simply would do this function. When a 5-volt signal goes low, energize a relay for 1 second. He had a particular application for this, so I figured, yeah, that's actually a pretty simple thing that could be handled by a monostable multivibrator. So I've built up the circuit on the breadboard here. I can simulate the loss of that 5-volt signal by shorting this wire to ground. And when I do that, we can hear the relay click, and I'm just lighting up an LED on the other side of the relay to indicate that the relay is closed. So we can see the relay is activating for about a second when that 5-volt signal goes away. So let's take a detailed look at the schematic and how this circuit operates. So here's a 555 based monostable multivibrator. This R and C determine the pulse width that you get out when the circuit is triggered. So those are kind of critical components to determine what the output pulse width is. Throwing a decoupling capacitor on pin 5, the control pin, is just a good idea for noise immunity, as is putting a decoupling cap on the power supply. Down here on the trigger pin, this is how I'm simulating the loss of his 5-volt signal by simply tying that pin to a 5-volt source through a 10K resistor and then momentarily shorting it to ground to simulate the loss of that signal. So this would just simply connect to his source for that 5-volt signal that he's monitoring. The output is just going through a current limiting resistor into a 2N3904 general purpose NPN transistor, which is going to pull current through the coil of the relay, energizing the relay and thus energizing the load. In my case, the load is a simple LED and current limiting resistor, but in his particular application that may be something completely different. And then of course we've got a diode around the relay coil to prevent that kickback voltage from damaging the transistor. The only other thing that we do is we're going to tie the reset line on the 555 to 5 volts, because we're not going to use that reset line to do anything. So if all you wanted to learn was how to make a one-shot with a 555, there's your schematic. You can go off and play and turn the video off now. But if you want to learn how this circuit works in more detail, stick around. Let's take a look inside the 555 and see what's going on. By revealing the functional circuit diagram of the 555, we can easily see how this monostable multivibrator works. The 555 consists of a little resistor string here, a pair of comparators, an RS flip-flop, and a transistor. The resistor string simply sets up a voltage divider so that 1/3 of VCC appears here, 2/3 of VCC appears here, and those are inputs to these two comparators. Upon power up, the RS flip-flop is in the reset condition. So that means that the Q output is low, which means that this out is low, the transistor is off, our load is not energized, and the Q bar output of the flip-flop is high, which means that this transistor is turned on, which means it's pulling current down through this resistor here and kind of saturating the transistor and keeping the capacitor here from charging up. So if that capacitor is not getting charged, this voltage is going to stay low, near ground, which means the output of this comparator is low, so we're not going to reset the flip-flop. Similarly, with the 5 volts applied to the trigger input, the output of this comparator is also low, which means that the flip-flop is not going to change state. So we're sitting here, if we're not triggered, we're going to be sitting in that reset condition. Now if the trigger input is brought down below 1/3 VCC, the output of this comparator will go high. And we're going to do that with on the circuit by simply yanking that down to ground. Once that happens, we hit the set on the flip-flop. The Q output then goes high, thereby turning on our transistor and turning on our relay. At the same time, we're also turning off the discharge transistor. So essentially this goes open circuit. Now the capacitor is allowed to charge up through this resistor, and it's going to charge up exponentially. And is going to keep doing that until the voltage on the capacitor reaches 2/3 VCC, at which point this comparator then goes high and resets the flip-flop. As soon as that happens, the output goes low again, we turn the relay off, and the discharge transistor comes on and quickly takes the charge off of this capacitor and brings that voltage back down to the saturation transistor, or saturation voltage of this transistor. And again, we're going to sit there until we trigger again. And in terms of component selections, not really critical at all on the decoupling cap on the control pin or VCC. We just want the product of R and C times 1.1 to equal our pulse width, so that's why we chose those. And generally I try to stay away from really large value of capacitors because they tend to be leaky and unstable. So this is a reasonable compromise, and in this particular case the actual timing wasn't super critical, so that would work fine. On this side here, the 10K resistor really wasn't critical at all, just a simple pull-up resistor to VCC. The base current limiting transistor was set to be 470 ohms, because that gave me about 10 to 20% of the collector current. Okay, we're going to saturate this transistor. You really want the base current to be about 1/10 or 1/20th or so of the collector current when saturated. So that gave me about the right amount of collector current when saturated to turn on this particular relay. So you may have to play with that value depending on what relay you might be driving in your circuit if you're doing this configuration. And then a simple switching diode around the relay coil to keep that flyback voltage under control. So it kind of makes sense that the on voltage is just a little bit greater than RC, or the RC time constant. And that's because you may remember from charging a capacitor that you charge to about 63% of the total voltage in one RC time constant. In this case, we need to go to 2/3 of the charge voltage, which is about 66.7%. So that's just a little bit greater than one RC time constant, so that's where the 1.1 comes from. If you stick around to the very end, we'll go through the math of where that came from, but let's go take a look at some waveforms on the circuit first. Now, because this circuit operates pretty slowly, I put the scope in this roll mode so we can watch the voltages kind of march by. Channel 1, the yellow trace, is probing the trigger input, so it's set on a 5 volt per division scale. Channel 2 is probing the output pin of the 555. Channel 3 is probing the voltage across the capacitor. Both of those are on a 2 volt per division scale. So if I trigger the circuit, we can actually see what those waveforms are doing. You can see I bounced a little bit when I hit the trigger circuit there. Let's hit it again and pause it and take a look at those waveforms. So we can see once I triggered the input, the output went high, and we started charging up that capacitor through the resistor. This has got an exponential charge to it, and once it reached 2/3 of VCC, then that other comparator inside the 555 reset the flip-flop, turn the output off, discharge the capacitor, and then we sit in that state. Well, pretty simple circuit. The waveforms kind of bear it all out. Now, another thing to note about this circuit is that once triggered, it won't be re-triggerable again until after it resets. So you'll notice if I hit the trigger a number of times, it doesn't cause the circuit to reset again. So you're always kind of guaranteed to get that pulse width out, even if the trigger circuit kind of gets hit multiple times. Now, there are a lot of other one-shot circuits out there. There's some monolithic one-shots, both in CMOS and TTL technologies. But this was a good way to take a look at the operation of the 555 timer. I hope you enjoyed the video, and again, if you stick around, the last thing we'll talk about here is a little bit more detail on the math of where that 1.1 times RC came from. Okay, so we'll answer the question of where the 1.1 times RC came from. For a simple RC network, when you initially apply a voltage, the voltage across the capacitor follows this equation. And so it's just the applied voltage times 1 minus e to the minus t over RC, the RC time constant. Now, if we want to figure out how long it takes to get to a specific voltage, we just have to solve for t. So it's just rearranging the equation. And we can do that by, say, dividing both sides by v. That gets us to here. And then we could kind of subtract, move terms from one side to the other to get to this point here. Take the natural log of both sides, and that gets us to the point where we've almost got t isolated over here. We simply multiply both sides by negative RC, and we're left with time is equal to minus RC times the natural log of 1 minus VC over V. Now in our case, with the 555 timer, we know that we're going to be charging up to 2/3 VCC. So VC, or the capacitor voltage divided by the applied voltage, is equal to 2/3. We plug that into the equation here. We have minus RC times the natural log of 1 minus 2/3, which is the same thing as the natural log of 1/3. And if you plug that into your calculator, you'll find that T is equal to, it's like 1.098, but we round it to 1.1 times RC. So that's where that came from. Anyway, I hope you enjoyed the video, learned a little bit more about how the 555 timer works, and how this monostable multivibrator operates. Thanks again for watching. Comments are always welcome. In today's Back to Basics video, we're going to talk about Zener diodes. And we'll talk about the basics of their characteristics, some of the uses of Zener diodes, and also talk a little bit about some of the easy design calculations to employ a Zener diode in your design. In the second half of the video, we'll talk a little bit about why all Zener diodes are not created equal. So let's get started. Now, most of you are likely familiar with the IV, or voltage and current characteristics of an ordinary signal diode or rectifier diode, where as you forward bias it, it begins to conduct and essentially allows current to pass, but when you reverse bias it, very little current flows. And that's how most signal and rectifier diodes behave. Zener diodes are designed to break down in the reverse direction and also start conducting then in the reverse direction at some pre-described Zener voltage. And this can have some useful properties. It can be used as a shunt regulator, like a little voltage regulator, and this is typically where you don't need any particularly good efficiency, because you're going to have to burn some current flowing through that diode at all times in order to maintain that Zener voltage. So it's not a very efficient regulator, but it's a very simple one. Also, sometimes in a circuit you might need a pre-described reference voltage, or a voltage that stays stable even if the power supply varies. It might be used as a reference for other parts of a circuit. So a reference voltage generator is another reason maybe to use a Zener diode. Maybe a voltage clamp or level shifting circuit, other applications like that. Typical Zener diodes have got a Zener voltage ranging from about say 2.5, 2.4 volts to even 200 volts or more, depending on the particular diode that you have. So lots of little applications, and basically, like I said, it's just a diode that's designed to break down at a particular voltage in reverse bias. So let's go take a look at how you would design something like this into a circuit. Each Zener diode is going to be specified to operate at a particular Zener current or reverse current through the Zener diode, and that's where the Zener voltage is specified to operate. So you're going to have to essentially pick a resistor value that when the circuit is powered up through whatever the positive supply is, that you're going to establish that Zener current through the diode. You have to take into consideration that whatever circuit you're using beyond that, whether it's a reference voltage or using this as a voltage regulator, you got to figure out how much current is going to be drawn by that circuit and take that into account when you design that resistor value. And the equation is actually pretty simple. We know that the voltage across this resistor is going to simply be our supply voltage, our nominal supply voltage, minus the Zener voltage. Okay, and you also then know that the current through this resistor is going to equal the sum of the Zener current, which is going to be some desired value that you get from the datasheet, plus your maximum expected load current. So the simple Ohm's law tells us what that resistor is. So it was a pretty simple calculation to design, the series resistor to be used to employ a Zener diode as a shunt regulator or, say, a voltage reference. Now, to demonstrate the operation of a Zener, I've got this very simple test circuit put together. A variable DC power supply connected through an ammeter, so we can measure the current going through the bias resistor, in this case 330 ohms, and my Zener diode. Now I've got 2 voltmeters hooked up here, 1 voltmeter that is hooked up directly across the Zener, so we can see what that reverse voltage looks like across the Zener. And I'm calling it reverse voltage because I've got the cathode here and the anode here, so from the diode's perspective it's reverse bias. So we'll measure that Zener voltage, or the reverse bias voltage, with one voltmeter, and then measure the total voltage applied with the other voltmeter. And what we expect to see is, as we start cranking the voltage up, at low voltages, these two voltages will match because there'll be very little current flowing through the diode because we're still in that condition where it's blocking. So no current flowing through the resistor, and we're going to virtually measure the same voltage on either side of the resistor. Once that diode turns on, as we bring that voltage up, we'll see this voltage start to stabilize, and the voltage across the 330 will increase as we increase our variable DC supply. And that indicates essentially that clamping condition where we've crossed that knee in the IV characteristic, and this is now just going to behave like a short circuit with a fixed voltage drop. So let's go take a look at that. So here's the test circuit on the breadboard. The 2 connections up here are to the DC power supply that's coming through the ammeter, and also a connection up to the top voltmeter. And now this is my 330 ohm resistor connected through the Zener diode. Notice the band is at the top here, which is the cathode, so I'm going to reverse bias this diode with a positive supply applied here. And then this is going off to the other voltmeter that's reading the Zener voltage, and then my return or ground connection here. Okay, here's the instrumentation. This is my variable DC power supply. The voltage on the Keithley multimeter here is going to measure the voltage across the Zener diode itself. This is going to measure the current that's going through the Zener diode, and then the voltmeter down here is measuring the total voltage appearing across the series combination of the 330 ohm resistor and the Zener diode. Okay, so if I turn the power supply up a little bit, let's say and go to about, say, 2 volts, I can see I've got 2 volts being applied across the 330 ohm resistor and Zener diode combination. That same voltage is appearing across just the Zener diode. We can see I've only got about 1 microamp or so of current flowing. So we're in this region right here on the curve where we've got some reverse bias, but we're really not conducting yet. If I turn the voltage up a little bit more, let's say from 2 volts to now, say, 4 volts. At 4 volts now, I've got about 0.3 milliamps flowing. Okay, so we're starting to walk our way down this portion of the curve here on the Zener curve. We're starting to get a bit more reverse bias current, and we can see that because now there's a little bit larger voltage difference between the voltage applied and the voltage just across the Zener. Let's go from 4 volts to 5. So now I made just a 1 volt change from 4 volts to 5 volts applied. Only 4.4 volts is appearing across the Zener, and I've got 1.8 milliamps of current flowing. So I'm walking my way down this curve just a little bit further. Let's go from 5 volts all the way to 10 volts. Okay, so now 10 volts applied, 9.96, we can see here the voltage across the Zener has changed very little. It's now at 4.69, so about 4.7 volts, which is about right because this is a 4.7 volt Zener. And we just walked our way a little bit further down this curve and closer to the rated Zener current. That's why we're getting the Zener voltage that we expect from this diode. So it's really just about as simple as that. By reverse biasing a Zener diode and limiting the current to within some operating range, you can essentially establish a relatively constant voltage to be used as a constant voltage source for a reference voltage, voltage regulator, etc. Now remember I mentioned at the beginning that not all Zener diodes are created equal. Let's take a look at what I mean by that. Now, to take a look at what I mean by not created equal, we've got to look at a little bit of the physics, but don't worry, we're not going to go too deep. Zener diodes, like any other diode, are made by putting together 2 semiconductor materials, a p-type and an n-type material. In the case of Zeners, the p and n materials are very heavily doped, meaning they've got a lot of carriers, free carriers. Now when you reverse bias them, a depletion region forms. But because the regions are very heavily doped, the depletion region is very thin. So the electric field that appears across that is really strong. So it's a large voltage potential over a very thin area. And that electric field causes carriers to essentially tunnel through that depletion region in a mechanism called quantum tunneling. Also seen it referred to as quantum mechanical tunneling. And these are true Zener diodes. This is the Zener effect and what leads to this operation. Now, Zener diodes that have got Zener voltages up to about 5 or 6 volts work predominantly under this behavior. Now, one of the downsides to this is that it's not a very sharp behavior. What I mean by that is, as you reverse bias, as you saw when we were doing our experiment, the current started to come down, and there was a bit of a knee that you had to roll down before you were in that reverse bias region where you looked like a very low resistance. It was that very soft Zener turn-on characteristic, and that's very characteristic of this Zener effect. Now, by contrast, Zener diodes whose Zener voltage is greater than 5 or 6 volts actually operate under a different principle. Actually, they're more accurately called avalanche diodes. In these diodes, the P and N junctions are very lightly doped, so that now when you apply that reverse bias, the depletion region actually gets quite wide. And because of that, you get a voltage, again, you get that electric field that appears across that. But because that is a relatively long distance, the electric field will cause some small amount of leakage current, just like it does in the other case. But in this case, because that those carriers that are in this depletion region are exposed to this electric field for a long time, they accelerate to very, very rapid, very, very fast velocities. And they go so fast that they can smash into other atoms and free electrons from those atoms. Those electrons get also accelerated by the electric field and smash into more atoms. And you get this avalanche effect that can cause a small amount of carriers being emitted from one side to result in a very large total amount of current that's coming through. So you get this impact ionization type mechanism, kind of like an avalanche of snow down the side of a mountain. It's the same type of an effect. Now, the one advantage, if you will, to this type of operation is that this characteristic of the reverse turn-on is actually very sharp. And we'll actually go take a look at this on the curve tracer. As you bring the bias voltage more and more negative, you reach a point where you turn a corner, it's almost like a very sharp corner, and boom, you're conducting. You don't have that soft transition region like you do in the true Zeners. So the reality is that Zener diodes, even though they're all called Zeners, most of them that are above 5 or 6 volts are actually avalanche diodes. And even most of the Zeners actually will have some of these two different properties operating at the same time. So you'll get some avalanche effect and some Zener effect. It's just that those that are rated at higher voltages will be more avalanche than Zener, and those that are rated at lower voltages will be more Zener than avalanche. Let's go take a look at the two on the curve tracer so you can see what we're talking about. Now, the curve tracer is going to allow us to essentially draw that same curve that you saw written on my note paper. The horizontal axis here is, in this case, set up to 1 volt per division, and the vertical axis is set up to 2 milliamps per division. So if I've got a simple ordinary diode in here right now, and if I turn the voltage up, we can see the typical ordinary diode characteristic where we're forward biased a little bit and we get that strong forward current, but in a reverse bias we essentially block and have no current flowing at all. We're sitting essentially at 0, which is the middle of the plot. And that's your typical ordinary silicon diode characteristic. Let's take a look at a Zener diode and an avalanche diode. Okay, so this is that same 4.7 volt Zener that we had in our test circuit. We turn the voltage up on here. We can see we're starting off by looking at like an ordinary diode, but as I continue to increase the voltage, now I start to see me walking down and doing that Zener breakdown over here. And here you can see what I was talking about, where we've got a relatively soft turn-on characteristic. So if you don't reverse bias it with enough current, you can be on this kind of higher resistance portion of the curve, and it won't be as stiff or as stable of a voltage reference as it is when you get further down the curve. So you've got to get enough Zener current to be in this low resistance portion of it to get good Zener action. So you do have to be careful of that with these low voltage Zeners, and there's really no other way around it. You just have to recognize the fact that you're going to have this kind of a characteristic. Let's look at an avalanche diode and see the difference. Now this diode is a 6.8 volt Zener diode, but it actually operates with avalanche mode. Now in this case, at 1 volt per division, I'm not going to quite see the breakdown, so what I'm going to do is slide this whole curve over so that my DC point is way over here, or my 0 point is way over here. So now I can expand that scale out and look at the reverse bias characteristic more easily. And now I can actually see that very, very sharp turn to avalanche breakdown. And we can see that the transition from reverse bias, where we're blocking, to conducting is almost like turning a corner. You couldn't draw it almost any better than that. So this kind of explains why the avalanche diodes actually are a lot more stable. They appear to be more stable with varying Zener currents because you don't have that soft turn-on characteristic. It actually turns on very sharp. Now to compare them on the same scale and everything else, I've got the curve tracer loaded up with both, and I can switch back and forth between them. So here's our avalanche diode, and this is the true Zener diode. You can see how much softer that turn-on characteristic is compared to the avalanche diode. Now something else that's interesting is that the true Zener diodes, this Zener breakdown characteristic, or the voltage at which we start to turn that corner, has got a negative temperature coefficient. So as the temperature goes up, the Zener voltage will actually decrease. By contrast, the avalanche diodes have a slight positive temperature coefficient. So as the temperature goes up, this voltage will tend to increase. And now, as I mentioned, most diodes are really a combination of both. You know, one might dominate more than the other. But manufacturers can, with very careful control of the processes and the doping, try to make those two temperature coefficients somewhat cancel out and make some pretty stable Zener diodes versus temperature. Now you pay more for those because they require a lot more process control, but it is something that's possible. Well, I hope this video gave you a little more background and information on Zener diodes and how to use them, and really what the two different types are, even though they're all called Zener diodes generally. If you like what you see, please give me a thumbs up. If you haven't subscribed already, please do so. And thanks again, as always, for watching.
Hi, I'm Jim, W6LG, your YouTube Elmer for Ham Radio Basics. Welcome to my radio room here in Rockland, California. I need to build a couple of dummy loads, and I already have this guy, and this is a Bird dummy load that is good for 500 watts at 30 minutes on, 30 minutes off. It is a brute. Now it says 500 watts. I put way more than 500 watts into it. I put 1500 watts into it. This darn thing must weigh 20 pounds. But where I need to go is outside and test some coax cables. So for my purposes, this dummy load is not going to do the job, but I need a couple more. In the past, I've built dummy loads using resistors like this. These are 5 watt 1000 ohm resistors. There are 20 let's see, these are 1000 ohm. There's 20 in here, and they're 1000 ohms, so 20 into 1000 ohms, they're parallel, is 50 ohms. And In checking it with an ohm meter, it measures about 49.5 ohms. In transmitting into it, it's okay to a certain frequency, and then it gets real reactive. And part of that is due to the wires that I used. There are wires that become a significant portion of a wavelength as you get close to 2 meters, and it gets real reactive. So the box I build during the break will be, the goal will be to have no inductive reactance, no capacitor reactance, to try to eliminate both of those and have it be just a resistive load. So what I'm going to do is take some rods that look like this, like that. They're copper, and then I'll parallel two of them like railroad tracks and put the resistors in between. And then I'm going to slap some copper sheets on both ends to try to eliminate the inductance of this rod. I'm going to cover it up. I'm going to solder copper to it. So it'll be pretty ugly looking, but I'm hoping it'll work up to 2 meters. Find out more about that on the Nano VNA right after this break, and during the break, which is going to be for me probably a couple of hours, I'll build the dummy load. We'll see how it works. So stand by. Be right back in just a few seconds, your time, but a couple hours for me.
Calling CQ, hello CQ. CQ calling CQ, hello CQ. Whiskey 6 Lima Golf. Whiskey 6 Lima Golf.
Okay. The couple of hours that I thought it would take ended up taking a couple of days. And what I ended up doing was building more than one dummy load. As it turned out, the insides of my dummy loads ended up pretty ugly, and I'm hoping that they work well. The first one I built was this one, and it was a box I had, and I've used it on a bunch of projects. It's just simply a box that had a relay in it. It was sold commercially for ham radio operators, and I've acquired a couple of them over the years at garage sales and things. So the resistors are on the inside, kind of in a circle, and I slapped copper on the top and bottom. Now that is just horrific looking, honestly. If you look at the solder connections are good. They're not cold, but they're ugly. And no matter how hard I tried, and I built a couple this way, I couldn't make it look any better. So anyway, I'm hoping that with the copper plate, if I can show that it will remove any inductance, because I've slapped that copper over the top of it. So we'll see how that goes. There are that wasn't supposed to happen. There are 20 resistors, 1,000 ohms, parallel. 20 to 1,000 is 50. Measuring this with just a plain old ohm meter, it shows 49.3 ohms. So close enough to 50, but we'll see what the reactance does, because the reactance will change that value. This one, yeah, it's a dummy load, and I put a fan on one side. There's an exhaust on the other. Yes, it's got a light bulb on top, and it's got its own little watt meter. So it's a 50 microamp meter. I took a circular ferrite bead, put some wire around it, and went through 1N34 up to this and through a potentiometer. And son of a gun, I calibrated it for 500 watts full scale, and it's really close. The light bulb, I do have a need for that, and I'll demonstrate that here in just a minute. In a subsequent video, I'm going to talk about pulse width modulation, and this seemed like a good way to demonstrate how that happens. So the bulb can be unscrewed and it's out of the circuit, and we'll see how that looks on the VNA. Okay, let's jump over to the VNA and take a look first at the small dummy load, and then last to the larger dummy load with the light bulb. Okay, I've scanned the box from 3 to 30 megahertz. It's virtually flat with an SWR of about 1.05. So that's excellent. Let's see what happens when we go to 2 meters. So I'll put in 148 megahertz and sweep this thing. Again, this is the small box with the copper. That's excellent. So a slight rise around 120, 30 megahertz. But still, that's only about 1.15 to 1. That's an excellent SWR curve. So again, it looks like the copper did the trick. Now, getting to 440 megahertz is going to be a whole different situation, because just about anything will react there. So let's sweep it and see what we get. All right. So it's about 1.7 to 1 at the worst. It's not terrible, but it's not going to be good enough for what most of us need to do. Basically, the box is good through about 2 meters, maybe 200 megahertz. There's a dip at 241 megahertz. That whole curve, although it looks a bit high, it's really not. It's about 1.15, 1.12 to 1, so through 250 megahertz. So that's really good. Now let's sweep the big box, and that will have the light bulb disconnected initially, and that will change. When the light bulb is screwed in, because it's cold, it's going to present a very different impedance, a very different resistance. So scanning it with a nano VNA may not tell us much. So let's do that now. Okay, it's better than I thought it would be. Again, it is virtually flat from 3 to 30 megahertz. So for HF, in that fan I've got inside, I've got a 600 watt dummy load. Let's try this with screwing in the light bulb and see what happens with that. Okay, that's with the light bulb. Screwed in but cold, so the reading will be different when it's got power going to it. This particular curve has no value because it won't apply with the light bulb heating up. So here we go. Let's put some light on the subject and see what happens. Okay, there's the filament is lit up. That's 25 watts roughly into the dummy load. I've got the blower going. I know it's making a lot of noise. So I'm going to crank up the power and see what happens. SWR is 1.2 to 1, so that's really good. There's 50 watts. And the filament is actually moving around, so I can show that. Okay, there's the linear amplifiers on. That is just about 100 watts with the linear. It's crank up the output a bit. Okay, there's 300 watts. So to summarize, I built the dummy loads that I needed. The one with the light bulb for demonstrating pulse width modulation, and the other one for going outside and doing some measurements on some coax cables. Anyway, I hope you've enjoyed this. If you have, please subscribe. If you have, also give a thumbs up. If it didn't work out for you, do a thumbs down and let me know. If you have a question, post that below. We'll do our best to answer it. 7:30 for now. I'm Jim, W6LG, your YouTube Elmer in Rocklin, California. 7:3 from Smoky Rockland. You can hardly talk. It's so smoky. See you later. Bye. Hi. I thought today would be a good day to answer some questions about what's going on with me. Today I start a week of chemotherapy, which has been postponed about 10 times now. It's been postponed because my blood tests were not good enough for me to receive chemo. In other words, I wasn't healthy enough. My white count still is pretty much 0. Although there hasn't been much improvement the last couple of tests, it was decided that since it had been postponed so many times, we needed to get the chemo going. And what's happened during the start of chemo and up until now maybe will help some others. It has not been easy. Each time I've had chemo, I've been terribly ill. In fact, the week following chemo, I've been in the hospital as an inpatient. During the time when I wasn't in the hospital, which was not fun. The beds are not comfortable. The nurses have to wake you up every couple hours to do vital. I was in intensive care in isolation each time. And during the times I was home, that hasn't been so much fun either. My blood tests indicate that I'm not improving, so I will be meeting with the oncologist this week. We'll see what she has to say. Really nice doctor, and I'm very happy to have her taking care of me. The medication they're using is called Dacogen, and it has huge side effects, as do all chemotherapies, I suspect. Some of them have been things like, and along with the disease, just spontaneous vomiting, which isn't fun to talk about, but we've had to place strategically around the house stainless steel bowls to take care of that when it happens. And my wife has gotten good at swapping out the bowls as I have my head bent over and emptying out my stomach. The disease that I have was shown to be a little bit worse in the last bone marrow aspiration. The bone marrow aspirations, I've had 3 of those. They are the most painful thing I've ever been through. So the last time I got the doctor to agree to give me some pain medication, which was a large dose of morphine and fentanyl to really put me out of it, and that did help. For this video, I wrote some notes, and I'm kind of reading from them on a computer screen, not in any particular order. Bone pain has been at sometimes severe, and it's again part of the disease that I have. It's like somebody stabbing your bone with a knife. Much the same pain that I had when they were doing the bone marrow aspiration, as they stick in what looks like a little bit like a gun, almost like a squirt gun, and it goes into the bone and it sucks out bone marrow, and they have to do that several times to get a good sample. As they suck it out, it changes the pressure inside the bone,
and that hurts from your toe to your head. It is just unreal. The times I've been admitted, a couple of them were unplanned and unforeseen. One was I'm in Rockland, California. The next city up the highway is Lincoln. And in Lincoln, there's a Kaiser facility, so we would go there for the blood tests, and those are being done twice a week. So I get through with a round of chemo, and it's time to do a blood test, and my wife parks the car, and I get out. I'm using a walker at this point, and now I have to use a wheelchair. So I start to walk in. I run out of breath about 30 feet in on my way into the door. And again, I get to the door, and I'm out of breath again. And I get inside, and I go to register, and there's two people taking registration. They've got glass shields, and I'm wearing a mask, of course. And when I go to register, the lady that was doing the registration, who's also a phlebotomist, said, "Do you feel okay?" And I said, "Yeah, I'm fine. I'm fine. I'll be okay." Now, I had stopped for breath, and she didn't know it. So next place you go is around the corner for the blood draw, and there's like 3 stations. And one of the ladies is in the first station, and she looks at me and she says, "Sit down." And I said, "No, I think I'll stand. I just want to stand for a few minutes." And she said, "No, sit down. I'm calling for emergency people to come in and look at you," which they did do. They put me in another room. Nurses come rushing into the room from doctor's offices, and they have an EKG machine and the rest of the stuff. And one of the nurses says to the other nurse, "Call 911." So they call 911. Fire personnel arrive first, and so they're in the room, and it's just a little tiny room. It's maybe 10 by 15 at the most. And then next thing I know, the ambulance folks are there. So I asked them to call my wife, because she was in the parking lot, didn't know what was going on, didn't know it was me, saw the ambulance and the fire truck show up, and thought, "Oh boy, somebody's in trouble." Well, the person in trouble was me. So ended up in the hospital for a week. The diagnosis at admission was organ failure. Another time, we're home, and I'd had again a blood draw done, and on my left arm, from the side of the blood draw, it became inflamed. And we thought it would go away, and the next day it got really bad. And so it got so bad, and I was feeling so bad, that we called 911, which we normally would have just driven to the hospital. So they arrive, and again, I've got a massive infection that at that point had stretched from my armpit down to my wrist, and it was determined to be sepsis and cellulitis. So for the next week, I'm in the hospital with bags of antibiotics going in, and fluids, saline. So they're running that full time. And the other time we drove to the hospital, and it was again not fun. And not fun. At that time, I had to wait in the emergency room for hours to finally get in to see a doctor, and then I was immediately admitted, and should not have had to wait in the emergency room so long. But it was one of those things. Along with the 3 admissions to the hospital, again, I'm reading off a list. I've had 11 transfusions, which isn't good because it tends to create a lot of iron in the body, from what I've read, and my iron level now is sky high. And I don't know if I could have another transfusion if I needed it. They look at the hemoglobin. My hemoglobin right now is 7.4. When it dips below 7.2, at that point I'm just so weak that they do want to do a transfusion. As to whether or not they would do it again, I don't know. let's see, I'm still looking at my list. The medication they're giving is called Dacogen, Dacogen, and it has huge side effects. And the list is just really long. And it's pretty much anything and everything you could ever think of. And it's as if they've created this list from every kind of complaint they could have possibly gotten. As I said, the cancer cells have increased in my bone marrow, unfortunately. So I suspect when we talk to the oncologist this week that she's going to recommend yet another round of chemotherapy and perhaps a more powerful drug. I have a port now right here in my chest, which is irritating and itching, and it's under the skin. And so they poke through the skin and do a thing that looks like a pin cushion. They push in saline and then draw out blood when they're doing a blood draw. So now my blood draws are done in oncology because it takes a specialist and special equipment to do it. How am I doing otherwise? Folks have said you look pretty good in the videos, and that's true. Sometimes I've changed my skin color on purpose in post to try to make it look better than it is. I'm pretty gray. Right now my white count is terribly low, and my red count is even lower than it has been. So, videos. Folks who are watching this may be watching it because of the title where I'm going to mention the cancer. The videos that I do them on days where I feel better, not the best, but just better. And some days I have the energy to do it early in the morning. And so I'll do what I can do. And then sometimes the video's been recorded over several days because I begin to lose energy as I'm doing them. Also, on some days, like yesterday, I slept all day. Got up in the morning, had lunch. My son came by here. We did something together for a few minutes. And then I went back to bed. And next thing I knew, it was 7 o'clock. So I had slept virtually 12 hours at that point. So many days I sleep, not because of medications, just because of the fatigue that goes with. Some of it is with the chemo, the rest of it is with the disease. So a lot of days are spent just laying down in bed or sometimes just in the recliner. Back to videos. As I said, videos are a performance, and as such, I'm trying to perform. And in one of the videos back, I wanted it to be sort of entertaining and funny because of something that I was doing, and so that's part of it. I have to get myself going. Sometimes videos take several takes. Another thing that I'm going through is spontaneous falling asleep. I just sometimes will just head down and out of it. And it's been upsetting for me because sometimes I'm in the middle of recording a video and fall asleep, which when you're performing and you're trying to be up and excited about what you're doing and thinking about the process, to just immediately fall asleep is distressing. And so I've deleted those. I don't even want to look at them. I've fallen asleep during some Zoom meetings with a group of guys. And some of the folks that were watching that were upset by it, others concerned. A couple of folks expressed that maybe I shouldn't return to the group, and that seems to be the decision of a couple, and so I pretty much stayed away. The pain medications that I've had to take include oxycodone, but just one or two of those, hydrocodone, and tramadol, because the muscle pain and bone pain can really hurt, and there's not much you can do about it. And if you can't sleep sometimes, and which is my case, if I can't sleep, it's the only thing that I can really take and try to get some sleep at night. Again, if you have any questions, post them below. If you have any comments, post those too. And again, this is not a ham radio video so much as it is a video about how I'm doing, and it may relate to others who are going through the same thing. My name is Jim. I'm in Rockland, California. Thanks for watching, and I'm going to leave in a little while to go start the next round of chemotherapy.
Today is December 31st, the last day of 2022. That means that tonight, at least tonight here on the east coast of the United States, at 00 Zulu, which will be 7 p.m. Local time, starts the annual Straight Key Night, a 24-hour amateur radio operating activity where you focus on operating Morse code with a straight key. And that got to me thinking, is what's your straight key sending style? There are a lot of ways to do this. Let's take a look at them and let me know what you do. Now, many beginning operators will start off by just using a single finger to tap out the code. But I think you'll find over time that doesn't give you as much dexterity and consistency in the spacing of your sending. And other folks will actually do the same thing but with 3 fingers. And I think you run into the same problem with that. So most operators will migrate to a different style. Now, one style I see is to actually rest your wrist on the table and just kind of rotate your wrist or your fingers a little bit to form the letters. And again, some people do that by just pushing down on the key. Some will use multiple fingers. I find that I've migrated a bit more to a grip, and I think that's what a lot of more experienced CW operators do, is actually will grip the key, sometimes with maybe 2 fingers on either side, maybe one on top, or maybe another one underneath the lip of it, just to kind of grip the key and operate it that way rather than simply pushing down on it. So I'm curious, what about you? When you are approaching the key, are you gripping it or are you just kind of tapping on top of it? What's your style? Let me know. Now another piece of it is, what do you do with the rest of your arm and your wrist and that type of a thing? Are you one that will put the wrist on the table and just kind of rotate a little bit down to make the letters that way? I started off by doing that, but I've since migrated a little bit from that as well. Now if you watch some of the old US Navy training films for CW, their style they advocate is essentially gripping the key, but the wrist is off the table, but your elbow is on the table. And you're essentially kind of rotating, your arm to kind of make those letters, like that. And that seems to work as long as you've got enough room on your desk to put your elbow in. So I'll do that sometimes, depending on whether I've got the key positioned here where I can put my wrist there. If I have the key kind of over here at the edge of the table, I really can't do that. Now, most of the time when I'm operating, I'm sitting in front of my desk here, and there isn't a whole lot of room from where the radios are down to the edge of the desk. And I'll usually have the key kind of more facing me, this way. So I don't have a spot to rest my elbow. So I've kind of adopted a style that, from my understanding, is actually more common in Europe, kind of called a European sending style, where you're still gripping the key, but your entire arm is kind of elevated, and you're just kind of using some motion in your arm to kind of form those letters. And this is kind of the style that I've adopted. And to me, it works well. I don't send really fast, somewhere between 15 or 18 words a minute is where I'm kind of comfortable. So there's a lot of different ways to do this, depending on how you grip the key, whether you're resting your wrist, where your arm is laying, and how you're actually making the motions. So I'm really curious to hear your experience. What do you use? What's your style? Give me some comments below. And if you're really new to CW and you want to learn a little bit more, I'll also link down below another video that I did a few years ago on just the basics of Morse code in terms of the character spacing for the dits and the das and between letters and words, and the different ways of sending, from using a straight key to using a keyer with a set of paddles. So be sure to check that video with the link down below. Now the only other question for straight key night is, what key do I use? I've got this Bonnell key from the 1920s, which I used most of the time. I've also got a nice Chrome SpeedX, like J38 type of a key. Or do I use one of the little portable keys that I have? I've got this little Buddha key made of kind of cast aluminum, pretty nice key with a magnetic return. I've also got this little portable key that I made or built a few years ago from a kit that actually works really well. One of my favorite little portable keys is this tiny little Camelback key from Vibraplex. So which one should I use? Well, maybe I'll spend some time with each of them. Anyway, I hope to hear you on the air on Straight Key Night tonight, and good luck with your Morse code journey. 7-3, and Happy New Year. In this video, we're going to talk about a really cool little product. This thing is it's called a Motino. This is what it looks like. More information can be found at www.motino.com. It's made by Low Power Labs, and really what this is, it's an Arduino clone that's got wireless built into it. It is available without the wireless, even cheaper, but the really cool thing is when you include the wireless here. And it uses one of these RFM12B transceiver modules that operates at with a license-free bands at 433 or 915 megahertz here in the US and Australia, and 868 megahertz in Europe. Again, it's a kind of a Arduino clone type of product, and the other side of this here has got the RFM12B module on it. You can kind of see how that's soldered right to the back of the board. It's kind of that second small board sitting on top of the main board there. But really neat little product, and lots of really cool features. It's compatible with other Arduino clones that include the RFM12B modules, like the G nodes that are out there. It is available with some flash memory on there that can be used either for data logging or program storage, and the bootloader can actually recognize it if you've got code on there and reflash the chip and that kind of thing. It's a pretty cool thing. But so these, I've got loaded on here a couple of sketches that actually were put on there by the guys at Low Power Labs, and I'll show you a little bit about how this thing works. So I'm just going to set this one down here and hook it up to power. So I'll just hook up my power supply to this here, flip the power supply on. All right, and now this guy is transmitting here on this little blue wire antenna going into the antenna here in the analyzer. We'll go look at what it's doing in a moment, but you can see kind of the little flash of the LED there. It tells us this is go ahead and transmitting data, and it's transmitting over to a second one I've got sitting right here, and this one is hooked up through the FTDI interface to this little USB Bub2 FTDI to RS-232 converter board. This one happens to be from Modern Devices. If I can get that to focus there right or not, I don't know. But neat little board, and that's going over to my laptop over here. And actually what we can see with the serial monitor, this is the data that's being sent by that little remote node. Okay, it's sending just a sequentially longer ASCII string, and then every third transmission or so there's an ACK that goes back and forth between the two nodes. So you can kind of see that in the serial monitor here. And so it's just kind of showing that I've got some wireless activity going on between these two guys. And just to take a look at what's going on with them, I've got them hooked up to my Tech M0ODZ mixed domain oscilloscope. So I've got the RF signals coming into the antenna here, and then on channel 1 I'm probing the RS-232 line on the interface. So we're capturing all that onto on the scope. And what I've captured here is a couple things. Down here at the bottom is the spectrum of the signal. So we can see it's kind of centered right at 434.02 megahertz. I'm looking at a span of 2 megahertz here. And looking at the spectrum, the two peaks here kind of indicate that we've got a binary FSK modulation, which is what this thing uses. Up on the scope screen, I've got channel 1, which is the yellow trace here is the RS-232 interface. We can actually see data going through here. And the purple trace down here, it says RS-232. That's actually the bus decode of that. So we can actually see the data that was sent and then the ACK that was sent. This trace down here that says A, that's the RF amplitude versus time. So this is showing when the transmitter from that node turned on. Okay, sent its data, turned off. This lower power one is coming from the gateway node here. That's the acknowledgement that's getting sent back. So the modulation is a frequency shift keying, and this trace here is showing the FSK, so frequency deviation versus time for both of these things. And a lot of this will be easier to see if we zoom in. So if I just hit the zoom button here to zoom in a little bit. So now what we're doing is we're looking at a smaller portion of that signal here, zooming in onto down here. So it's pretty easy to see that there's my rising edge of the RF coming up. All right. Now if we look at the spectrum right during this very first part, it looks like we're just doing a quick kind of almost like a synchronization in the FSK. You can see what the spectrum looks like at that point in time. And then as we start sending data, let's kind of walk over. Now we're looking at the spectrum, over at this point in time. So we get a little more of what you'd expect to see of an FSK transmission. So this thing runs through the entire transmission here, okay? And when that transmission stops, then the RS-232 data gets sent from the Arduino across the RS-232, and we can see the actual data that's being sent there. So in this case, we just caught it when it was sending 1, 2, 3 and A, B, C, D, E. All right, and then the acknowledgement got sent back, and we can see the FSK of that acknowledgement, and then this is the decoded from that acknowledgement. I can go in here and let's turn the packets off on this, and then we can actually see the actual data that's sent kind of lined right up with the data packets. We zoom in on that a little bit more. You can actually see what the actually ASCII codes are within the RS-232 here, and then in the acknowledgement going back. You can actually see all the codes built right in there. But just a pretty cool little product, and I thought you might be interested in seeing it if you're messing around with microcontrollers and you want to do some wireless sensing, maybe some for environmental data collection or remote monitoring of water level in a sump pump hole, or whatever you might want to do with remote, or even some robotics. Really nice way to go for some low power wireless connectivity. So anyway, give it a try. Motino.com by Low Power Labs. Great support from these guys, and I look forward to putting these guys to some useful use, and I hope you enjoyed the video. Thanks again for watching. One thing that's great about this electronics hobby is that often one project will lead to another, and lead to another, and lead to another. And this is a good example of that. You may remember this project here. This all started by me creating this little sketch in an Arduino to draw out my ham radio call sign in XY mode on the scope. And that kind of came from doing some other XY projects with the scope. That led to another video that basically went through a digital to analog converter built of nothing but resistors, called an R2R resistor ladder DAC, or digital analog converter. We did a whole tutorial on how that R2R ladder works. So then that led to this project that you're seeing here, where we wrote a little sketch to take this 1980s vintage tech logo and make it look like it's spinning around on the screen as a little bit of an attention getter. So these projects just build on one another, and this led to the next project. So let's go take a look at that. The idea for the next project came after watching this video on YouTube. This is a 1930s vintage model 905 CRT, and it's kind of unique in that it's clear, so you can see the deflection plates and things like that. And Bob over at the Vintage Tech Museum in Portland, Oregon, put this video together to show the operation of the CRT. But what really caught my eye was that he was doing some nice XY graphics with a whole lot more resolution than what I did with my project. So I got in touch with Bob, and that kind of started the path for my next project here. So when I did the first XY project with my block letter call sign, I built this little R2R ladder DAC, and this is being driven by essentially an 8-bit port and a 6-bit port on the Arduino Uno, and so I had 8 bits of resolution in the X orientation and 6 bits of resolution in the Y orientation, and that worked okay for my low resolution graphics. Now when I went to do the spinning tech logo, I really didn't have any more requirements for higher resolution, but I wanted to make the design a bit more robust. So I built this proto shield up with all of the resistors to make the R2R ladder DAC, and that worked great. But both of these suffer the same problem in that the Y axis, if you will, has only got 6 bits of resolution. So in going back and forth with Bob, he said, why don't you just, why did you use 6 bits? I said, well, you only have an 8-bit port and 2 6-bit ports. And, he kind of gave me the obvious answer that I didn't think of was, well, why don't you just take 2 bits out of the other 6-bit port and get 8-bit, 2 8-bit, resolutions. It's like, oh, well, that's a great idea. So I built a more, even a simplified version of the a dual 8-bit R2R DAC. In this case, I used a pair of R2R resistor networks. Here's the data sheet for them. They're made by Bournes. They make a lot of resistor networks and things like that. So this is the format for the single inline package 8-bit R2R ladder that I used on this proto shield. So it's very simple on the top, and the back is just point-to-point wired, but even cleaner and a lot more robust even than my version with the sea of resistors. So now I've got a dual 8-bit R2R DAC. So that was the first step of the puzzle, to get the resolution up in both X and Y, or at least in Y, so that it matches X. So the next bit of it was to take a look at what Bob had done with his graphics. So Bob had actually worked at the graphics division at Tektronix, and certainly a real programmer, and I'm not. I'm a hack when it comes to programming. So so he was able to do this really fancy graphics. So he had sent me some information and sent me some code for the Arduino here. And one of the things that I saw when I started to read the code was that he uses this optimized implementation of this Bresenham's algorithm. And certainly this is a whole lot more advanced than what I was doing with my simple programming here. So Bob and I got to talking. He said, well, let me modify the code for you so you can do it with your 2 8-bit R2R DACs. Yeah, so here's the result of marrying Bob's sketch and my dual 8-bit R2R DAC. Now Bob did a couple things in the code that were a lot different than what I did. First was using this digital differential analyzer, Bresenham's algorithm. But what he also did is, since he's got so many more points that are being used to generate the graphic, those points are all stored in flash memory as opposed to the program memory inside the microcontroller. There's a lot more available space there, so that is a good logical choice to store the data. So the two graphics that we've got XY data for are this old Tektronix logo, which happens to match the same logo that's on this 465B oscilloscope, and there's certainly a lot of XY points in there. And the other graphic that you see is we call the Wizard. The Wizard is one of many little graphic cartoons that made an appearance in a lot of the Tektronix service manuals and schematics. And I think the Wizard first appeared on the schematic of I think it was the 454 vertical preamp. So if you actually look in the service manual for that, you'll see the Wizard sitting on the schematic. And there are, I don't know, maybe a dozen or more cartoons that you'll find hidden away in some of the old Tektronix documentation. So I just thought that was kind of an interesting story. And to me, now this really is a really nice attention grabber if you want to kind of set something up as a demonstration on a table. It's a really interesting way of just kind of showing some of the old XY graphics on a nice vintage scope here. So I really appreciate Bob sharing this stuff with me. And I thought I'd also take a few moments to talk a little bit about Vintage Tech and what that's all about. Vintage Tech, located in Portland, Oregon, was established primarily to commemorate Tech's kind of decades-long leadership in the analog CRT oscilloscope segment of the test and measurement industry. They're a charitable organization to provide educational and a scientific museum. They've got a ton of really nice restored scopes and equipment and things like that in their location. And they really commemorate the early history of Tektronix, and really Tektronix's role in spawning more than 300 high-tech companies in what's come to be known as the Silicon Forest, which is kind of the 4-county, 2-state metropolitan area around Portland, Oregon. Many companies, kind of owe their start to Tektronix. They are a fully independent nonprofit, 501c3 organization, and they do some really fantastic work there. They've got a fantastic museum of equipment. There's a lot of volunteers that maintain all the equipment there. They restore things. They also have several things for sale on the website, some excess materials and things like that. Lots of picture galleries and video galleries. Just a really great place. A couple of really great guys that kind of run the place. And if you're ever in the Portland area, I would definitely recommend going to visit them. They're only open, I think, currently 2 days a week. The hours you can find on the website here, 9 a.m. to 5 p.m. Friday and Saturday. But really great place. Take a look through the website, peruse around, look at some of the things that they have for sale. Just a great organization. And I've met kind of the founders there, Stan and Ed, and a number of the volunteers, including Bob, who basically provided all the code for this little project we talked about, and a lot of the other guys that do a lot of the restoration work and record keeping and things like that. But anyway, great place. I'll have some more information in the notes for the video here, not only for vintage tech, but I'll also give you some links for the code for today's project, a schematic for today's project, and whatever information I think might be helpful for you watching this video. Anyway, thanks again for watching, and certainly appreciate you being there, and we'll see you next time.
Hi, this is Jim, W6LG, your ham radio Elmer, here on YouTube. Welcome to my, no, this is not my radio room. Welcome to my hospital room, as it has been for much of the last 2 months in Roseville, California. So what's going on with me? Well, glad you asked. I have had a series of tests, and most recently a bone marrow aspiration. The results of the bone marrow aspiration indicated that I was not suffering from acute myeloid leukemia anymore. I had gone back to myeloid dysplastic syndrome, but there's something wrong with that, and it's going to be fatal for me. My bone marrow is not producing new blood cells. My bone marrow is not producing stem cells. It's not doing anything. So it has sort of died off. I talked to the oncologist 2 days ago now, and there's nothing they can do except ease my pain as I go through this. I'm hoping I'll be able to go home for a short time, but even that looks like it's not going to happen. So, it's all bad news. Doctor said that in the past I have lived longer than they expected, and during some of the admissions to the hospital, I survived when I was not expected to survive. But this one, it's not survivable. She expects me to live at the most a couple of months. I'm hoping to prove her wrong. My white count is at 1,000. My hemoglobin at roughly, I had a transfusion. It was 7.2. It went up to 8.4 with the transfusion. My red count right now is about 2. As I said, white count about 1. Other things sort of fall in line. So that's the update from me. I want to say thank you to everyone who has been so kind, and it has helped me out a lot. People have been very generous with their compliments and helped me through a lot of things. Several individuals have really been special in my life these last few months. You know who you are, and for that I am most grateful. I'm not sure if I'll be in condition to make another YouTube video. I want to get out of here. I want to get on the air, but it frankly does not look like it's going to happen. I've had some good doctors and some really lousy doctors while I've been in here. I've had some good nurses, and oftentimes some absolutely dreadful nurses who simply don't listen. At the moment, I'm taking Norco for pain, and that does help a lot. The pain sometimes has been severe. Anyway, it's been a rough road. It's been tough on my XYL also. I don't know what to say. That's pretty much the update. I hear some noise out in the hallway. It's likely that the phlebotomist is here to draw blood and do a CBC and white count differential. There's nothing else I can say. It's pretty upsetting, frankly. Again, to everyone, the most important thing I can say is to everyone, thank you. You've been very kind, and I appreciate it a lot. So, from Jim, 73, and we'll see what happens. If I can, I'll record another video. See y'all later. Bye.
Well, it's dark 30. Well, actually, 4:56. Means it's time to head out to the Hamfest. Well, the horizon is starting to get a little brighter. The sun should be up in about a half an hour. And there's a deer walking through the parking lot. Righty, well, here is the high school. Good thing we're only about 10 or 11 minutes away from the Hamfest site, so we didn't have to get up too early. A little after 5 o'clock, and getting there really early because I'm bringing a lot of the tables that are going to be used by some of the vendors, and the club table, and the announcement table, and the VEs. But looks like we're going to have a beautiful day. High 70s, low 80s. Looks like we're going to get some nice blue sky. So it should be a good day for a Hamfest. All right, early morning, getting set up. One or two vendors already here, but we should see a good crowd later on this morning. We got some test equipment available on the club table. And it looks like my friend Bob has got some tubes.
Yes.
What do you say, Bob? You got tubes?
Oh, I got lots of tubes. How many you want?
We lost our longtime club member and great mentor, Drew, this past year. And we'd always sit in this spot at the Hamfest greeting people and providing good information and great stories. So we just have a nice chair sitting out here for him to remember his presence here at the Hamfest. Pretty good crowd. Still got a decent number of vendors here. Got ARRL here. KJI is one of our vendors that's there along with the club table. But we lucked out with the weather, and everything really worked out well for the Hamfest this year. So hopefully things will return back to normal. We'll start doing more and more of this. And sometimes we get to see some really cool cars at a Hamfest. There's a 66 Barracuda, the 273 V8 in really nice shape, and you just don't see these cars. So very cool to have brought this out to the Hamfest here. And of course, it's right next to my friend Bob's radio flyer. This is a Pontiac sport wagon. So you might have, the old Vista Cruiser had that sport roof like this, but I had never seen one of these Pontiac sport wagons until Bob got this thing. It's got like a Skylark front end, but the back end looks like a Vista Cruiser wagon. Just a real cool machine. Bob does a lot of old radio work, and he put the radio flyer moniker on it here. Very cool. There's another interesting vehicle. It says Rover because he's got that thing outfitted to go and all over the country and maybe sit in some rare grid squares and work people from those rare grid squares. It looks like on a lot of VHF and UHF, given the size of the antennas there. Continuing the theme of unusual vehicles at Hamfests, there's something you don't see every day. It's a Chevy motor? Interesting.
Yep, a VTEC.
Look at that. Crazy.
Nice little headers on it. The headers and the exhaust system. I was looking at that. That's pretty sharp. Do you have to carry a spare belt with you? Very cool.
There's Pete, one of my favorite guys at the Hamfest. Say hello, Pete.
Hello, Pete.
Pete is the manual man. You need manuals for anything, you talk to Pete.
Thank you.
Check out manualman.com.
I'm a very impoverished person, so any help you can give me, I would greatly appreciate it.
We'll do what we can. Well, things are starting to wind down here at the Hamfest, and some of the vendors are leaving. Some of the more commercial vendors are still set up here. but I gotta wait around till everybody's gone so I can grab these tables up, load them up, and get them back to the rental place. Alright, we got most of the tables all loaded up here, just waiting for our last vendor to clear his stuff off the tables so we can load it back in the truck and bring them back to the rental place. And that's a wrap from the 2021 Raritan Valley Radio Club Hamfest in Piscataway, New Jersey. The weather held out good, but we'll see you all next year. Right, this video is going to take a look at the difficulties in trying to measure two signals that are at dramatically different frequencies at the same time. And it really comes down to playing a game of sample rate and record length in the scope. So on the signal generator right here, I've got two channels. One channel is putting out a signal at 1.5 kilohertz, and the other one is at 15 megahertz. Okay, so they're coming out here on channel 1 and channel 2 respectively. And bring them over here into the scope. So right now, if we're looking here at channel 1, this is the 1.5 gigahertz or 1.5 kilohertz signal. Look down here at a frequency measurement, I can see it's 1.5 kilohertz. And there's the signal on the scope screen, no problem. So if we kind of switch this over and put the 15 megahertz signal up on the screen here and kind of speed this thing up here a little bit, I can see that this guy is indeed 15 megahertz. Okay. So let's see what happens when we try to look at both of these at the same time. So I'll put the 15 megahertz signal on channel 2, the 1.5 kilohertz signal on channel 1. Let's bring this back down here. So there's my 1.5 kilohertz signal again. I look at its measurement down here. Everything looks good, 1.5 kilohertz. Let's turn on channel 2. Okay, well, doing that, I really can't see much on channel 2, right? So, what's going on there? Well, one of the things that we can see by looking at this is that we're running at just 10 megasamples per second, right? Because we're running at a very low sweep speed, effectively, or time scale, 100 microseconds per division, and at a 10,000 point record length, which is our default here, that translates to 10 megasamples per second. Well, 10 megasamples per second is undersampling this 15 megahertz signal. So I'm not going to get an accurate representation of that. And we can actually see that if we actually turn a measurement on here for that channel. Let's turn a frequency measurement on for channel 2. And we can actually see the frequency measurement is showing something, it's bouncing all over the place. It's like 5 megahertz, sometimes it's changing. Well, part of that problem is we're undersampling that signal. We're aliasing it. Okay, and if we kind of play around with sweep speed, we can actually see that signal doing all kinds of wacky things. That blue signal is the one that is actually 15 megahertz, and we're undersampling it here by playing around with the sweep speed. So it actually can look like a very, very low frequency signal here, but that's just because we're undersampling it. It's the same effect that makes wagon wheels go backwards in the old Western movies, because you've got this undersampled frame rate, if you will, undersampled sample rate. Or if we speed things up and do a single shot, I can very easily see that 15 megahertz signal, and there it is. But if I speed things up to see that, now I can't see the 1.5 kilohertz signal because it's running, it's too slow. I can't see even one cycle of it. If I slow things down so I can see, a cycle of that, I can't see anything on the 15 megahertz signal anymore. And it really comes down to what's going on with sample rate. Because as I bring the sweep speed up, or the time per division up, I get to the point where I can actually see, my high frequency signal. But that's because now, in this case, I'm running at 100 nanoseconds per division at 10,000 points. That gives me 5 gigasample per second that I'm running here. Okay, but now it isn't helping me in terms of looking at the lower frequency signal. So how do we get around that? The way we get around that is, let's adjust things for our low frequency signal. Okay, but now we're undersampling the high frequency signal, so we need to bring the sample rate up. Now the way that we do that is we're not going to change the horizontal time base, or the time per division on the horizontal scale. We're going to leave it at 100 microseconds per division. But now I want to do more sample points, so what I'm going to do is acquire more data. So instead of doing 10,000 points here, we'll adjust the record length to be something greater than 10,000 points. Let's bring it down to say, or up to say 1,000,000 points. Now if we do 1,000,000 points, now at 100 microseconds per division, 1,000,000 points gives me 1 gigasample per second. That's going to sufficiently oversample this 15 megahertz signal that I've got here, so I can accurately see it. So even though I've got a 1,000,000 points going across the screen here, okay, obviously the screen isn't showing all of them, but the scope is actually measuring on all of them. And this is something that's unique about, or not unique, but I should say there are scopes on the market that even when you set the record length to be very long, like we have here, 1,000,000 sample points, and some of the scopes will only make the measurements on the 1,000 or so points that are displayed on the screen. This scope doesn't do that. This one will make the measurements on the actual sample points, even if it's not showing all of them. In fact, if we do a single shot on this, I can see I've got an accurate measurement on frequency on both of these. And if I zoom in, okay, I'm just going to zoom way in on this. Okay, now I can actually see each of these measurements. So there's my high frequency one. I'm just kind of moving that back and forth. I can see my low frequency signal moving back and forth as I scroll back and forth through this record. Okay, we can actually see me walking through here, so you can actually see each of those signals at the same time. So the key here was to ensure that we captured both of these signals accurately by setting the record length long enough so that the resulting sample rate is high enough to oversample each of the signals sufficiently. And that's really the trick. That's all you have to do. In today's Circuit Fun video, we're going to take a look at an interesting op-amp sine wave oscillator. Not one that you read about very often. The oscillator we're going to look at is called a twin T oscillator, and it was suggested by one of my viewers. Now, in doing my research on this oscillator and this circuit, because you don't hear about it very often, I came across this really good application note or article from Texas Instruments dating back to, oh, guess what is it, 2000, by Ron Mancini. And he talks about the design of op-amp oscillators, in particular low-frequency oscillators that only use resistors and capacitors. Now, especially for low-frequency oscillators, just using R's and C's is preferable to using inductors, because for low frequencies, the inductors can get pretty big and bulky, where R's and C's can be kind of small and compact. So the goal here was to design and play with an op-amp oscillator that produces a low distortion sine wave and only using R's and C's. Now, I'm not going to go into the theory. This article actually does a really good job in talking about the theory of oscillators and what it takes to make them work, and actually goes through several examples of different types of oscillators, ranging from things like Wien-Bridge oscillators to phase shift oscillators, and a couple of other interesting ones, including one called a Bubba oscillator, as a quadrature oscillator. So I'll give you a link down below the video in the video description here to where you can go download this article yourself. A really good read, and if you want to learn a bit about the theory, that's a good place to go. Now again, the twin T oscillator is kind of interesting again because it uses only R's and C's, no inductors, and is relatively easy to get a pretty good low distortion sinusoidal output. So it's not easily tunable, that's one of its downsides, but if you need just a fixed frequency low distortion sinusoidal oscillator, it's a nice way to go. And then some minor trimming might be needed to get the lowest distortion. Now other RC oscillators that are op-amp based are a relaxation oscillator here. This one does not produce a sinusoidal output. It'll produce a square wave output and a triangle wave if you take the output from here, but it's not sinusoidal, but is super simple and pretty stable, and I've used this before when I've needed a simple square wave oscillator. Now for sinusoidal RC op-amp oscillator circuits, the RC phase shift oscillator is pretty common and just uses a series of RC delay networks to create a phase shift to satisfy the Barkhausen criteria for oscillation, and you need to trim its gain to get a good sinusoidal output. And this is covered pretty well in the article. Another very popular one is the Wien-Bridge oscillator. It is sinusoidal, but it generally needs some, again, special gain control to keep it from distorting. And oftentimes you see this done with an incandescent lamp that provides essentially a nonlinear load. So as the amplitude goes up, the lamp resistance changes and alters the gain. And by choosing the resistor and the lamp correctly, you can get low distortion. But to me, it's just kind of unusual to use a lamp in the feedback circuit. But again, it's documented pretty well in that article, and I invite you to go play with it. Another variation that's described in the article is to actually use an automatic gain control circuit around this using an FET in the place of the lamp, and have that controlled by a separate feedback loop to adjust the gain. And it all works and works pretty well, but it's also a whole lot more complex than what I'm going to show you next. Now, the twin T oscillator is based on something called a twin T network. The twin T network consists of essentially two circuits in parallel, both of which are T-style filters. So this first one, think of an RCR filter, and this essentially is a low-pass network, right? High frequencies are going to be shunted to ground, low frequencies will pass through, so it essentially has a low-pass characteristic, kind of similar to this in terms of response versus frequency. If we put in parallel with that, the corollary to that, essentially two capacitors in series and a resistor to ground, that forms a high-pass network. Okay, so its frequency response would look something like this. So if we take this guy and add it in parallel to that guy, we wind up with the twin T network. So with the twin T network, if we arrange the resistors and capacitors so they have this relationship, where if we get whatever value of R we use here, we use the same value here, and we use half that value down here, and then whichever value we pick for the capacitor, we use double that value here. If we put those things in parallel, these circuits will resonate at the same frequency, and what you wind up with is a combination of those two responses, and it creates a really nice notch filter. And if you ever need to notch out a particular frequency like 60 Hertz or 120 Hertz in a low noise preamp design or something like that, this is actually a pretty good filter to use, because this notch can be 40 or 50 dB deep and do a really nice job of nulling out a unwanted frequency. And of course the frequency at the notch is 1 over 2 pi RC. Let's actually take a look at the response of this twin T notch filter on the scope using a Bode plot. So I built the twin T network here on my proto board using some 10K resistors and 10 nanofarad capacitors. You can see here this is the 2 series R's, and these two capacitors in parallel double their values for the 2C leg going down. Then this is the 2 capacitors in series, and rather than taking two 10K resistors in parallel to half the resistance for the leg going to ground, I used a 4.7K resistor and a 500 ohm trim pot. And the reason I did that is when we configure this for an oscillator, we may need to tweak this value a little bit to get the lowest possible distortion, so I just built it up that way. I'm going to measure the frequency response using something called a Bode plot, and that is using the signal source in the scope to generate a signal that is being measured on one channel of the scope and being applied to the input of the network. The output of the network is being probed by the other channel, and the routine is going to essentially measure the input versus the output and plot both the magnitude and phase of the response of that filter, and we should see a nice notch response. Now I've configured the measurement to look from 100 Hertz to 20 kilohertz using 50 points per decade. Now since this is going to take a while, we'll speed the process up so you don't have to watch it. It actually takes several minutes to run because it's making 50 points for every decade change in the frequency that it's measuring. So we'll just let this run. Like I said, it takes a couple of minutes, so we'll just wait for this to finish. Okay, that measurement is done. Let's just zoom in on the results there a little bit and maybe reconfigure these plots to get a little bit better view of what's going on. So we take a look at this. The green line is the gain or the response through the network. We can see at low frequencies it's basically 0 dB. It basically just passes the signal through. And up again at 20 kilohertz, it's doing about the same thing. But right here in the middle, well, not quite in the middle because it's a logarithmic scale, we can see a notch that's well under 40, close to 50 dB down. So that is at that 1 over 2 pi RC. In this case, that's just under 1.6 kilohertz. The red trace is the phase, and where we see this kind of phase reversal, in there is where we're going to get our 180 degree phase shift, which will be necessary to sustain oscillation. So this is exactly what we expect to see from the Twin T notch filter. Now let's stick this in the op-amp circuit and turn it into an oscillator. Now by sticking this Twin T network in the feedback path of an oscillator, when this thing goes effectively to a high impedance at the notch frequency, that actually winds up causing an increase in gain of the op-amp. So what that really means is that at very low frequencies and at very high frequencies, this is a very low impedance, so we're going to get a lot of negative feedback and the op-amp is not going to do anything. But once we reach that notch frequency of this notch filter, that causes the gain in the feedback loop to be much, much higher, and essentially will amplify its own noise and things like that, but that's only going to happen at one frequency, so that's why we get an oscillation. I'm using a rail-to-rail op-amp here. It's a microchip MCP 6002, but just about any rail-to-rail op-amp will work, and even others that are not rail-to-rail will work. I'm using just a simple resistive divider to bias up the non-inverting input. In your case, in some cases, depending on the op-amp, you might need to add a little bit more positive feedback with a resistor, around from the non-inverting input to the output. But I've found I didn't have to do that in my case. And here's where I made that trimmable element. So rather than just putting two 10K resistors in series to get my 5K here, I elected to drop that resistor down a little bit and put a trimmer in there. And whenever I do this, when I want to trim up gain or something like that, I tend to try to take the ideal element value that I want to use and reduce it by about 5%. And then take a trimmer that's about 10% of that value to stick in series with it. So that gives me essentially a plus or minus 5% adjustable range around the target value. So that's why I picked those values there. Now with this adjusted properly, it's very easy to get sinusoidal total harmonic distortion well under 1%. Let's go take a look at that. So now here's the oscillator in operation. We can see just visually it looks like a really nice, clean, low noise, low distortion sinusoid. And if I take and adjust my trimmer here a little bit, you can kind of see that we reach a point where the oscillation goes away. And if I bring it back the other way, the oscillation will come back up. And we can see if we adjust it too far up, we can see we start to clip at the top and the bottom. That's going to create harmonic distortion. And we can adjust the value to till that is just minimized. We can see that be a little too far and the oscillation goes away. And we come back to just where it gets up there and just starts clipping a little bit. And that'll be the point where we have the lowest possible distortion. So we've got two different ways of looking at that level of distortion. First, let's just add an FFT on the scope to look at the harmonic content. So with the FFT added, I adjusted the frequency scale to go from DC to 20 kilohertz. And we can see the vertical scale here is essentially 20 dB per division. So but if we take a look at our peak signal here is up near that gradical right there. So there's 20, 40, there's 60 dB down. And here's the harmonic pieces, the second, third, fourth, fifth harmonic, etc. We look at those and they're more than 60 dB down. So that's actually quite good. If you go back and look at some of my previous videos on total harmonic distortion, you'll see that this will lead to a very nice clean response. I had to collect a little more data in time to get this resolution on the FFT, but we can see those results quite clearly. Now we can also take a look at total harmonic distortion with this Keithley 2015 THD multimeter. So let me go in here and probe the output. And we can see from here that the total harmonic distortion is 0.12 and change percent. So well under 1% total harmonic distortion. Well, I hope you enjoyed this little circuit fun video talking a little bit about op-amp sine wave oscillators, but in particular about the twin T oscillator, which you don't see written up very often, and make some pretty nice clean sine waves with an op-amp. So go build one yourself, go play with it, and let me know in the comments how well you do. I'll give you links to my notes as well as a link to the TI article that I referenced here in the video in the show notes down below. Thanks again as always for watching, and we'll see you next time. Hasta later. In today's video, we're going to talk about the basics of tunnel diodes, or you can call them the bucking bronco of the diode world. And we'll talk about what I mean by that term here in a moment. Most diodes that we run across, whether they're rectifiers or switching diodes, that we talked about diode switching in the past, or Zener diodes, or PIN diodes, or varactors, or even LEDs, they all share a common characteristic in that they generally will conduct current in one direction, block it in the other. Of course, the Zener is an exception in that case, where it'll break down, but they all have that same basic IV characteristic. Now, the tunnel diodes do not follow that same basic principle. The tunnel diodes were invented in the late 1950s by Leo Esaki, and there's some really good references that I'll link in the video notes down below. There's actually a lot of information online about tunnel diodes. Some of the original data books and text and tutorials on tunnel diodes from the late 50s and early 60s are all scanned and available online, literally hundreds of pages where you can go research the theory and details to your heart's content. So I'm just going to kind of give you an overview of tunnel diodes in this video, talk about their characteristics and some of the basic applications. Those tunnel diodes don't have, as I said, the normal IV characteristic of an ordinary diode. In fact, they've got this very unusual IV characteristic that looks like this. They'll conduct in the reverse direction like a low-value resistor, so they don't really block current in the reverse direction. So you can't think of them as a diode in that sense, but it is a diode because it's a PN junction. The really unique feature about the tunnel diodes is this forward characteristic, where you've got as the voltage across the diode is increased, the current increases, so it behaves like a low-value resistor at very low voltages. You reach a value of current called IP, and all of a sudden, if you increase the voltage beyond that point, the current actually begins to fall. And you have this kind of negative differential resistance region where the current falls with increasing voltage. So that's kind of a negative resistance characteristic. And then you reach a valley voltage where beyond that, increases in voltage will cause the current again to rise. So that portion of it looks a bit more like the regular diode characteristic, but in between here in this little region you've got this negative resistance characteristic, and this is the thing that gives the tunnel diode its unique characteristics and leads to the unique applications for a tunnel diode. The symbol for the tunnel diode is shown here. It looks a bit like, almost like a Zener diode characteristic, or even a Schottky, but both of these little legs are turned back towards the diode itself. So that's what the symbol, or one of the symbols for a tunnel diode is. There's a couple that have been used in the past, but that's the most common one that you'd run across. So this strange IV characteristic that has kind of this buck or this hump in it is one of the reasons why I call this kind of the bucking bronco of diodes. It kind of bucks the trend of what a normal diode does with this kind of weird humping characteristic here. But this negative resistance region where the current is falling with increasing voltage is a very unstable region to operate in, and because it oftentimes result in positive feedback in a circuit and other things like that. So we're going to see this can lead to some troubles with the diodes, but also leads to some interesting applications for the diodes. Now, this negative differential resistance, or NDR region of the diode, makes it even very tricky, remarkably tricky, in fact notoriously tricky and difficult to measure the IV characteristic, because the diode will tend to oscillate when you hook it up in kind of just a normal kind of IV curve tracer type configuration. So you can still kind of get a measure of where the peak current is and where the valley current is, but in this region you may not get exactly the shape because of the oscillation. So let's set this very simple thing up here and take a look at that real quick. Okay, so I've got this variable DC power supply set up here, who's sending its voltage essentially through the Simpson 260 on the 10 milliamp scale. So this is being used as an ammeter here to measure the current. Then that comes out and goes through the diode and back to the power supply. And then so that'll monitor the current through the diode. And then this multimeter is set up across the diode to measure the voltage. Okay, so as I turn the voltage up, we can see that the current is rising on the Simpson meter over here, and we can see the voltage is rising. So if we get up to right about mid-scale here, there's 5 milliamps of forward current through the diode. You see the diode sitting at about 33 millivolts, so we're kind of right on this portion of the curve right here. If I keep turning the voltage up, okay, now we're up to about 60 millivolts or so forward voltage, running close to about 8 milliamps or so. Keep going up here, and watch what happens right here as I turn the voltage up a little bit further. We are sitting right now at about 8.5 milliamps, about 90 millivolts. A little bit further increase in the voltage now. So now I can see I'm up to close to 200 millivolts or so on the diode. The current is falling, so we're walking our way down this curve here now. If I keep increasing the voltage across the diode, we can see the current really dropped off here. And we're now at 373 millivolts. And we keep going, and we can see now the current is coming back up again. So we went down through the valley, now we're walking back up the other side of this curve. Now, so that's kind of the traditional, classic characteristic of a tunnel diode in terms of what the voltage and current relationship is. Now, one thing you may have noticed when I was doing this is that even though I was bringing the voltage up very slowly and fairly linearly, the current dropped off pretty sharply right here. As I keep going up linearly, it dropped off very sharply again down there. And that's kind of an indication that there's some oscillation going on. So instead of getting this really nice curve, we're reaching a point where it's dropping quickly and then kind of going shallow for a while, then dropping quickly again and then coming up. So let's actually take a look at that by putting the scope probe on there. We can actually see what's going on. So now I've got the scope probe hooked up across the diode here, and we can take a look at what's going on across that diode as we sweep through this IV characteristic. So if we walk up from 0 voltage, start turning that diode voltage up, we can see the current rising linearly, everything's fine, the voltage is coming up linearly, it's coming up on the scope, no problem. We cross over the peak, get into that negative differential current region, or negative differential resistance region, and we can actually see the oscillation on the scope. We can see that the current has dropped down, so we've recognized it as a tunnel diode. As we keep walking our way down towards the valley, we can see the oscillations start to change, go to a high duty cycle, and then eventually go away. And then the voltage is just going up normally on the far side of the diode characteristic. But as soon as we bias ourselves within that negative differential resistance region, we see this thing busting into oscillation. Now what that means is it would make it difficult to actually accurately measure this portion of the curve, but if you just want to check to see if a tunnel diode is working right, you can kind of ignore the fact that you're not accurate in terms of where you're measuring this, but just the fact you can actually see that a dip in the current as the voltage is increased on the ammeter is sufficient to tell you that the tunnel diode is working. And you could also tell as you're bringing the voltage up. Let me kind of work my way from 0 again. As we bring the voltage up here, we can see that we clearly reach a peak point where the current will kind of peak and then start dropping. And that would be essentially this point right here in the IV characteristic. Now it is possible to surround the tunnel diode with various components, resistors and capacitors and things like that, to stabilize this. But it turns out that the actual values that you need to surround this diode with are going to depend pretty highly on the particular diode characteristics, the slope of the negative differential resistance region of the diode, the capacitance of the diode, the current that it's operating at. All of these things are parameters that you have to take into account when designing the circuit that goes around this diode to keep it from busting into oscillation like this when you make the measurement. So for our purposes, it's not that important for us to kind of squelch that oscillation out, but just to recognize that we actually do have this basic shape as we increase the voltage across the diode is enough to tell us that, hey, this is a tunnel diode, and that characteristic is indicates that the tunnel diode is still in operating condition. Of course, when these tunnel diodes were developed in the late 50s, early 60s, semiconductors were still pretty new. And the speed at which these diodes could traverse this negative differential resistance region was tremendously fast. Well under a nanosecond, some of the fastest semiconductor devices available. So there's a lot of work that went into looking at ways of exploiting that characteristic. Things like there are various types of oscillator circuits, monostable and astable type switching circuits, trigger circuits for oscilloscopes was a big application, logic circuits and things like that. And again, the references that are in the show notes will have, some of the data manuals for the tunnel diodes will have examples of different types of circuits. So we're just going to look at a couple here. So let's look at the operation of a simple relaxation oscillator. We've got a voltage source here that we're going to bring up to about 1.5 to 2 volts. And along with these resistors is going to bias the tunnel diode just past the peak current. And what happens as that voltage is coming up, that increase in voltage causes an increase in current. That positive di/dt causes a positive voltage to appear across the inductor. As that voltage crosses, or as the current crosses IP, as that voltage comes up, that current wants to start coming down in this series string. That change in slope of the current is going to cause this inductor to react by trying to maintain that current flow. And by doing that, it basically slams the voltage all the way across over to the other side of the curve here very, very quickly. And so as soon as that happens, now the voltage is higher than the voltage that would appear normally because of this voltage source. So the current starts coming down. As that current comes down, it reaches the valley point, and at which point we start hitting that negative differential resistance again, and we get that same reaction for the inductor, but now in the opposite direction. That slams you back over to this side of the IV curve very quickly, and then the voltage starts rising and the process repeats, and the thing just bounces around here. So let's take a look at that operation on the scope. Okay, so I've got my tunnel diode here, a couple of pair of resistors. I've got a 220 microhenry inductor here, and the oscilloscope probe is looking at the voltage across the inductor. So if we start turning the voltage up, we'll reach the point where we essentially cross into that negative differential resistance region, and now I can actually see the oscillation here on the scope. You'll notice that as I move the voltage up and down, I can actually change the frequency and duty cycle of that oscillation. So it's pretty sensitive to that. But we can actually see this behavior of this thing slamming, from one side of the curve to the other side of the curve, back and forth, just like we showed in the IV diagram. Right, so this thing's oscillating, about 38 to 39 kilohertz or so, and again is a little bit dependent on where I set the bias. And of course, the frequency of oscillation is depending on a lot of things. The bias is depending on the parasitic inductance and capacitance of my board and things like that here, and the capacitance of the diode and things like that. Well, in fact, if I pop out this 220 microhenry inductor, and let's pop in about a 3.6 microhenry inductor here in its place, you can actually see the frequency has gotten a whole lot faster, as you'd expect. If we turn that up here, we can actually see that's running at about 2.25 megahertz by simply changing that inductor value. Now, of course, as I said, this is going to depend a lot on diode characteristics and things like that in order to get a particular oscillation frequency. So one way to make it a bit more controlled and less dependent on the diode characteristics and the parasitics of the circuit is to simply replace just the inductor here with a tank circuit. Of course, what I mean by that is simply putting a capacitor in parallel with the inductor here that will kind of dominate the frequency characteristics. So I'm going to use that same 3.6 microhenry inductor, and if we put a 6.8 nanofarad capacitor in parallel with that tank circuit is going to result in a frequency of about 1 megahertz. And because the impedance of this is really only going to be high essentially at that one frequency, we're going to take a lot of the other harmonic content of that oscillation that we see out of the circuit, and the oscillation that we see here will be a bit more sinusoidal. Okay, so let me pull out this 3.6 nanohenry or 3.6 microhenry inductor. I'm going to replace it with this basically the same type of inductor, but now with a 6.8 nanofarad capacitor soldered in parallel with it. So now I can actually see the oscillation is a bit more sinusoidal. Of course, there's still some distortion in it, but a lot of the other harmonic content is gone. And now the oscillation is going to be less dependent on bias and less dependent on the diode. Now, this is an extremely simple oscillator. There's lots of ways to improve it, but it just shows that with just a small handful of components, how easy it is to create an oscillator with these tunnel diodes. Okay, so the last application circuit we'll consider here is a monostable trigger circuit, and this is basically the application of how these diodes would be used in an old analog scope to essentially kick off the horizontal sweep on the old analog scopes. If we set up a constant current source, and that's what this is, a constant current source that biases through this inductor, biases the diode at a constant current level, okay, kind of indicated by this dotted line, we can see that that line crosses the IV characteristic in 3 spots. So you could say that the voltage that it appears across the diode could be one of these 3 voltages. Well, the reality is, we've kind of learned with the relaxation oscillator, is that because of the series inductor, that this spot would be unstable. So we're either going to be sitting here or here. So when we first turn the circuit on, the diode starts from nothing, and as the current comes up, we're going to basically land at point number 1. And the way that this trigger circuit works is that you provide a small input voltage, okay, a little input pulse that I'm going to do with my little function generator that couples into the bias of this diode, and just enough to push the voltage on the diode above, past this point, to essentially get ourselves up over the hill. And then as soon as we cross over into the negative differential resistance region, the inductor is going to cause this the voltage to slam all the way over to point number 2 very quickly. And that's how the old analog scopes utilize this, that very fast rising edge going from this voltage to this voltage was used to kick off the sweep, and the faster that edge was, the less jitter you'd have and the more stable trace you'd have for a given trigger input. Okay, so I've got that circuit set up on the lower half of the board here. I'm coupling in my signal generator to the inductor at this point, and I'm measuring the diode voltage with the probe here on the scope. If I flip on the power supply to turn on the current source, you can see the voltage across the diode jump by 60 or 70 millivolts or so. When I hit the trigger button here, we can see that the diode voltage will switch from the low voltage state to the high voltage state on that IV curve. We need to take a single shot measurement to really kind of capture that edge. Okay, so let's reset the tunnel diode to the low voltage state by turning off the current source and back on again. Put the scope in single shot mode and trigger it to capture one edge. And with that one edge captured, we can just quickly zoom right in and see that the rising edge there is on the order of, let's see, it's a nanosecond per division, so it's a little bit under 1 nanosecond. Now, of course, that's not taking into account any particular layout here to really increase the speed. I'm using the really long leads on the diode and that kind of thing, so it's probably even faster than the sub-nanosecond that we're seeing here, even with this pretty crude fixture that I've got put together. So that's just one example of how you could use the bistable nature of the diode characteristic here to create a fast edge from a trigger source. So I hope you enjoyed this little tour of tunnel diodes, what they are, what their characteristics are, and some of the applications. Again, I encourage you to take a look at some of the links that are in the video description. There's a couple of really good resources on tunnel diodes, some of the original manuals that were written by GE and RCA, covering applications in theory and circuits and all that kind of thing. So anyway, thanks again for watching, and I hope you enjoyed it. Please subscribe if you haven't done so already, tell your friends, and we'll see you next time. Thank you.
This is the start of a bonus video series and probably not for everybody. We will build a satellite station to reach a geostationary amateur satellite 36,000 kilometers away. In the end, I should be able to talk to other amateurs using this ground station. First, I did not plan to do this video, but many of my viewers asked for it. And because such a complex project will cover many areas, you might profit from one or the other episode, even if you are a typical maker and no radio amateur. What do you think? Should I continue with the series? Grüezi YouTubers, here is the guy with a Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. The most important part of a project is its goal. It should be smart, as many people say. Smart means a goal should be specific, measurable, attainable, relevant, and time-bound. So let's start with our project. Its purpose is to talk to a radio operator at New Mayer Station 3 in Antarctica from my home. To achieve that, I will use the QO100 transponder, which is part of a larger satellite and is given to the community by Qatar Telecom. And the first communication, in amateur radio speak called QSO, should take place before my summer holidays. Frequent viewers of this channel know that I was able to bridge 200 kilometers with a small 868 MHz LoRa transmitter and 3 kilometers with a LoRa transmitter on 2.4 GHz. But how can I reach 36,000 kilometers? Including the return way, it is 72,000 kilometers. Crazy. What do we need? We need a so-called uplink on 2.4 GHz and a downlink on 10 GHz. The transponder in the satellite has a simple job. It mirrors all signals received on 2.4 GHz and sends them back to Earth. So we have the essential components. A high-power transmitting path for 2.4 GHz, which is capable of reaching the satellite. And a sensitive 10 GHz receiver, which is capable of receiving the weak satellite signal. The transmitting path consists of a modulator which creates a signal on 2.4 GHz, modulated in single sideband, short SSB. A series of amplifiers to get at least 20 watt output. A high gain antenna using a feeder and a 80 cm dish. The receiving path consists of a standard low noise block down converter, short LNB, also used for TV satellite reception. This LNB receives the 10 GHz signal and converts it to around 800 MHz. A 800 MHz receiver which can demodulate SSB. Fortunately, we can use an ADALM Pluto, a relatively cheap software-defined radio, as a modulator and a receiver. And SDR console to control it. Because I want to avoid long cables at high frequencies, I want all these things closest to the dish antenna. This is why I need an internet connection to the ADALM Pluto. If you want to know why short antenna cables are essential on high frequencies, you can watch videos number 219 and 220. The last thing we have to talk about is frequency stability. An SSB signal has a bandwidth of around 2 kHz, and you start to hear Mickey Mouse voices if you shift the signal by just a few hertz, as you see and hear here.
J'utilise actuellement un module Wi-Fi booster qui est au foyer d'une parabole de 80 cm. Et pour éliminer la parabole, j'utilise encore un cadeau de Gérard F5LY. C'est une big quad.
Can you imagine how stable the modulator and the receiver has to be to avoid Mickey Mouse voices? By the way, we just listened to QO100 using a receiver in the UK, which is very stable. Let's assume a drift of 50 Hz, and the receiving frequency is 10.48 GHz, equals 10.48 times 10 to the 9th. A typical quartz resonator has a stability of up to 20 ppm in outdoor conditions here in Europe. This is not usable for our needs. We get 0.5 ppm oscillators for the ADALM Pluto. Better, but still not what we want. Rubidium sources are the next level up. They are called atomic clocks, and you get them ready-made at, for example, DigiKey. Fortunately, they are cheaper than an atomic power plant and less dangerous. But they easily cost $2,000. Maybe you get one used on eBay. Definitely not the way I want to go. Fortunately, we have such frequency standards available as a free of charge cloud service. All GPS satellites have such stable clocks built in, and we can use them here on Earth by building or buying a so-called GPS Disciplined Reference Oscillator, short GPSDO. So we need one of those to stabilize the ADALM Pluto SDR, as well as one to stabilize the down converter for the LNB. Both contribute to the frequency shifts if they are not stable. That's it. I will start with building the transmission line, because the 20 watt amplifier comes from China, is very expensive, and I want to test it before purchasing protection runs out. This is all for today. Please comment if you are interested in this topic or not. One last thing. The ham operator who currently works in Antarctica is another guy with a Swiss accent. As always, you find the relevant links in the description. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. Thank you. Bye.
Today's Back to Basics topic is an introduction to the field effect transistor, or FET. And we'll talk about JFETs and MOSFETs and different polarities, N channel and P channel, and the different types, depletion mode and enhancement mode devices. We're just going to cover some of the basic characteristics of FETs so you can understand what you're looking at when you find them in the wild. When we talk about an FET, we talk about the channel. The channel really refers to the path between the drain and the source terminals of the device. And we'll see how we apply that a little bit later. A good analogy that helps people to understand FETs is this pinched garden hose analogy. Picture a garden hose with the drain and the source here. Water flowing through the garden hose is like the current going through the channel, where the hose is the channel. And then the voltage on the gate with respect to the source determines how much we're pinching off that garden hose and restricting current flow. We'll talk more about the operation of a FET in a moment, but let's first take a look at the FET family tree to understand how the types and polarities and modes all relate to each other. Now, the first major distinction is between the JFET and MOSFET, or the junction or metal oxide FET. We'll cover details of the differences in construction between these two shortly. Under the JFET, all the JFETs operate in what's called the depletion mode, which means that without any bias between gate and source, the channel conducts current, and then by bringing the gate down below the source voltage, we start to close off and control the current or shut the current down. The MOSFETs can be built either as depletion mode or enhancement mode devices. The vast majority of the MOSFETs that you find are going to be enhancement mode devices. Enhancement mode means that the channel essentially does not conduct current when there is no gate to source bias, and then you change the gate voltage with respect to the source to enhance the channel and allow it to start conducting. The depletion mode MOSFET behaves very similar to the depletion mode JFETs. While you can also have depletion mode P-channel devices, I don't know that I've ever seen one in 30 years in the industry. There are N-channel depletion mode devices, but they're not very common as compared to their enhancement mode brethren. Again, we'll cover the depletion mode operation and enhancement mode operation here shortly, but I just wanted to kind of give you the family tree to kind of understand where all these terms fit within the family. Now, regardless of what we're talking about in terms of FETs, they all have some key common characteristics. That the gate input draws virtually no current, just a very, very small amount of leakage current, has a very high input impedance, and they're typically very efficient in switch applications. And there's certainly a lot of other characteristics too. Certainly there's been chapter and verse written around FETs, but these are the major differences compared to, say, bipolar transistors. So let's dig into how these FETs operate. So the first thing we'll talk about is the difference between depletion mode and enhancement mode. And again, depletion mode means that the channel is already filled with carriers when there is 0 volts between gate and source, and then we control that current by depleting carriers out of the channel as we change VGS. Enhancement mode devices means that the channel is void of carriers when we have a zero bias on gate to source, and then we control current by enhancing the channel with carriers by changing VGS. So this table might help with the understanding for depletion and enhancement mode devices. This table is kind of written around N-channel devices. So for an N-channel depletion mode FET, the channel is on, meaning it conducts current when the gate to source voltage is equal to 0. And that's this point on this curve here, where we have IDS, or drain to source current, when VGS is equal to 0. And then as we bring VGS below 0, or negative, meaning we're bringing the gate voltage down below the source, we're starting to restrict and turn that current off. For depletion mode devices, we generally never operate with the gate to source voltage positive, meaning we're never going to bring the gate voltage above the source voltage. Now for enhancement mode devices, the channel is off when we have 0 volts from gate to source. Okay, so that's this point on this curve here. Gate to source voltage 0, no drain to source current. And then as we bring the gate voltage above the source, making that greater than 0, then we start getting current going through drain to source. So this is enhancement mode operation, and this is depletion mode operation. And similarly, just like we don't operate here for depletion mode devices, for enhancement mode devices there's really no need to bring the gate voltage down below the source voltage because the channel is already off when VGS is equal to 0. Now, most of the discussion in today's video is going to focus around N-channel devices, but to understand P-channel devices we just have to turn everything upside down. What I mean by that is that for P-channel, all the terminal voltages and all the currents are simply opposite polarity as they are for P-channel. And this is very similar to the difference between PNP versus NPN devices for bipolar transistors. So here we can see that for a N-channel device, the drain current is kind of defined going from drain to source in this way for conventional current flow. And then for P-channel devices, see I've driven things kind of upside down here. The source is now on top, so the current flow is now going essentially from source to drain. And then when the drain voltage, essentially for N-channel, the drain voltage is greater than the source voltage and the drain sinks current. For P-channel, the drain voltage is less than the source and the drain sources current. And so even though we're going to focus primarily on N-channel devices today, you simply can turn things around and take all of these same discussions and apply them to P-channel devices. One more thing to be concerned with and careful about when dealing with FETs, particularly small signal FETs and like TO92 packages, is watch the pinouts. You know, this J310 JFET has got a different pinout than this 2007 or 2N7000 MOSFET. So you do have to kind of be careful, check the data sheets to be sure you get the pinouts right, because it may differ whether we're talking about a JFET or a MOSFET or different other types of devices. So let's start off talking about the JFET or junction FET. It's called a junction FET because it's constructed with a PN junction. The N material here has got a lot of carriers in it, allowing current to flow from the drain to the source. However, when we reverse bias this PN junction, we create a depletion region, essentially depleting an area to make it void of any carriers. Therefore, the channel that's left becomes more and more resistive and restricts more current flow. So essentially we never forward bias this junction, and we get the most current flow when VGS equals to 0, because that's when the depletion region is the smallest. Okay, so you can think about this almost as a voltage dependent resistor, okay, where the more negative we make the gate to source voltage, the less current that will flow as a function of VDS. So you can see we can get this kind of different slope to the voltage and current curve, essentially different resistance values, by changing the gate to source voltage. Now the size of this depletion region, like we said, is controlled by the voltage, but in reality it's the electric field that's set up by that voltage that causes the carriers to move around. So that's why it's called a field effect transistor, because it's the electric field that affects how the transistor operates. Now what I've described right here with this variable resistance versus gate to source voltage is a region of operation called the linear region for the FET. And it's really only valid for low values of VDS. As the drain source voltage increases, there's another effect that goes on here that we'll talk about shortly. But let's take a look at the linear region here first. We're going to take a look at this operation in the linear region with this little test circuit. This will be the transistor that I'm testing, and I've got a variable voltage source, power supply, sitting between gate and source. And note the polarity here, where positive and negative here, meaning that I'm going to bring the gate voltage down below the source voltage. And I've got a DMM sitting at the gate so we can see what VGS we're applying. We're going to apply a sawtooth voltage from a function generator essentially to the drain of the device. And I want to measure the current IDS. Now I don't have a current probe to go measure IDS, so I've basically constructed this little current mirror. Okay, just a couple of kind of PNP transistors here, 2N3906s, so that as whatever current is flowing here is going to be mirrored coming down here. That allows me to dump that current into a resistor, and I can measure the voltage across that resistor with respect to ground, which will give me a voltage that's directly proportional to the drain to source current. So since I don't have a current probe, this is a good, easy way for me to generate essentially these curves, of voltage versus current on the scope in XY mode. So this is the same test circuit we'll use when looking at all the rest of the FETs in the rest of this video. So I've got a J310 N-channel JFET sitting here in my little test board. These two transistors up here are that little current mirror. And then this is the XY display showing VDS, or drain to source voltage, in this direction, and essentially the representative of drain current flowing in that direction. So we can see with negative 4 volts VGS, meaning that the gate is 4 volts below the source voltage, I essentially have no current. This thing looks like an open circuit. I reach over to my power supply and start reducing the VGS. We can see, and now I can start seeing the effect of, looks like a resistor. Okay, as we keep coming up here, we can see this thing is just we're just changing the resistance of that channel by adjusting the gate to source voltage. So this is, again, what we call the linear region of operation, where we're just going to get a nice linear resistance, if you will, versus VDS. So a linear current change versus a linear drain to source voltage. So that's why it's called the linear region of operation. Now as the drain to source voltage is increased further, we transition from the linear region to the saturation region of operation. Because what happens is the depletion region is not only affected by the electric field of the gate to source voltage, but it's also affected by the electric field between the drain to source voltage. So what that causes, instead of the depletion region kind of just being bounced around the junction, it kind of gets pulled and skewed due to the field from the drain to source voltage. So we can kind of get this kind of weird shape to that depletion region. And as that happens, we start pinching off the channel more and more up here, even for a given gate to source voltage. As the drain voltage gets higher, we pinch the channel off more. So that causes things to kind of deviate from that nice linear resistive behavior into what we call the saturation region. And what that looks like on that same set of curves is this here. At these low values of VDS, we kind of have this just linear change in resistance kind of in this linear region down here. But at larger VDS voltages, the curve starts to flatten out. Okay, and we call that the saturation region. Now, most applications for things like switches, the devices are used in the linear region with very low VDS. And most applications such as amplifiers and mixers and other places where FETs are used, that operation is often occurs here in the saturation region. Now, as I mentioned, we never forward bias the gate to source, so the most positive the gate gets was essentially equal to the source voltage value. And at that value, the drain current maxes out due to this effect at a value called IDSS. So that's essentially the maximum current for a JFET is IDSS, and that occurs again when VGS equals to 0. Alright, so let's kind of zoom out here and take a look at at that behavior, and we can actually see, there we go, we can actually see that behavior of transitioning from the linear region into the saturation region. And as I change the gate to source voltage, we can actually see we'd actually have that family of curves that I showed you on the piece of paper. Yeah, so again, the linear region here is really where the depletion region is dominated by just the gate to source voltage, and then we flatten things out here because the field due to the drain to source voltage starts to pinch off the channel a bit more. So just to review, all JFET devices are depletion mode devices. There are no enhancement mode JFETs. The channel is controlled by depleting the channel of carriers by expanding or shrinking the depletion region, and that can be a combination of VDS or VGS and VDS, or a combination of the two, depending on which region we're operating in. One really nice thing about JFETs is that they're really super easy to bias. This is a very, very simple bias scheme that's very commonly used when using JFETs. We don't, like a bipolar transistor, we don't have to set up resistor dividers or anything here, because what will happen, let's say in this case here, where we ground the gate through a large resistor, there's no current flowing in the gate, so we don't have to worry about really any voltage appearing across this. So essentially the gate sits at ground until there's an input signal. When the gate is at ground and the source is essentially grounded through this resistor, the current that flows here is going to be what? IDSS. So as that current flows, the voltage generated across the source resistor raises the voltage of the source up. That effectively creates a negative VGS, thereby reducing the amount of current. So it's kind of a self-biasing type circuit where the source will increase to the point where the VGS just kind of supports that current, so it's kind of a balanced condition. So a simple one resistor or two resistors needed to bias a JFET. Very, very simple type of deal. So next let's take a look at a MOSFET. A MOSFET is constructed a bit differently. The gate is not essentially a diode with the rest of the device. It's actually insulated by an oxide. Well, it used to always be, but now there's other techniques that are used. But in effect, the gate is insulated from the body of the device. Now for an N-channel device, there are N contacts kind of diffused in to create the drain and the source contacts. Again, the gate looks like a capacitor, so to speak. And that's all kind of built onto this kind of P-type material or body of the device. So without any bias on the gate, there's just a natural depletion region that will occur just due to this kind of PN junction. And because we have this depletion region, the channel between these two contacts is essentially void of any carriers, and therefore the channel is off. So this is an enhancement mode device. When the gate to source voltage is increased above 0, carriers are drawn from the body of the device into the channel, thus allowing drain current to flow. So it's again the electric field of the gate to source voltage that enhances this channel or allows current to flow. Now very similar to the JFET, at low drain to source voltages, that depletion region is somewhat uniformly controlled by the gate to source field or electric field. But as the drain to source voltage increases, that field tends to skew just the same way as we saw with the JFET. So you get the same linear and saturation regions in the MOSFET that you get with the JFET. In general, with the MOSFETs, the linear region is a bit shallower, meaning we can get much lower resistance values for the MOSFET. So it makes the MOSFETs pretty ideal switches because they can have very low on resistance in that linear region. And also now you'll find that the saturation region here, you typically get a bit flatter response, much higher essentially output impedance, if you will. They think about it that way with the operation of those devices. Okay, so let's take a look at some of those curves on the scope, just like we did with the JFET. So what I've done is I've replaced the J310 JFET here with a 2N7000 enhancement mode N-channel MOSFET. I reversed the connections of this variable power supply so that I can adjust VGS from 0 to positive values. But those are the only other changes I made. So again, this is an N-channel enhancement mode device. So with 0 volts gate to source, the device is essentially off, very, very high resistance. As I bring the gate voltage up, we'll start to conduct, and now you can actually see here's the linear region here, and then we flatten out into the saturation region. In this case, I've got about 1.6 volts of VGS. Now you can see as I keep bringing that up, you know, the current here, or the resistance, is actually getting pretty steep. Okay, but again, MOSFETs typically can have a very low RDS on, which is the drain to source resistance in that linear region. So we can see it's very easy to control the amount of current that we can get in the saturation region, where you typically use it as an amplifier or other linear applications like that. And then we could also see we've got a pretty nice, easily controlled low value of RDS on, which is useful for things like switch applications. Now, as I mentioned, there are depletion mode N-channel MOSFETs. They do exist. They've got some applications in power applications for things like maybe high side switches or normally on switches or constant current devices and things like that, but they're not real common. You know, the vast majority of the MOSFETs you'll find out in the wild are enhancement mode devices. In a short introductory video like this, it's really impossible to talk about all the aspects of FET operation and really to get into any of the applications in any depth. But I hope that this introductory video has given you an idea of the difference between a JFET and a MOSFET, and depletion mode and enhancement mode devices and how they operate, and what controls the difference between the linear region and saturation region of operation of these various devices. Comments are always welcome. Thanks again for watching, and we'll see you next time.
Well, I was a building inspector. And just a quick summary of my background, a lot's changed, and I don't consider myself an expert anymore, but I was employed by two counties, Los Angeles County and Nevada County. I worked as a real estate appraiser, deputy tax assessor, deputy building inspector. I was on the fire code board, the building code board, the building code board of appeals. I was a planning commissioner. I helped write 2 general plans. I had a general contractor's license. I had an advanced appraisal certificate from the state of California. And I did expert testimony in Superior Court. Also held a real estate broker's license. So I've inspected a lot of houses with an UFR ground. That was the common ground. Today it's a little bit different. The National Electric Code, as I read it, is going to want 2 ground rods. It could be an UFR ground and a ground rod, or it could be 2 ground rods that are at least 6 feet apart. Here's the point that I'm getting to, and it took me a long time to get to this point. Should you drive a ground rod, and run, usually the video recommends, or even a lot of the publications, a number 6 wire from your station, we'll talk about where that would connect, to that ground rod? And my answer is no, because it is probably too far from the main panel. The electric code wants everything back at that common point ground. If you drive a ground rod outside, you provided a different path to ground, and the electric code doesn't want that. If that driven rod is relatively close to the panel and you go from that rod with a conductor to a driven rod, and that one's connected to the main electrical panel, or in a relatively short distance, say 6, 8, 10 feet, connected to the main panel, that would be fine. But if it's on the opposite side of the house and you drive a ground rod, technically you're in violation of, as I read it, the National Electric Code. In some jurisdictions, they've adopted more strict regulations than the NEC. Some are real extreme. Even here in California, there are some jurisdictions where even the connections to outlets are tightly regulated, and in many cases, it's a good thing. For example, in some jurisdictions, you can't take an electrical outlet and poke in the number 14 wire on a 15 amp service. They want it to go to the screw. So this is the typical plug that you would see maybe on your computer or the power supply for your ham radio equipment. Sometimes these are called stabs. Whatever you call it, we'll call them prongs if you want. This prong is the ground. It's the longer of the 3. The one on the left is the neutral. It's can be vertical for a 15 amp outlet, can be horizontal for a 20 amp outlet at 120 volts. The one on the right is the hot, and that one's usually smaller than the neutral one. So you've got a hot, a neutral, and a ground. Ground is the green wire, the hot is the white wire, and the neutral is a white wire, and the hot is the black wire. And when you plug into an outlet, those 3 wires wouldn't necessarily be green. Probably doesn't have any coating on it at all. Goes back to the main panel from your receptacle. The reason for the two lines back to the main panel is it's a redundancy in the ground system, so that grounding system, again, if there's a failure, they want to make sure the equipment is grounded. Real quick, in building my station here, I went to the extreme to test what I really already knew, because I had been on the air for 56 years, and in my prior station I had no connection to a ground rod other than the electrical ground. So for safety purposes and as a test,
The room is lined with foil, aluminum foil on 3 walls. On the 3 walls is 2 strips of this copper. And this copper then runs around the room, one on top of the other, so I have about 6 inches of this stuff. Comes out of the wall and connects to a copper pipe that's underneath the desk, a 3/4 inch copper pipe. Okay, here's the underside of my desk, and there's the copper pipe that runs under the desk to the 3 legs. It's an L-shaped desk, and that copper pipe is in turn connected to grounding straps. There's one there that lead to a 1-inch copper pipe. Then each piece of equipment, there's one that's I've not yet connected or hook up to that kind of a braid thing. And the braid is attached mechanically to the pipe with a clamp. So I put everything on that pipe that I could. This is an A/B switch to choose between 2 transceivers. There's a strip with 12 volts on it, and I've got a meter to read the 12 volt. The AC terminal strip, it's got a switch on it. That box is, I know it's hard to see, but that's the one of the relay boxes, so I can select various antennas, and that heads outside. That cluster is watt meters and other devices to sense RF before it does go outside. And again, it's connected to the frame of the desk using that copper pipe. It's pretty messy wiring, but that's the best I could do, I guess. So everything is connected to that copper pipe, and that in turn connects to the copper strips that lead to the copper pipe that goes to the main electrical panel. So each piece of equipment has this connected to the back of it, goes to that pipe. What I'm trying to accomplish is keeping each box at the same potential. Could be a half a volt rather above ground, could be 1 volt above ground, but each box is going to be at the same potential so that I don't end up inadvertently getting shocked. We'll continue this discussion in the next video, and we'll talk about RF grounding, and in particular, when questions come up about RF and the audio, what causes that, and the answer is pretty simple. Oh, before I forget, in one of the videos from an expert, he recommends that, back to this plug, that to stop ground loops, you cut off this pin so that you don't have that ground connection. That would be a violation of the building code, and it isn't safe. So no matter what that guy says, don't do that. Keep everything grounded. Safety. All right, this should generate some questions and probably some emails. Go for it. Let me know what you think. If you have a question, post that below. If you like this video, give it a thumbs up. If you do a thumbs down, give me an explanation. Tell me what you'd like to see done differently. In any case, thanks for watching. Please subscribe. I'm Jim, W6LG from Rockland, California. 73, and stay safe.
Good evening, everyone. Hope everyone's having a great, blasting day. Turn off my phone here. Not sponsored, but bubbly. Oh crap, let me get the chat going. Hang on one second. Here we go. Perfect. Hope everyone's day and evening is going well. I'm gonna move this over to right here. Oh, never mind, I'm not. Am I? There we go. Okay. Yeah, we are. Okay, so this stream probably gonna be going over some of the things that I wish I knew as a technician. If you guys have any questions, I will be able to answer them. I will, to the best of my ability. Thank you, Adam. Yes, Deet. Of course, you gotta have that shirt, you know. Let's see. I'm gonna drag this over to here, actually. I'm trying to set up my computer right now, so I can see y'all and OBS at the same time. Gotta make this... because I only have my computer right now. I don't have my big monitor right here open. Let's see. Yeah, so let me go over some things I wish I knew. So let me open this. So we can go over the first thing. That is, the one thing that I had when I was a technician was like, how the heck do you get onto a repeater? Because like I read the books and all, and I'd be like, how do you get on a repeater? So I can show with the Baofeng here. So I thought repeaters were always one of those things where you would tune to a frequency and then you would just say your call sign and it it makes sure that your call sign is in regulation, that you're able to go in that frequency, and if it is a real call sign, and then it'll let you in and you can do some CQ stuff. That's not what it is at all. I later found out that you can program it's not just a frequency. You have to program polarity, you have to do offset, tone, all that good stuff. So I didn't know that at first. I had to change that. And then you don't always have to put your call sign in first. And then I didn't know that there was tails, that there was, that actually it's improper to call CQ on a repeater. You should never do that. It only should be simplex. So I really wish I knew that so I could get into repeaters faster. Also chirp, holy cow. That came in handy because I used to manually program on the Baofeng. And that was not fun at all. Actually, I'm on VHF. There we go. That was not fun at all. It took a while to do on the Baofeng, but then once I found Chirp, I could program it from my computer into my Baofeng, which was really nice. My second thing is how to program Chirp. So that wasn't too big of a problem since I used ChatGPT and it helped. It took some time because I had to learn what offset was, polarity, and all that good stuff. Chirp wasn't too bad. My third point, don't be scared to transmit. That was a really big thing. And actually today I met my first Morse code contact operator. We met up November 4 Tango uniform. And that was a blast. The thing that I was scared with was with the Baofeng, at least frequency modulation, was calling CQ. I eventually got comfortable with it. Made a mistake though, calling CQ on a repeater, and some guy got mad at me actually. Not really mad, he was just called me out for it. And then my first Morse code contact experience. Yeah, Mike Fright it's very real. That's true, Adam. my Morse code experience when I first started to like call CQ, that was fine. That was fine to call CQ, but once I found someone on the air and I sent out my call sign to them, that was a scary moment because I was like, they could say anything to me and I wouldn't be able to translate. But I had my USDX with me, orange and blue knob, and so it had a little decoder on it, and luckily N4TU was 599, so my transceiver decoded it very well. I used 100% of that for the decoding, 0% of my brain, except for the 7.3s and DD, you know. So that was a good blast. It's a little scary, but people are really nice in the community, and you shouldn't be afraid. Definitely would transmit as fast as you can when you get comfortable. And then one thing that I've learned in my Morse code experience really, really fast was power is not the solution. I remember with my USDX, I used to get Florida a lot, New York. I would get all these states with just 5 watts QRP of Morse code, and I mean, going to 20 watt radio definitely helped and changed, but it isn't always the solution. It's always propagation. Now 20 watts to 100 watts will be a change, considering of an amplifier and new radio, but it's not always the solution. I remember a story of when someone was, there's a 40 meter net, and so there's this guy who in Florida who was transmitting QRP 10 watts for single sideband, and he actually, it was 5 watts, he said, and he hit from the like South Florida up to New York, which is crazy, and he was 599 also. So propagation is everything, man. Propagation. What is the propagation today? One second. Forrest commented on a video. I always gotta check up on that. Hope everyone's day is going well so far. Who's joined the chat or live stream? One second. I'll look at that later. Well, not much to talk about now. Maybe back to the repeater stuff. Echolink is amazing, by the way. When I first discovered it, because on Wednesday nights I hit Echolink with a net down in South Carolina, which is really nice. I've talked on the air a couple of times. Oh, I don't know what else to talk about. I'm bored now. I don't know if I show chirp. Ever run into any sad hams? How did you handle this situation? Sad ham radio operators. Sad. I have... sorry, ESPN. I've never personally run into a sad ham radio operator. Single sideband, you can't really hear it more good. So single sideband, I remember my first single sideband, this guy was going rapid fast because he was POTA up in Canada. I've never encountered someone sad. Just never heard like a sad voice before. What about you, Adam? Sounds like you have a story about something like that. Let's hear it. There's the NOAA weather report. Can't tell if Adam's typing up a storm in here. Might be. Ran into a couple of them on the local repeater before. Best thing to do is keep it positive or end the conversation as quickly as possible. What do you mean by sad hams? Like people who are depressed or like people who are being boring or having a boring time? Cause that sounds strange. Actually, wait, I have my, No, people who are mean or obnoxious or standoffish. Sad ham is basically a ham gatekeeper. Okay, sorry, I didn't, yes, I have. Yeah, there was that one guy I was talking about when I was calling CQ in a repeater. And it happens on YouTube. On YouTube comments a lot too. Like a post today, someone was saying that I look extremely skinny, which is funny. I really don't care. I mean, I care if I do, and I've been told that a couple times, but I don't care about those people. Kind of just got to blame them out. But I was calling CQ on a repeater, and I mean, it was okay because my microphone was terrible. It's one of those cheap Baofeng like microphones, and he was like, "Dude, you sound like you're coming from the bottom of a barrel." I was like, "All right, thanks, man." From that point, I turned off. I unplugged my microphone. I went to the PTT on the handheld, and he said I sounded much better. So I knew it was the microphone, and I knew he was trying to make a point. So that's the closest I've gone to like a mean, obnoxious ham radio. Standoff-ish. I mean, like when air traffic control tower gets like rude to a pilot or vice versa. It's interesting. I'm trying to think if there's any been other. Because if it is, it's gonna be more. It's gonna be voice. I mean, I've heard sometimes on the net operations that go on our local net at. Yeah, I'm actually I actually work out a lot. I just need to eat more protein. I'll say that. Thanks, Adam. But the local net, I've heard some people get mad when Sid, he's like 70 years old. He's a net operator. He can't get some call signs. You know, it's okay. And so I've heard. Oh no! Wait, hang on. Was it? I swear, it was something else. I remember there was one specific either net operation. It was probably net because it was coming from the Baofeng. And this one guy got like really stern when he couldn't hear. When the net op couldn't get his call sign right. I feel like that happens with Morse code too. When like you ask for the call sign like 3+ times. I feel like they have like a madness in them, but at the same time, when people ask for my call sign like 3 times, I'm like, it's cool because they're still learning, you know, just like me. Oh, good old Morse code. Good old Morse code. What is the furthest place I've been able to communicate with... Don't worry, I have a dummy load and I'm not actually transmitting. What's the furthest place you've been able to communicate with someone from? So that would be high frequency Morse code. The farthest I have gotten, I thought it was England, but it wasn't. It was a guy from Chile, way south of Chile. I think he was 4,900 miles. Let me double check. World Radio League really quick. I think it was 4,900 miles. Let's see. And actually, just for y'all, let me. Okay. The farthest I've gotten was 4,970 miles. It was X-Ray Quebec Tree Whiskey Delta. He was from Chile. My second farthest, is it England or Argentina? 3,900 was Argentina, 4,800 miles, and then England, which was 3,960. So those are the farthest I have gotten. It's really nice. It's only Morse code too. My farthest with my... Actually, that's a good question. The farthest with frequency modulation, and with frequency modulation, I was down in Hilton Head, South Carolina, so it counted down there, because I hit someone down there. My farthest with frequency modulation is, let's see, that's 18 miles, 17, okay, so my farthest with frequency modulation is 18.7 miles. And then for single sideband, sorry, I keep closing it because I keep forgetting. Single sideband, let's see. I've only have 7 single sideband contacts. I don't do much. 1,200. Yeah, 1,200 is miles. Victor Echo 1, Mike Delta Foxtrot. Wiz Nation, welcome to the stream. Hope your day's going well. I need help with my test. Do you... Oh, you need help with your ham radio test? Oh my gosh. See, I was going to make a series on a course for ham radio. Should we start that today? And just go over... I think that would be a great idea, actually. Because I need to review some. What test is it? General or technician? You have 2 of the same radio. I have the G90 USDX. Do you know if people from other countries have to translate their language to English and then Morse to learn? Yeah, so good question, Butter. So for ham radio, you have to know the English language. I've heard people talk in Spanish before, but maybe that's like inside country, something that's going on. Maybe that's more lawful stuff. But technician, okay, I'll get to that, Wiz. But you have to know English. And then the international, the UV5R, yeah, this is such a great radio. Then the Morse code aspect, you can actually, there's different Morse code, not aspects, languages. I've heard Indonesian Morse code, I've heard South American Morse code before, but I know the international Morse code language, and I think most operators know that. Hey Noah, welcome to the stream. Alright. I have not done this in a good bit, so it's probably a good review for me too. I better get some of these right though. I kind of memorized for the test, you know. I feel like most people do. But what I'm gonna do, because it's gonna be annoying if I do that. Okay, hamstudy.org. We can minimize this down to, I'm gonna put the chat like a great bit smaller and put it up here just for now. And then we're gonna expand this way. I'm gonna be kind of like out of frame here. Ugh, crap, this is a mess. I don't know. Yeah, there we go. That's okay. Cool. Just tell me if you can see the hammerstudy.org well. Can you guys just tell me if you can? Is this gonna troubleshoot, or is this gonna hurt OBS? Oh yeah, it does. Okay, hang on. Let's do this. That should be fine. Okay, cool. So, technician, so what do you need help with? Like, just going over questions, Wiz Nation? And also, there's like a 30-second delay from stream to real life, so your chat messages are going to come in like 30 seconds. So, sorry about that. Maybe I'll see if I can fix that. Yes, okay. Well, let's just go over there. Let's do study mode, and then oh, hang on. Oh, crap. Sorry, y'all can't hear me. I completely read those questions and forgot. Yeah, sorry. Yeah, I blocked it out because I was actually showing my email. Sorry. And my microphone was gone. Sorry. You need to take your test in 3 weeks? Okay, that's not bad. Oh, what score did I get on mine? So, technician, I think I almost got 100. I think I missed 2. And then general, I missed 4 or 5, I believe. Okay, so let's go somewhere over these questions. Oh boy. This is not going to be good, guys. I haven't done this in a while. What is the unit for capacitance? I'll let you guys take a guess. I'll wait 30 seconds. For me, I made 100 tech, missed 1 general. I got 100 on extra, like a boss. I think I'm gonna get my tech, or sorry, not tech, extra in the summer of 2026. Okay, what is the unit of capacitance? Volt. I think it's not volt. It's fraud. Okay. I thought it was volt. So it's going to be farad. Wait, is there a way to show? Oh yeah, so when you click on the I, it shows you why. Okay, so the basic unit of capacitance, the fraud, is named for the physicist Michael Faraday. So a volt is a basic measure of your unit of voltage. The ohm is for resistance, and the henry is for inductance. So your fraud will be for... your capacitance is going to be fraud. What factors affect the radio frequency exposure of people near an amateur station antenna? A, distance from the antenna to a person, frequency and power level of the radio frequency field, radiation pattern of the antenna, and all these choices are correct. I believe it's all of these choices are correct. I know it's distance from the antenna to the person. That's right, because why wouldn't it be? It's not an infinite distance. And the frequency and the power level of the radio frequency field. If you have a higher level of power, that's why you can't be too close to antenna when transmitting 1 kilowatt. And then different radiation patterns of the antenna can vary. Yeah. So, yeah, you guys can read that if you need to. What's going on in Discord? Yeah, so that's that. And honestly, for Wiz Nation, one second. Wiz Nation, I really recommend before you take that test, try to get 100%. Go through 100% of all these questions so you know what's going to be on the test. Because this is what's going to be on the test. A couple of these questions will be. Ham radio trivia night? Yeah, I think that would be best for all of us, and especially me. We can yo, what is going on in the Discord? Okay, whatever. I'll respond to those later. The Youth Network, RHR website editor. I'll look at that. That'd be cool. But yeah, definitely go through all these questions. 3 weeks is enough. I went through them in 1 week, so. Who's a... No, you're fine. I'm joking. Who is accountable if a repeater inadvertently retransmits communications that violate FCC rules? The control operator of the repeater, the owner of the repeater, the control operator of the originating station, both the originating station and the repeater owner. You might have to say boiler, what? B-E-U-L-E-R, boiler at times. Yeah, if we have a trivia night, I'm gonna have to study before that, because this guy just knows how to transmit Morse code and doesn't know the whole aspect of it. What got you into radio communications? KI7QCF for Forrest on YouTube. I saw some of his videos. Really thought it was cool, so I looked into getting a test done, and I did it. And then I got some radios and started to transmit on air. I thought it was sick. Mainly the Morse code aspect of it, though. Okay, I think it's... I don't think it's the owner of the repeater, because I own a G90 and I could transmit illegally on here, and it's not Yagzu's fault, but this is a repeater. So I'm going to say it's the control operator of the repeater. Oh, you think it's C? Of the originating station. Okay, interesting. Oh, repeaters run on automatic controls and thus do not have control operate. Oh, what am I thinking? Okay, yeah. So it's gonna be the originating station. Sorry about that. Yeah, the 30-second delay of the stream is a little bit much. I'm sorry about that, guys. Oh. What is the approximate bandwidth of a typical single sideband voice signal? I think this one is 3 kilohertz, if I remember. No, we smart. I think it's 3 kilohertz. I don't do much single sideband, but I think it is 3 kilohertz. Let's see. Yes, I knew it. It was 3 kilohertz. And you can tell that a lot once you do single sideband. You can tell. You'll see. Yep. What is a common repeater frequency offset in the 70 centimeter band? Oh my gosh. Guess what? I'm going to cheat. I'm going to go to a 70 centimeter band and look at the settings. 4, menu. I'm going to cheat on this. Repeater frequency offset. Okay, let's go to offset. But it's common, so it might not be this. I'm not looking at chat. Oh, great. The offset is 0000. Crap. Let me go to another. It's still 0. Well, I might need chat's help here. I think it's 500.